left with the correct answer. Or if you know what is going on, just go straight to the correct answer and then circle what is left. Okay. So the question tells us that a car is moving at a constant velocity. It's even in bold. Which of the following statements about the forces acting on the car is correct? 1, the net force acting on the car is 0. 2, there are no forces acting on the car. The weight of the car is equal to the normal force acting on the car. And then there is a non-zero net force acting on the car. Wow. So one thing we know is that for as long as a car is moving at a constant velocity, which means the V final is the same as the V initial. Let's start with option number 1. They're telling us that the net force, how do we calculate net force? F net is equal to MA. Okay, and we know that M is the mass, this is the acceleration. So literally, for as long as the velocity is constant, there is no change that is happening within the velocity. So which means our acceleration is going to be 0. We know that acceleration is given as the change in velocity over the change in time. Yes, time will be there, but then the change in velocity is going to give us a 0. So for as long as the acceleration is 0, which means the net force is also 0. So I feel like this option is the correct option. Okay, so I already have a correct option. So these ones, there are no forces, that's wrong. I mean, there's always a force that must push the car forward. Okay, and then there's always friction that must try to bring the car down. And then the weight of the car is equal to the normal force that is acting on the car. I mean, this is okay, this is true. But then we're talking on a car we're talking about a car that is moving. This is possible if the car is stationary and there's nothing else. And then there is a non-zero net force. No, this is wrong because we said the net force is 0. So option A would be the best suited for that. And then 1.2, a ball is projected vertically upwards. We ignore resistance. Which of the following statements about acceleration of the ball at its maximum is correct? Statements about acceleration is correct. So we know that for as long as the ball is projected back upwards, there is just one acceleration, which is G. It's more like the influence is just gravitational force, but in which direction? So gravity just acts downwards, regardless of the position of the ball. So acceleration is 0, no, this is out. G, now that the acceleration is G and then it's directed downwards, which is the correct direction, and it's G. G directed upwards, no. G directed horizontally, no. G will always be directed downwards. Whether the object was vertically up or vertically down, regardless of the initial direction of projection. Then 1.3, we have a graph that is not to scale, the relationship between the gravitational force and then the mass and its distance. Okay, so this is the distance, this is the force. They are telling us that the magnitude of the force at a distance r is F. Which of the following statements is correct for the magnitude of the force X? Okay, so if the distance is now 6 times bigger. So what do you suggest? Okay. So from the universal law of gravitation, M1, M2 divided by R squared. So we know that if it is R, just capital R, this is going to be the force because F is going with capital R. Now what if we increase this to 6? So that's going to be G M1, M2 over 6 R but squared. So we know that 6 squared is going to give us 36 R squared. So if I exclude this, okay, I'll be left with just 1 over 36F. So this whole thing represents F. So 1 over 36F should be the correct option. Now that's the force. For as long as you increase the distance, the force must also decrease. So D is the best option for this. Then ball M, moving at a speed V to the right, collides with a stationary ball N on the smooth surface. Immediately after collision, ball M comes to rest. And then N moves to the right with a speed V. Which of the following about the collision is correct? 1, total momentum is conserved, and then the masses are unequal. So the first statement is correct. Okay, but then how do we tell about the masses? The fact that the speeds are the same after and before, because this is, one is at rest, the other one is moving with V. After the collision, this one loses the velocity and then just goes to rest, and then this one moves off. So there's no way that the masses are unequal. There has to be something unique. Chances are high that the masses are the same, because it's more like looking at balls of equal masses, and then this one carries the same velocity or carries a velocity V, and then this one just transfers the velocity to that one. And then this one moves off with the velocity. So the masses have to be the same for the velocity to be the same. So total kinetic energy is conserved and the masses are unequal. This is not making sense. I'm not at peace with it. I don't know. I'll see. Let's see. Total momentum and total kinetic energy are conserved, and then the masses of the balls are equal. I'll go with C. Why? Because of the masses being equal. But also D has masses being equal. Okay. Total momentum is conserved and total kinetic energy. So what sort of collision is this? It definitely has to be elastic collision. Why? Because it's going to be M1V plus 0 is equal to M2V plus 0. So momentum will be conserved. What about the EK? Same story with the EK. It's going to be M1V squared, and that's going to be M2V squared. Now, for as long as the masses are the same, it means so C is the best option, because this one is telling us momentum conserved, kinetic energy is not. So C is the best. Then 1.5, a small stone is dropped from rest and undergoes free fall. Which of the following below shows the correct gravitational potential and V and so on? A stone is dropped from rest, undergoes free fall. So we know that with the energy, if it is at the highest point, it's going to have EP max. And then at the bottom, where it reaches the ground or the surface, it's going to have EK max. So if it's EP max, this is going to be EK minimum. Now I say 0. Then if it's EK maximum, then EP will be minimum. So EK, okay, both graphs, that is that, starting from there, going that side, which is okay. This one and that, which is still fine, makes sense where the graphs are starting from. This and that, okay, this and that is also fine. So all the graphs represent the correct orientation of the EP max and the EK minimum and so on and so forth. Now let us look at some other aspect. Okay, so how will these graphs look like? So chances are high these graphs are not going to be straight lines, because the change that is happening within the energy is not uniform. So I'm going to cross this. I'm going to cross this out because it has a straight line. Let me just focus on just these two. Okay. So if the energy is being lost from the EP, is it going to be this much or this sharp? In other words, is it going to be an inverse proportion? Chances are high it won't. Is the EK going to increase exponentially? Which is correct. So we can see that these two have the same type of graphs. Actually, 1, 2, 3. The EK is just the same. So the issue is for us to highlight the correct E. So I'll go with option C for number 5. Then 1.6, the stationary passenger at a railway station listens to a train approaching at constant speed. So this is Doppler effect. Which of the following is correct for the sound of the approaching train that is heard by the listener? Okay. So for as long as the source is approaching, we expect the listener to get the most, the loudest sound. Okay, and if the sound is the loudest, which means it has to be a higher pitch. And for as long as the pitch is high, then what's going to happen to the frequency? Let's first look. So this one is out. And then the last option is also out. So that is lower pitch. Now, the observed frequency, since the source is approaching, should also be more, because you tend to hear more of the noise or the sound. So higher pitch, higher frequency, because pitch is how high or how low a sound note is. Then 1.7 particle P and Q, as well as R, have charge of 2Q, separated by a small distance R. Which of the following statements below allowed about electrostatic forces, FPR, which P exerts on R, and FRP, which R exerts on P, is correct? So we're being told particle P has a charge of Q, and then particle R has a charge of 2Q. They're separated by this. They want us to tell about the forces between FPR and FRP. Now, without even doing calculations or what, okay, we can start with that. You know that the force will be K, Q1, Q2 over R squared. That's K. In this case, we have a Q. We're going to have a 2Q over a distance R squared. So which is 2AQ, Q1, Q2 over R squared. Does it make sense? Doesn't matter. Doesn't matter. This is relevant. We know that if two bodies are being separated, the forces that will exist between them will be the same, but just in the opposite direction. So FPR must be the same as FRP. So this is out. I'll take this out as well. I need to have the same values. So we have this option and this option. So which one do we take? I'm going to go for the last option. Why? Because if P is experiencing a force as to Q, let's say the force will be in that direction, and then this one's force will be in that direction. Okay? The forces have to be the same, but opposite from Newton's third law. Okay, then 1.8, so the same thing applies to universal gravitation. So will be the charges. 1.8 is electricity, battery of EMF of that and that. Negligible resistance, there's an internal what resistance and so on. So which of the following combination about the ammeter reading will be correct when the switch is closed? Remember, ammeter reading is giving us the value of the amount of electricity that is flowing within the entire circuit. Okay, let's look at option A. Ammeter only reads the current in R1. This is wrong. Because remember this, where the ammeter is located, it's going to read the current of the entire circuit, which means this current that is passing through R1 and R2. I don't even need to Well, whoa, wait a minute. Why am I doing it like that? Let me read nice. They're telling us if the switch is open. Okay. If the switch is open, will it make any difference? Ammeter reads only R1. It's still wrong. Because the moment you open or close the switch, I mean there's a connection through R1. It's not a big deal. Only thing is that there's just an alternative path for the electricity that side, or even a short circuit. Okay, so that is wrong because it's just not R1. R2 is part of it because the two tend to be in series, or I can say this whole part is in series with R2. So that is out. We're not going for that. Then ammeter. So this 7 is also wrong. Ammeter reads only the current in R2. That is wrong also because it's both. Ammeter reads the current in both R1 and R2, which is correct statement. Let's look at this side. If we close it, if we close this, ammeter reads the current in R1 and R2. No, it's not going to do correct. Because now, the moment you close the switch, there is no resistance here. There is resistance this side. So the current will just go through straight via that channel. So which means the only current or the only resistor to focus on is R2. I don't know, is what's option 4? R1 and R2, and then just R2. So option D is the best. 1.9, the direction of an induced current in a coil of a generator depends on ... The length of the coil, the speed of rotation, direction of the magnetic field, the strength. But this is out. Does that make sense? 1.9. Saying it's out. Why am I saying it's out? Because it just stands out compared to the rest. Okay. How does the length influence direction? How does speed influence to? Doesn't. How does the strength of the field influence? No. So all these ones will just work on the amount of induced current or induced EMF. So see the direction of the magnetic field. That will tell us more about the direction of the induced current. Okay, then 1.10, the work function of a zinc is greater than that of magnesium. Which of the following statements about threshold frequencies is correct? So remember, threshold frequency is just the minimum frequency needed to eject an electron from a metal surface. So the threshold of zinc is greater. So if zinc is having a greater work function, remember, work function is HF0. So if the work is greater, which means even the frequency will be greater. So zinc than that of magnesium, that makes sense though. Makes sense. Threshold of zinc is smaller, no, both, no. Threshold of zinc and that are independent, no. So A would be the best. Okay, let's move on to question number 2. Okay, this mechanics now. A person pushes a lawnmower of mass 15 kilograms at a constant speed. Pay attention to this constant. So I know that the mass is 15 kilograms of a flat surface with a force of 90 newtons. So force applied is 90 newtons. And then it's directed along the handle. The handle has been set at 40. Okay, the horizontal, refer to that. And then they want us to draw a free body diagram for the lawnmower. Free body diagram for the lawnmower. So when I look at the lawnmower, I can see that this force applied is in that direction, which can still be translated to that sort of direction. Then we have the weight We shall have the normal force. And then is there friction? Definitely there has to be friction. Definitely, because it's grass. So with what I'm going to do, since it's 4 mass, so I need a minimum of 4 forces. So I can indicate my N, and then I can indicate my weight. I can indicate my F friction, and then the force applied, since it is just in that direction. So in most cases, we dislike components of forces, just want the forces themselves. Then 2.1.2, why is it correct to say that the moving lawnmower is in equilibrium? Okay, what would be the explanation? This for 1 mark. So we could say that it's in equilibrium because the lawnmower is moving at a constant speed. And for as long as it's a constant speed, the net force is 0. The left-hand side is equal to the right-hand side. The force being applied, which is just a component, should be equal to the frictional force. So we can say that it's moving. Okay, it's moving at a constant speed. Moving at a constant speed. Thus the acceleration. Thus the acceleration is 0. Okay. And then they want us to calculate the magnitude of the frictional force acting between the lawnmower as well as the grass. Okay, so since we already know that it's moving at a constant speed, let me just try to break this down. If this is a 40 with a horizontal, which means this is also 40. Okay, if I try to resolve this applied force into components, it's going to be in this sort of direction, down and okay, so it's going to be F, the sine of 40 is going to be F, cos of 40. So looking at the number of forces that are acting on the lawnmower horizontally, I'll only have, I can start by saying F net is 0, or F net is equal to MA. Then my F cos of, it's fine, I can say cos of 40 should be equal to my frictional force. So that's a 90 times the cos of 40. Okay, so I put that into my calculator. I end up with 68.94. Okay, 68.94 newtons. Since the direction of motion is just horizontal, then we focus on the horizontal component. Okay, then the next part, they're telling us that the lawnmower comes to a stop. Okay, calculate the magnitude of the constant force that must be applied through the handle in order to accelerate the lawnmower from rest up to 2 in a time of that. So we have our V initial as 0. The velocity with which the lawnmower is moving is 2 meters per second, and then within a time of 3 seconds. Assume that the frictional force between the lawnmower and the grass remains the same as 68.94. What is the question asking for? Magnitude of the constant force that must be applied. Okay, so that does not take away, what do you call this thing? It does not take away the 40 degrees. at which applied force is acting. So we can start by determining the acceleration of the lawnmower itself, okay? We can say that our V final should be equal to V initial plus A multiplied by delta T, okay? So our final velocity, if it's a 2, the initial is 0, because they told us that it's moving from rest, plus now the acceleration multiplied by the 3 seconds. So when I divide both sides by 3, my acceleration becomes 2 over 3, which is a 0.6, I can say 7 meters per second. Okay, so that would be just the first step. Then if I apply, where should I write this? Let me just jot it here. If I bring in the F net is equal to MA, what I need is the constant force, which is F. But we know that the horizontal component has to be F, the cos of 40. So that's what I'm going to use. I'm going to say F applied minus my frictional force should be equal to the mass of the lawnmower. They told us the mass, which is 15 kilograms, okay, multiplied by the acceleration that we just got up there. So this is going to be F applied, the cos of 40, minus our 68.94. Okay, should be equal to 15 multiplied by, let me use 2 over 3 straight away, just to avoid the decimals. So this is going to be F cos of 40 is equal to, that's going to be a 10, because by 3, 1 by 3 is 5. So 10, when I add that, I'm going to have 78.94. And then when I divide both sides by the cos of 40, so 78, okay, divided by the cos of 40, I end up with 103.05 newtons. So that should be our force applied. All right, so that is that. That is that with that question. Then 2.2. A planet Y has a radius, okay, of this much, and then a 10 kg mass weighs 20 newtons on the surface of planet Y. I calculate the mass of the planet Y. Okay, so one thing we know about Newton's law of universal rotation is that the force that is experienced between the bodies must be the same. Okay, so regardless of how big or how small it is. So if a 10 kg is experiencing this much of force, which means the 10 kg must also apply this much of force onto the planet Y. So from F is equal to Gm1, M2 over R squared. So which means my force is going to be 20. The question wants the mass. So if I called my G to, no, I know my G from the information table, 6.67 times 10 to the negative 11. I'm multiplying it by the 10, multiplying it by the mass of Y, and then they told us the radius is 6, that's just going to have 6 times 10 to the 5. Everything must be squared. Okay, so I can simplify the right-hand side, can exclude that my. So 6.67 times 10 to the negative 11 Okay, I'm multiplying it by 10. And then I'm dividing everything by 6 times 10 to the exponent of 5. That's squared. That's giving me 1,85. So 8 times 10 to the negative 21 my. And then I have to divide both sides by that. So I'm going to say my 20. Let's just have that. And then we're saying 20 divided by my answer. I'm getting 1,079, so which is like 0.8 times 10 to the 22 kilograms. Okay, guys, so that is question number 2. Then question number 3, we're being told that a ball is thrown vertically upwards, okay, with a velocity of v from the edge of the roof that is 40 meters tall. The ball takes 1,53 seconds to reach the maximum. Okay, so might is 1,53 seconds. Ignore that. Can we define free fall? So free fall is just the motion of an object under the influence. Okay, under the influence of gravity, or you can just say gravitational force. Then 3.2, calculate the magnitude of the initial velocity v. So it takes 1,5 to reach the maximum. So we know that at maximum height, okay, I'll say height max, the final velocity must be a 0. So I can use the first equation of motion. V final is equal to V initial plus the A delta T. So my V final, we say it's a 0. V initial is what I want, but we know that G is going to be 9,8 multiplied by 1,53. Now, the direction that you use for the G will matter. Let me take downward to be positive, and since we're going up, I'm just going to use negative, okay? So then I have 0 is equal to V initial minus 9,8 times 1,53. That gives me 14,99. Then I'll move it that side. So my V initial is 14,99 meters per second, which is more or less the same as 15. I don't know. I'll just leave it as that. It's fine. Then 3.2.2, calculate the maximum height that is reached. So we can still use the effects that we have, that the delta T is 1,53. The V final is 0, and then we're looking for the displacement. So you can use, we can choose to use the V initial. Either way, we have to use the V initial, because if I look at my displacements, V initial multiplied by time plus a half G delta T squared. Either way, there is V initial. If I use V final squared, it's going to be V initial squared plus 2 multiplied by G delta X or delta Y. So either way, so let me use this second and say that my delta Y is going to be the V initial. My V initial is 14,99 multiplied by the 1,53. Now I'm going to use minus 1/2 times 9,8 multiplied by 1,53 squared. Now you can use a plus, yeah, but then the value of the sign next to the G should be a negative. That's if we're using the same direction as my soap. So 14,99, okay, times 1,53 minus 1/2 times 9,8 times 1,53 squared. I'm getting 11, something. 11,47 meters. So that is the height, or the maximum height, 11,47. All right, so that is 3.2.2. Then 3.3, can we take the edge of the roof as the reference point? We need to determine the position of the ball relative to the edge of the roof after 4 seconds. So from this point of projection, if this is our 0 line, that's what it means to take it as a reference point. So after how long, or after 4 seconds, what will be the position of the ball? So I can still use the same formula of the delta y, but where there's time, I can just use the 4 seconds. Is that okay with people? Good. So we said we're using the same formula. So delta y is equal to V initial times delta t plus 1/2 G delta t squared. Okay, my delta y. So let me just correct this, guys. It's supposed to be A. Let me even correct this. It's supposed to be A because A is the formula. We don't have G in the formula. So let's write the formula down. You get that mark. And then the substitution, then you replace A with a G. Okay, so V initial, we said is 14,99. Now we're looking at 4 seconds plus 1/2. That's going to be negative 9,8 times 4 squared. Okay, if I punch that into my calculator, saying times 4 plus 0,5 multiplied by negative 9,8 multiplied by 4 squared. That gives us negative 18,44. Okay, so one thing we need to know is as long as an object moves from the point of projection, reaches maximum and comes back to the point of projection, we call that a displacement to be 0. Then afterwards, this 18,44 is just the distance below the building or below the reference point. So we interpret the negative sign by telling us the position is 18,44 meters downwards, or we can say below the top of the building, below the edge of projection. Edge of projection. All right, then 3.4, will any of the answers in 3.2 and 3.3 change if the height of the building is now 30 meters? Choose a yes or a no. Now, looking at what we've been working with in 3.2 and 3.3, I mean, we've not applied this height in any way. Okay. So the fact that this 40 is not in any of our calculations and it does not have an effect on the maximum height that the ball must reach, I mean, there's not going to be a change. Because remember, we are ignoring air resistance. I mean, if air resistance was there, then we would say that yes, it might have a change. But since air resistance being excluded, our answer is going to be a big no. Okay, it's a no. And what is the reason? It's saying that motion of the ball is only independent. Should I say independent or dependent? Let's use dependent. dependent on initial velocity. It does not depend on the point of projection or what. Okay. Then someone says, will that give you 3 marks? Yes, to give us 3 marks. Remember, we took a stand to say it's a no. And then our explanation can give us the other 2 marks. All right, then question number 4. This is momentum. We also looked at it. They're telling us that a soccer player kicks the ball of mass 0.45 kilograms to the east. And then the ball travels horizontally at the velocity of this. Okay, I'll just write this there, 9 meters per second, along a straight line without touching the ground, and enters the container lying at rest. I mean, the soccer player should be a star. That's magic. Okay, then the mass of the container is 0.2 kilograms. And we know that its velocity is at 0. Then okay, maybe this 9 is here. Okay. The ball is stuck in the container after the collision. And then the ball and container now move together along a straight line towards the east. So the direction is still the same. Okay. Then they want us to state the principle of conservation. Okay. So remember what we said? That in an isolated system, okay, any isolated system, the total linear momentum stays constant or remains constant or stays the same or is conserved. Can use those things. And saying an isolated system, total linear momentum remains conserved. Okay. And then 4.2, they want us to calculate the magnitude of velocity of the ball and the container immediately after collision for 4 marks. So let's just use the principle of conservation. So I'm going to say that if I get the mass of the ball, velocity initial of the ball, plus the mass of the container, velocity initial of the container, must give me the mass of the ball plus the mass of the container multiplied by the combined velocity. Okay, so this is what we want. So the ball is 0.45. Okay, they told us it's moving at 9 east. Plus the mass of the container, it was 0.2, but initially it was at rest. This gives us 0.45 plus 0.2 times V. I'll say V final, it's fine. So this dies out to a 0. Then I'll be left with 0.45 times 9. That gives me 4.05 is equal to 0.65 VF. Then divide both sides by 0.65 over 0.65. That cancels that. So my VF is something like 6.23 meters per second. Okay, so that is 4.2. And then 4.3, determined by means of statistical calculation whether the collision between the ball and the container is elastic or inelastic. So remember what we said. As long as a question of this nature comes, the first thing you need to go for is the kinetic energy. Okay, so go calculate the EK before, and then we also look at the EK after. So for the EK before, I'm going to say it's a half mass of the ball, velocity of the ball squared, plus a half mass of the container, velocity initial of the container squared. This is initial. When I do my substitution, it's going to be a half times 0.45 times 9 squared. This is going to die out because the initial velocity is a 0. So that's going to be 0, 0.5 times 0, 0.45 multiplied by 9 squared. That's giving me 18,225. So this is energy to be in joules. Then let's get the EK after, which will still be the same as a half. This is now going to be the combined mass since the two are moving together. Mass of the ball, mass of the container multiplied by the velocity that we got. So it's 6,23. We square that. Okay, so that's going to be a half. Mass of the ball was 0, 0.45, but we saw the combined mass. Why am I stressing myself? Which is, we said 0, 0.65 multiplied by 6,2 squared. What we get? Okay, multiplied by 0, 0.65 multiplied by 6,2 squared. I'm getting 12,49. Remember, this was 18,225. This is 12,49. So just by looking at this, I can already see that the kinetic energies are not the same. And the fact that the kinetic energies before and after are not the same, therefore the collision is inelastic. The reason EK before is not the same as EK after. Okay. Question number 5. Here we saw also energy. So I believe this will be the last question. Then we go back to the guideline. Okay, a 70 kg box is initially at rest. Okay, at the bottom of a rough surface. This word is important. It's even in capital letters. At an angle of 30, okay, to the horizontal, the box is pulled up by means of a lightning eccentric string held parallel to the, okay, force applied is 700, good. What is the name given to the force in a rope? So all ropes, all strings, they usually possess one force, and that is the tension force. So the force there is tension. Please don't tell us force applied. It's the tension force. Okay. Then 5.2, give a reason why the mechanical energy of the system will not be conserved as the box is pulled up the plane. So the reason for this, okay, why energy is not going to be conserved, because the surface is rough. I mean, as you're trying to pull it up, friction is trying to pull the box downwards. So in that way, you'll have to cover up for the losses and all of that. So we can say that the presence of friction, the presence of the frictional force, we can also say the tension in the system. Both tension and frictional force will have an effect on that. Okay, then the box is pulled over a distance of 4 meters. So from here up to there is 4 meters. And then the kinetic frictional force between that is 178,22. They want us to draw a free body diagram as the box, or for the box as it moves up the incline. Okay, so with this, before I even draw the free body, just look at the forces that are going to be acting on the box, the way it is. So we know that this is going to be the force applied. Whenever we have an incline, it's automatically that the FG parallel will always act downwards. Okay, remember we said we don't want components, but I might be forced to put it. So frictional force is also going to act downwards. And then we're going to have the weight and then the normal force, the N up. How many marks is it? It's 4 marks. So if we can have just 4 forces, that will be good. Okay, so we're saying force applied, and this force applied is in the form of the tension. Okay, and then we can also have the frictional force, which is F, and then we say the normal force, and then we can have our weight. which is also okay. Alternatively, you could have the normal force, the tension, even this component, Fg parallel, because it's acting downwards anyway. Okay, because our focus is just going to be the motion along the incline. So you could also indicate it the Fg parallel. Okay, so that is the free body diagram. These two have to be in a straight line. I don't know why mine is Q. I know it's a weekend, but good. Okay. Then 5.4, they want us to calculate the work done on the box by the frictional force over the 4 meter. So from our formula page, we know that the formula for work done do we have it here? It should be here. So this formula here is what I'm going to use. Okay. So we're going to have W, work done by the frictional force. I'll just call it WF, is equal to F multiplied by the delta X and then the cos of theta. So my frictional force is 178.22 multiplied by the displacement, which is 4 meters. And then I'm going to use the cos of 180. Why are we using 180? We know that the object is moving up the incline. Okay. So up the incline will be our reference point, which is a 0. But then frictional force is acting on the opposite, which means it's acting within an angle of 180 in the opposite direction. Okay. That's why I'm using cos 180. So I punch that into my calculator. That's going to be 178.22 times 4 the cos of, we said 180. That's correct. So that's going to give us negative 712. Okay, 88. Remember, this is work done. Work done is measured in joules. So the explanation for the negative sign is just the direction. It's acting in the opposite direction. All right, then 5.5, use the energy principle to calculate the speed of the box after it has moved 4 meters up. I need space, I need space. Okay, let's just explain this nicely. So, one thing we know about energy principles. Remember, we said we have WNC is equal to the change in EK plus the change in EP. But we also say that the net work done should be equal to the change in the kinetic energy. Okay? So I think I can use this one for me. The net work done should be equal to the change in kinetic. So in that way, I'll have velocity involved straight away. So let me just scratch this out because I need space like badly. All right, so for the network, since the direction is up and there's just one force that is working up there, so I'll look at the, let me not use that. We're saying net is going to be the work done by the tension, okay, plus the work done by the frictional force, and then the work done by the Fg parallel, because from our free body we saw that Fg parallel and F frictional force are acting in the same direction. Okay, let me just get this first. So work done by the tension is going to be 700 multiplied by 4 multiplied by the cos of 0, since it is acting in that direction. And then the work done by the frictional force, we already got it as 712.88. Then plus the work done by the Fg parallel, we know that the force FG pi is giving us the mg sine of theta. Okay, so this theta is this angle of inclination. The cos theta here has to do with just the direction of motion. Okay, so I'm gonna use this formula and say the mass is 70 times 9,8 multiplied by the sine of 30. So that's just the force. I'm multiplying it by 4 and then the cos of 0. So if I try to substitute this or punch that into my calculator, first, so 700 times 4 cos of 0, I'm getting 2.8. Okay, negative 12.88 plus 70 times 9,8 sine of 30. And then I'm multiplying by 4 cos of 0. So this is giving me 3459. 3459,12. So this is just the network. Okay, so we say network must be equal to the change in kinetic energy. So the change is going to be a half m. It's going to be V final squared minus V initial squared. I think that's how I can best put it. Okay, so I'm going to equate all this to 3459,12. We know that the mass is 70, so a half of 70 is 35. Then I'll divide both sides by 35 and then replace all the other information. So what do we want? We want the initial velocity. Calculate. Calculate the speed after it has moved up. So which means we need the final velocity. Initially, this thing was at rest. If I am not being forward, is at rest. Perfect. So which means the initial was a 0. So which means our VF squared should be equal to this divided by 35 and then under the square root. Okay, so let me divide this by 35 because a half of 70, I'm getting 98,832. And then I need to find the square root on either sides. All right, square root is giving me 9,94 meters per second. Okay, 9,94 meters per second. So guys, that's how we would have obtained those 5 marks. I don't know if there are other options of how to get that, but this is how I'm getting mine. This is how I'm getting mine. Someone is saying, let's go back to the calculations and just confirm. Yeah, there's a problem. There's a problem. Okay, let me just, because I've seen my mistake. So this is going to be wrong. Same applies to that. So the wrong thing is this part. Okay, remember we said it's 70 times 9,8 sine of 30. I'm multiplying it by 4 and then the cos of 180. Why are we putting the cos of 180? Because it's also acting in the opposite direction. Thank you for that. So this is also not in. This is also out. So I'll have to redo it again. So 700 times 4 cos of 0. We said negative 712.88. Okay, plus 70 times 9,8 sine of 30 times 4, and the cos of 180. I'm getting 715. Okay. Comma 12. 715,12. I'm gonna divide it by, we said, the 35. This is going to give us 20. So VF squared is 20,432. Because remember, this is a 70, then simplify. So the square root of that, square root, I'm getting 4,52. 4,52. That is meters per second. Thank you very much. Okay, then we move on. So we have to erase this also. We say it's 4,52. Then when the box is 4 meters up the incline, the rope breaks, causing the box to slide back down the bottom of the inclined plane. What will the total work done by the frictional force when the box moves up and then down the incline to the bottom? Okay. So looking at the work done by the frictional force, remember we got it as negative this much. This was just to move up the box, which means even when the block is sliding down, the same amount of energy will be done because it is still the same surface, the same coefficient and everything. So I'm just going to say 712,88, and then I'm just going to multiply it by 2. So 712,88 multiplied by 2, which gives me 1425,76 joules. But that will be negative. All right, so that is question number 5, and that is the work, energy, and power. All right, then we go back to our guideline where we have the next topic being Doppler effect. So Doppler is a grade 12 topic, which is not carrying that much of marks. So all we need to know is at least state Doppler effect in words. Okay, and we're being told that it is the change in the frequency of the sound detected by the listener because of the sound source and the listener having different velocities relative to the medium of sound propagation. So find sweeter words, or you can just use exactly this. Okay, but for as long as we have words like relative velocities, okay, then the difference, you said change or difference in the frequency by the listener because of the sound source and listener having one. So we just need to know also how to explain using illustrations the change in pitch observed by the source as it moves towards the listener or away from the listener. Okay, this could be explained through, let's say, some drawings. Okay, we've seen cases where we have such circles that are moving towards one point and then so on and so forth. And then you need to know when is it moving away, when is it moving towards, and stuff like that. Then we also need to remember this formula, the Doppler formula. Okay, so remember we have 2 signs on top and 2 signs down. When do we use which format? Okay, an example, if we're looking at the frequency of the listener, and let's say the object or the source is moving towards, so which means it's going to be V plus VL over V minus Vs times the frequency of the source. So why are we using plus and minus? Because we know that when the source is moving towards the listener, we expect the frequency heard to be bigger. And for us to have this right-hand side to be bigger, there has to be a plus on top, and then the bottom has to be smaller. Then if it's moving away, it's just the opposite. Just switch the signs and then they're around with that. Then we need to look at the applications of Doppler effect and which machines, like in the Doppler flow meter. What is the use of the Doppler flow meter? We also have the radar machines that are used to detect the speed of cars and so on and so forth. Yeah. Then still under this, we need to also do explanations with the red shifts and the blue shifts and all of that. Okay. Then the next topic, I'll just combine the 2. Okay, from here, we have electrostatics. So this was mainly done in grade 10 and 11. So there's nothing new to add on to that. So whatever knowledge we gained in grade 10 and 11 is basically the same knowledge that must be carried on to grade 12. Okay. So we need to know how to state Coulomb's law. That the magnitude of electrostatic force exerted by one point charge to another is directly proportional to the product to the magnitudes of the charges and inversely proportional to the square. So this and the Newton's law of universal gravitation are just the same things. But as long as you get to know one, just change that side from masses and then bring charges here. The rest is history. Then 2, you need to solve problems using this formula. And then we said we're only going to use 3 charges. We can't go beyond that. Then you also solve problems using this, as long as we're looking at 2D. So 2D is basically, okay, 1D is where the charges are just in one straight line. 2D, 3 forces, but maybe they are forming some sort of a rectangle or a vector kind of drawing. All right, then electric field, you need to describe, know how your definitions work. Regional space in which an electric charge experiences a force, or regional space in which a charged object experiences an electric force. Direction of this is the direction that a positive test charge would move if it was placed at a point. How do we draw electric field lines? Let's say with a single point charge. We know that with positives, the field lines or the arrows must be seen moving away. Okay, and then with the negatives, the arrows should be seen entering. Okay, and then if you have, let's say, 2-point charges, just need to know how they work. The opposite charges will always attract each other, and then the negative charges will repel. Then for as long as the charges have the same magnitude, just pay attention to the number of field lines, and also know that these field lines do not cross each other. Okay. Then they said we're going to restrict this to just charges with that are identical in magnitude. Okay, beautiful. Okay, define what electric field at a point is. Okay, it's a point electrostatic force experienced by unit positive charge. So just know how to define that and also the formula. How to solve problems using that and calculate the electric field at a point using this formula. So this is derived from that. Yes, we're saying the force, which we said was K, we're going to use Q, and then Q over R squared, and then you're saying you're dividing it by 1 over. So this cancels that. Then you're left with. So Q is just the normal charge, and then the small q is just the point charge. Okay, so that is that. Let's look at the sample questions and we see. Question number 6 in this case. They're telling us that a patrol car is moving at a constant speed towards the observer. Okay, so the scenario changes. It's moving towards. The driver switches on the siren when it is 300 meters away from the observer. Okay. The observer records the detected sound waves of the siren as patrol car approaches, passes, and moves away. Information is given on the graph. Wow. This is interesting. Okay, so approaching, probably around and then moves away. Does that make sense? Approaches, passes, moves away. All right, then they're asking us to calculate the velocity of the car. Okay, so if, I don't know, let me just, I love drawing so much. So if this is the source, this is the observer or the listener, they're telling us that the distance there is 300 meters. But we already have the frequency. Okay, the frequency is 932. So at this point, the listener is getting a 932 hertz of frequency. How do we get the velocity of the car? Which formula can we use? Formula can we use? Do we have the time? There's no time. What else do we have? Okay, yeah, we have this 10. Yeah, 10 seconds. So this 93 watts is going to last for 10 seconds, which means that this car, the vehicle, is going to move for 10 seconds before it gets to the observer. All right. So if I use speed distance over time, which is 300 over, which is 30 meters per second. I don't know. That's what I'm getting. I'll take that. So state Doppler effect, remember what we said? That the change in the frequency of a sound detected by the listener because the sound source and the listener have different velocities that is relative to the medium or the sound or medium propagation of sound. Okay, then 6.1.3, they're telling us the detected frequency at this. What is the question saying, guys? They're saying the detected frequency suddenly changes at this. And what is the reason for that? Okay, so the changes, I mean, if the car just comes and is making a lot of noise and immediately it passes you, definitely there's going to be a change. Okay, so we could say that the car just passes the listener or observer. Okay, that is one reason. Or you can just tell us the car starts to move away at that instant, and can also tell us that maybe the car and the observer are just in the same place, because the moment you're just at the same place, then there's going to be that change. And then 6 point, next, they want us to take the speed of air to be 340 and then calculate the frequency of the sound emitted by the siren. So what we saw was that the frequency of the listener was 932. Okay. The velocity of the source was 30 meters per second. The velocity of the listener was 0. The velocity of sound is 340. Why am I saying Vs? It's supposed to be just a V. Okay. So I think, what do they want? They want the frequency of the source. All right, so remember what we said? Frequency of the listener should be V plus minus V what? VL over V plus minus Vs times F of S. That's the formula. Let's just go back there and be sure. Let's listen on top. Perfect. Okay, then let me do the substitution. This is going to be 932 is equal to my 340 minus velocity of the listener is 0. Am I using a minus? That's going to be a plus since it's approaching, okay? Then this is going to be 340 minus the 30 times the Fs. 932 is equal to 340 over 310 times Fs. All right, so 340 divided by 310 is giving me a fraction when I'm, what fraction is it? 34 over 31, okay. Fs is equal to 932. And then divide both sides by this thing. So 932 divided by my answer, I'm getting 809. 8.76 hertz. Okay, so that is the frequency of the sound, 849.76 hertz. Okay, state two applications of Doppler effect. Remember, we said it can be used in the Doppler flow meter. Okay, that meter that is used to measure the heartbeats of the fetuses and all of that. Two applications, okay, in the Doppler flow meter. And then we also said they can be used in the speed radars to detect those speed cameras and things, okay. And then we could also look at the sonar, okay. And then also to detect the moving stars and all of that. So all those are applications of Doppler effect. Question number 7, electrostatics. 2-point charges Q1 and Q2 are placed 30 centimeters apart along the straight line. Q1 is this, the point P is 10 centimeters, okay. As shown, the net electrostatic force is 0. So F net is 0. All right, then define the term electric field at a point. Remember what we said? This is the electrostatic force, okay, experienced per unit positive charge placed at that point. Okay, you can just go back there and then you just read our definition. Electric field. All right, then state giving reasons whether the point charge Q2 is positive or negative. State giving reasons. Now, the fact that we're having two charges, one of which is negative, and then we have a net force of 0, then chances are high that this Q2 is going to be a positive. Why is it a positive? Because it needs to counter this negative force or the negative direction so that there is some sort of attraction between the forces themselves. Okay. So we're going to say that the electric force due in Q1 will be negative. No, not really negative, but the direction will be different, because if this point charge is positive, so which means the force applied here is going to be force experienced, that this is going to be to the left. And then if this is a positive and this is a positive, then the force is going to be to the right. There's repulsion and what. So that's why I'm going for positive. Okay. So explanation, we're going to say that since the E net is not is definite, electrostatic field is E, not F. Okay, so we're saying the E net is 0, E1 and E2. So E1 and E2 are in opposite directions. They have to be in opposite directions. All right, so that is that. Then I want us to calculate the value of Q2. So we have to use the electric field. So remember we said E is KQ over R squared. Okay. So I'll start with the first one, which is Q1. 9 times 10 to the 9 multiplied by 3 times 10 to the negative 9 divided by 10 changed to meters. That's going to be 0.1. I'll square this. Now, since we know that our E net is a 0, which means the E1 must be the same as the E2. Okay, let me simplify that. I'm having 9 times 10 to the 9, I'm multiplying this by 3 times 10 to the negative 9. This is over 0.1 squared. I'm getting 2.7. Okay, let me look at E2. E2 is saying it's going to be K, which is 9 times 10 to the 9, multiplied by Q2 over the distance. Now it's going to be 40 centimeters, which is now 0.4 squared. If I simplify that, I'm going to remove that, put a 4, going to remove all of this. It's going to give me 5,625 times 10 to the 10 Q2. But remember, E net is 0, so which means E1 and E2 have to be the same. So this is the same as 2.7. Divide both sides by 5.625 times 10 to the 10. So when I do that, I'm going to have 2.7 divided by my answer. Getting a weird answer. It's very weird. It's 4.8 times 10. 1, 2, 3, 4, 5, 6, 7, 8. This is negative 8 coulombs. Okay, or you can just give it to us as 480 microcoulombs. 480 times 10 to the negative, or 480 microcoulombs. Yes, perfect. All right, then 7.4 state coulombs law in words. Remember what we said? That's more like the definition of electrostatic force. We're saying the electrostatic force between 2-point charges is directly proportional to the product or to the product of the magnitude of the charges, but it's inversely proportional to the distance of separation, to the square of the distance of separation. Then calculate the magnitude of the electrostatic force exerted by Q1 on Q2. So we already have the Q1. Now we calculated our Q2, which is now 4.8 times 10 to the negative 8. So let's just get the force. Remember, the distance is 30 centimeters. So force, we said it's K, Q1, Q2 over R squared. So 9 times 10 to the 9. This is going to be 3 times 10 to the negative 9. And then times 4.8 times 10 to the negative 8 over 30, which is 0.3 squared. And then I just get my force, punch this into the calculator first. 9 times 10 to the 9 times 3 times 10 to the negative 9 times 4.8 times 10 to the negative 8 again over 0.3 squared. That gives me something weird again. I hate this one. So it's 1.44 times 10, 1, 2, 3, 4, 5 here. So it's negative 5. Remember, it's a force, so it's newtons. All right, then 7.6, we've been given point charges and they drew for us the fluid patterns. So 2 charges are now brought into contact with each other and then separated. So whenever this happens, after the separation, the 2 charges will have the same magnitude. And the same sign, which means we expect some bit of repulsion afterwards. All right, so with this one, they are telling us that a learner draws the electric field pattern for Q3 and Q4 after contact. Is the diagram correct? The 2 charges are now brought into contact. So, is it still connected to this? Yes. This is a negative 3. This is a positive 4.8. Okay, so if you combine this, Let me just be sure. 4,8 times 10 to the negative 8. I'm saying plus negative 3 times 10 to the negative 9. Okay, I get a positive answer. I divide it by 2, so which means it's correct since the field lines are moving out. So the answer is a yes. Okay, because both charges are positive and equal in magnitude. All right. Then question number 8, which is electricity. So, and electricity, we just need to know about Ohm's law. Okay, how do we state Ohm's law in words? So the potential difference across a conductor is directly proportional to the current in a conductor at a constant temperature. So this is important. Then the directly proportional part is also important. So those keywords, at least they shouldn't miss in your definition. And then the relationship between current, potential difference, and resistance at a constant temperature for a simple circuit. You need to know that difference between ohmic conductors, those that obey Ohm's law, and then the non-ohmic that disobey Ohm's law. Then we solve the problems using this Ohm's formula for series and parallel circuits. We need to know the difference between the two and what happens in the series, because many times circuit diagrams are given and then we fail to notice what's happening. So one thing we need to remember is that for parallel circuits, the velocity, not velocity, it's the voltage, which voltage is also known as the PD, is always constant across. For series, it's the current that is constant. Okay, then power energy, define what power is, rate at which work is done. This is the formula. And then the different formats of power, okay, right from there. Then solve circuit problems involving concepts of power, electrical energy, deduce that 1 kilowatt hour refers to that, calculate the cost of electricity, okay. And then the great 12 aspects of internal resistance, series and parallel, and then EMF also needs to be understood quite well, okay. How do you define EMF? And so on and so forth. Okay, so let's just focus on this electricity, then we shall come back for electrodynamics. Okay, so 3 resistors, and light bulbs are also resistors. A, B, and C, each are rated 6 watts and 12 volts. Define the term power. Power. So we say the simple one, rate at which work is done. Okay, the rate at which work is done, or the rate at which energy is transferred. You can say that. Or rate at which energy is converted. Any other definition is also acceptable. Then 8.1.2 calculate the resistance of each bulb when used as rated. So we have the power, we have the voltage. What do they want? The resistance R. So we need to look for a formula of power that has resistance involved. So if I have P is equal to IV, but I know that V is IR, so which means I'm going to use P is equal to, no, that's not going to make sense. Let me make I the subject, which means it's V over R. So V squared over R. So which means that my resistance is going to be V squared over the power. My V is 12 over 6. So 12 squared over 6. What do we get? We get 24. I'm getting 24 ohms. Use any other aspect of power. Remember, we said we have different formats of power. But as long as it has resistance in it, we don't care. We shall give you the marks. Our job is just to give you marks, as long as you write the correct thing. Next, the light bulbs are connected in a circuit with a battery that is having EMF of 12 volts and an internal resistance of 2 ohms. So I think this was meant to be that small e, and that is the ohm symbol. All right. This is what they do for us, and this is how they are connected. Assume that the resistance of each light bulb is the same as calculated before. So this is a 24 ohm. This is also a 24 ohm. And then even this one is a 24 ohm. Okay. What is the first question asking for? They want the total current within the circuit, 5 months. Yo. Okay, so I can use the EMF formula and say it's I into R plus R. It told us EMF of this. So we have the EMF of 12, the internal resistance, we have it. Do we have the current? We can get the current since we already have the power and the voltage. Okay, let me start with that. So power over, are we still on the same thing? No, I'm not gonna do that. I'm not gonna, that is going to be risky for me. Let me start by getting, what is the question asking for? They want the current. So if I use that, I'll be committing suicide. Okay, this I don't know. It's a different question. So I need to get the capital R first. Okay, so resistance external. So I see that B and C are in parallel. And then A is in series with this parallel combination. So let me just get the R for the parallel. That's 1 over R1 plus 1 over R what, and I prefer using product over the sum. So that is going to be 24 times 24 over 24 plus 24. Okay, so 24 by 24 divided by 24 plus 24. That gives me 12 ohm. So the combined resistance for these two is 12 ohm. And then since now this 12 is in series with this, which means that my R effective is going to be 12 plus 24, which gives me a 36 ohm. Then come here and substitute, and my current is going to be EMF over R plus capital R. EMF we said is 12. The small r is 2. The capital R is 36. Let's punch this into the calculator and see. 12 over 38. I'm getting 1 over 3. Is that even reasonable? Is that reasonable? 12 over. That's fine. Let's keep it that way. There's nothing to do. So 12 over 38. No, man. What's my calculator? Because when I punch it back, I'm getting 0.315. So it's 2. Okay, we keep it that way. Then, so we have our current here at 0.32 amps. Then calculate the potential difference across C. Now, since we know that this and this one, the parallel one, are in series, which means there's going to be a voltage that is different from this voltage. But the voltage of B is going to be the same as the voltage of C. So I'll start by getting the voltage across. How many marks is it? It's 3 marks. Let me get the voltage across the A. Okay, so we know that the voltage, I'll say V is equal to IR. Let me just get the external voltage. That's going to be the current, which is 0.32 multiplied by the resistance here. Total resistance was what? 36. No? Is it going to be 36? Mm-hmm. It's not going to be 36. How am I going to do that? Because they want the potential difference, which is the V. Okay, let me do this. Let me do this. So without, I'll just include the small r so that I just focus on this. So if my I is a 0.31, I'll say 32 into, that's a 24 plus a 2 should give us the V external. That's one, the external voltage. So 0.32 multiplied by 26, I'm getting 8.32 volts. Okay, that is 8.32 volts instead of the 12. Okay, then if I get my overall, which was a 12, remember now this is just the EMF across this one. 12 minus 8.32. That's going to give me 3.68. So 3.68 is across the parallel. Okay, and remember what we said, voltage across the parallel is always constant, or it's always the same. So I'm going to say that the voltage across is 3.68. Okay, I'll keep that. I'll go with that. Then 8.1.5, can we explain why C in the circuit will not burn at its maximum brightness? Now, the fact that we have an alternative path, okay, or B, okay, that is one. But we can also look at the power ratings. The power rating is 12 volts. This is how much it can handle. But then what is going through there is just a 3 something. So I believe it is too low. It is too low. So how do we put that into consideration or into explanation? We can say that for any resistor, the power is always directly proportional to I squared. Remember I said it was I squared over R, or V squared over R, and inversely proportional. Inversely proportional to the resistance. So which means that however much the power increases, the resistance just tends to decrease. (8.2) resistors A, B, C, and D are connected to a battery that is having EMF and energy given to resistance as shown. Give a reason why current in A is greater than the current in C. So by virtue of looking at this, it's like A is connected to the line that is going to feed these others. And the fact that C is in parallel with this, there's a division. Okay, there's a current, maybe A, there's a current B. So the current of A should be equal to the current of C plus BD. Okay, so basically, that is the literal explanation. Or you can put it in words and tell us that the total current through A is equal to the current through C, B, and D. Total current through A is the total of that, which means it's greater. It's equal to the sum of that. Or you can tell us that the current through C is just a branch. It's just a portion of that. Then 8.2.2, resistor C is now removed. Beautiful. How will the current in B compare to the current in A? So the answer is going to be the same. Or you can tell us it will be equal to each other. Why? Because for as long as this is out, A, B, and D are going to be in series. And we said in series, the current will be basically the same. Okay, so you can say resistors will be in series. All right, then we move on. We move on. Question number 9, that is electromagnetism. Let's go back here. Said electrodynamics. We need to look at electrical machines, that's the generators and the motors. We need to be able to state the energy conversion in the generators. What does the generator do? What does it convert? So it converts mechanical to electrical. What do motors do? Motors convert electrical to mechanical. Okay, use the principle of electromagnetic induction to explain how generators work. Okay, using those Fleming's left, right hand rule and so on. Explain the functions of the AC and the DC generator. Examples of uses of the AC and DC generators. And then energy conversion in motors. The motor effect, to explain how the motor works. Functions of the components like the slip rings and all those things, the brushes. Examples where motors are used, or uses of motor. And then under this, we also tackle the alternating current, the AC, advantages of AC over DC, sketching the graphs, okay, define the RMS of this. So here is the definition. The difference, define the RMS potential, no, it's not the definition. RMS potential difference is the AC potential difference, which displays the same amount of energy as the DC. Yeah, it's the same. So RMS current is the alternating current, which displays the same amount of that. So we just need to remember that. Then the formula of IRMS and Imax, all this will be given on the formula page. Just know how it works. Okay, back to our practice questions. They're telling us the diagram below shows the voltage output of a generator. Then we have 312, negative 312. Have the time intervals, and then the graph is given to us. So we know that for as long as it is a sine graph, this is a generator, with the motor to be more like amps. Okay, so does this generator have split rings or slip rings? What's the reason? Okay, we're saying the slip rings. It's the slip rings. The 9.2, which one of the diagrams below, A or B, shows the position of the generator's coil at a time 0,1. So you're seeing that at 0,1, the potential difference is 0. So when do we have a 0? Is it when the coil is parallel to the direction, or it is perpendicular to the direction? So we get a 0 when the coil is perpendicular. Okay, when the coil is perpendicular, that's when we have the 0 voltage or 0 EMF. Okay, then they want us to calculate the root mean square voltage of this generator. So from these formulas, we said root mean voltage. So we said Vmax over square root of 2. So Vrms is going to be Vmax over root of 2. So it was 312 over square root of 2. Let's put that into our machines. I'm getting 220.62. 220.62 volts. Okay. Then a device that is having a 40 ohm resistor is connected to this generator. Calculate the average power that is dissipated. So power average will be equal to Vrms over R. So that is going to be 220.62 divided by the resistance, which is 40. Okay. But just a moment, why am I have to use VR squared, V squared over R. So it's V squared because I'm looking at the power. So I need to square that as well. Okay, so 220.62 squared. I'm dividing it by 40. That gives me 1216.829, which is 83 watts. Okay, and then 9.4.2, they want the maximum current that is delivered by the generator. Maximum current that is delivered by the generator. So number one, we need to start by getting the current itself, okay? That I max. Is it going to be the I max? Definitely. It's going to be, remember, it's V is equal to IR. So I max is V max divided by the resistance. We don't have resistance max. Okay, so our V max, remember, was 312 divided by the 40. 312 over 40, you know the same thing? No, it's 7.8. This is amps. And then for us to get IRMS, it's going to be I max over root 2. The question wanted the I max, maximum current. So why am I getting root 2 again? No, there's no need for that. That's just fine. Just the formats that look so direct and there's a lot. All right. That is question number 9. And then lastly, question number 10 deals with the photoelectric effect. Okay, so we go back here and we say optical phenomena and properties of materials. Photoelectric effect describe what it is as a process where electrons are ejected or removed from the metal surface when a light of a suitable frequency is shown. When you shine, when the light is incident, then that will be able to remove an electron. What is the significance of photoelectric effect? Define threshold. Remember, so it's the minimum. Okay. Then define the work function, which is the minimum work to be done in removing an electron. Then calculations using this. And then we need to know that E is equal to HF, where H is Planck's constant. Then this is the formula for the work function. And then the EK max is given as that. Explain the effect of intensity. So this simply means that if you increase the intensity of the light, what will happen to the number of electrons that will be ejected? Okay, when you change the frequency, what will happen? Then state the photoelectric effect as demonstrates the particle nature of light. Then you also have to discuss emissions, and then absorptions, the different spectra, and so on and so forth. So this we need to know, at least before we go for the paper. Okay, let's answer this last question. They're telling us a potassium metal plate is irradiated with light of this much wavelength. Okay. In an arrangement as shown below, the threshold frequency of this is this much, and then define threshold frequency. So we say this is the minimum frequency of light needed to eject electrons from a metal surface. So the words minimum frequency and then eject electrons from a metal surface, those are keywords. Then 10.2, calculate the energy of a photon incident on the metal plate. So since we want the energy, remember E is equal to HF. Okay. But do we have the frequency? No. Remember, we're not talking about the light as yet, because this is a potassium metal plate. So a potassium metal plate is irradiated with the light of this much of wavelength. This is just the threshold. It's not the frequency that we're just going to. So I think we can use the wavelength formula. So we're going to modify this. We know that F is equal to C over lambda. So where there is F, I'll just put a C over lambda. And then I have this. What does the question want? The energy. So my H Planck's constant is 6,63 times 10 to the, is it 34? Negative, positive. Should be negative. I hope so. Then the speed of light, 3 times 10 to the 8 over the wavelength, which is 5 times 10 to the negative 7. Okay. When I substitute all of this, punch it into the calculator, 6,63 times 10 to the negative 34 times 3 times 10 to the 8, because that is the speed of light. Okay. I'm dividing it by 5 times 10 to the negative 7. This gives me 3,98 times 10 to the negative 19. Since it's energy, to be measured in joules. All right, 10.3, use a suitable calculation to prove that the ammeter will show some bit of reading. So what do we do? So for us to have some bit of reading, which means there should be kinetic energy. Okay, so what I'm going to do is I need to get the energy, which will be the work function plus the EK max. Do we have the work function? We can get it since we have the threshold. Okay, so this is going to be H times F. Work function, we said, okay, I'll just keep it. This is a half mv squared. That is the maximum velocity. So then I don't have frequency, so it's H C over lambda again is equal to my work function plus EK max. And then I'll do my substitution. We know that this work function is the same as H multiplied by F naught. So Planck's constant and this whole thing, isn't this what we just looked for? The energy of a photon instant. Yes, that's what we got. So you're going to have 3,98 times 10 to the negative 19 is equal to 6,63 times 10 to the negative 34 multiplied by the threshold frequency, which is 5,55. Okay, times 10 to the 14. That is correct. And then plus acting up now. This thing is acting up on me now. Okay, so the repulsion, we're gonna just draw something like that. Have that and that. Doesn't matter. The field lines could be the same. So Just need to show the arrows moving out. Okay, just something like that. You can draw the sphere, or remember these are point charges, so it's better I use that. I can call this A, then I can call that B. For as long as there is a repulsion that's taking place, that's what's going to count. Then the magnitude of the net electric field at P is given as 27 Newton per Coulomb. Calculate the value of R. So we know that the formula of electric field is given as E is equal to KQ over R squared. So I'm going to calculate the electric field at P due to A. So I'm going to say EA. That is KQ. Let me just substitute 9 times 10 to the 9. The charge is 3 times 10 to the negative 9 over. That's going to be R squared, because the distance between A and P is just R. Then I do my magic with the calculator. So that is just the 27 over R squared. Okay. Then I'm going to look for EB, the electric field at P as a result, or due to B. So that's going to still be KQ over R squared. That's 9 times 10 to the 9. That's 3 times 10 to the negative 9. But the distance is going to be twice R squared. And I simplify that. I'm just going to get 27 over 4R squared. Now, I need to know the direction. Okay. So one thing I know, that since this point charge is a positive, there's going to be repulsion that is taking place. So at P, the first force A, the EA will be acting east or to the right. And then the EB, that's also going to be repulsion, so which means it's going to be acting to the left. But then the net is a 27. So I'm going to say my EA plus my EB must give me 27 Newton per Coulomb. So my A was a 27 over R squared. My B is now negative 27 over 4R squared. Is that true? Is that true? I think it is true. Then it's equal to the 27. Then we just need to simplify. So the 27, 27, 27. So what I can do, I can multiply through by 4R squared. Okay, so that I don't have to work with denominators. So multiply by 4R squared, multiply by 4R squared, multiplied by 4R squared. So this cancels that. This R squared cancels that R squared. I have 27 times 4. Is it going to make sense? It's fine. Let me just do it the hard way. Okay, that's going to give me 108. I'm subtracting a 27 is equal to 108 R squared. So 108 minus a 27, I'm getting 81. Okay, so 81 is equal to, let me just, okay, it's fine. Let me not rush it. Over 108 over 108. So that cancels that. So R squared, let me just say R is the square root of 81 over 108. So square root of 81 over 108, that's going to give me 0.866 meters. Did they tell us centimeters or meters? Meters, okay. So which means that is my value of R. All right, then 7.3. They want us now to calculate the magnitude of the net electrostatic force that an electron would experience at a point P. So we know that F is K Q1, Q2 over R squared. Okay, that's electrostatic force. But if we look at this, this will give us what we call the electric field. So which means the force must be electric field multiplied by the charge of interest. Okay, because electric field is the force over the charge of interest, so you can use small q. But now, since we're focusing on an electron, we're going to get the net electric field, which is the 27, multiplied by the charge on an electron, which is negative 1,6 times 10 to the negative 19. Okay, when I simplify that, I'm getting 432 times 10 to the negative, yes. I'll just say 4,32 times 10 to the negative 18. That is going to be newtons. So that is how I would get that. So that is question number 7. Question number 8 is electricity. They're telling us that the circuit diagram below shows a battery with an EMF of 12V and an internal resistance of 0,5 ohms connected to 3 resistors. There's a light bulb, a switch, and an ammeter. Okay, and connecting wires. The ammeter and connecting wires have negligible resistance. Now they want us to state Ohm's law. What is Ohm's law, guys? So we know that the relationship between that the potential difference across a conductor is directly proportional. Okay, so across the conductor is directly proportional to the current, directly proportional to the current at a constant temperature. At a constant temperature. So you can just design it or reframe it in a way, but we know that V is equal to IR. Okay, so this PD, which is the V, is directly proportional to the current at a constant temperature. Okay, then they're telling us that switch S is initially closed. Okay, just the way it is. Now the question wants us to get the total external resistance. Okay. There are 2 ways to this. Okay. They give us the EMF. Yes, they gave us the EMF. Which is that? Do we know the current? We don't. So which means we need to go the long way. So we know that this pair is in parallel. But then this pair and this are going to be in series because this bulb is having also some bit of resistance. Okay. Then the result we get is going to be in parallel with the 15 ohms. So what I normally do with 2 resistors in parallel, for me to get the effective resistance, if I call this A, I'll just get the product over the sum. So that is 10 times 10 divided by 10 plus 10, which is a 20. So 100 divided by 20, I'm just going to get 5 ohms. Okay. So that is 5 ohms. So which means that this combined pair is giving me just 5 ohms. Now, when I look at these 5 ohms and the light bulb, they are in series. So I'll get the 5 ohms plus the 10 ohms, which gives me the 15 ohms. So this entire part can be reduced to just the 15 ohm combined. Now, this 15 and this 15 are in parallel. So I'll say R3 and RL, they're in parallel. So I can still do the same thing since I'm looking at just one resistor. So the product over the sum again. So that is 15 times 15 divided by 15 plus 15. So 225 divided by 30. Is that true? 15 times 15 is 225. Dividing it by 30, I'm getting my effective resistance to be 7,5 ohms. So the answer for this is just going to be 7,5 ohms. That's how you get the 5 ohms. Okay, so start by getting the effective resistance of this parallel, combine it with the bulb that is in series, and then combine them. All right, then the reading on the ammeter. Where's the ammeter? The ammeter is here, just reading the current. So for me to get the current, I'll just use my EMF formula and say that EMF is given as the current into R plus small r, which is the internal resistance. So my current will be the EMF over capital R and small r. So that is a 12 over the 7.5 plus the 0.5. That is 12 over 8. So 12 divided by 8 is giving me 1.5 amps. So that is my current, or that is the reading of the ammeter. Then the power that is dissipated by R3. So we need to know where our R3 is. So R3 is this 15. Okay. So what is happening there in R3? So what we need to do, how many is 4 marks? So we need to first of all get the voltage. Okay, the voltage that is across. So remember, this entire top part is going to be in parallel with this bottom part of the 15 ohm R3. So which means the external voltage is going to be the same across. So let me get the voltage. Is that going to make sense? Yes, it will make sense. I need to get the voltage of the internal. So which means my EMF is equal to V external plus the V internal. So from the EMF formula, I have my IR plus my I small r. So my I small r is going to be 1.5 times the 0.5. Okay, 1.5 times the 0.5, I'm getting 0.75V. And then I'm just going to subtract this from the 12. So which means my V external is going to be 12 minus 0.75. Okay, that is going to give me 11.25. So remember we said since they are in parallel, within a parallel combination, the voltage is always constant. The current will change. Now, since we have our voltage, we need to look for a power formula that combines voltage and resistance. And the power formula I found was the V squared over R. So our V squared will be 11, we say 25. Let's just confirm 11.25. So 11.25 squared, we're going to divide it by 15. 11.25 squared divided by 15. So what does this give us? 11.25 squared. I'm dividing it by 15. Eyeball. Oh, okay. It is what it is. I'm getting 8.44. 8.44 watts. So that becomes the power dissipated. Then 8.3, they are opening the switch. Okay, let me just remove this. They are opening the switch, which means that this resistance will be out. Okay, the 15 will be out. We shall be only left with, remember our effective resistance was 7.5. Now, if 15 is removed, we shall only have this 5 and a 10, which gives us a 15, which means there's an increase, okay, by 2 times or 2 times the increment. So if now the resistance is 15 ohm, they're asking us if the resistance of the light bulb remains constant, okay, how would the brightness of the bulb be affected? Is it going to increase or decrease or remain the same? So regardless of the current that is flowing, remember this bulb is more like connected in series. with the circuit for as long as this is open. Okay, so the same current will be flowing upwards. So the total resistance within the circuit has increased. So the current that is getting to the bulb will have to decrease. Okay, and when the current decreases, even the brightness will have to decrease. Okay, so that is a decrease. Now, what is the explanation? We're going to say that there's going to be an increase within the total resistance. Or we can say that the V external will increase. Okay, since we know that V is the same as IR. So if we increase the resistance, even the external voltage will definitely increase. So increase in the V external, okay, will lead to a decrease in the resistance. Or we can talk about the resistance decreasing, which leads to a decrease in the V external. That's why the brightness has decreased. Question number 9. Okay, there's a telling us a simplified DC electric motor is shown. Okay. This is what we can see. Now they're asking us to write down the name of component A. So we know that A is the split ring. Okay, split ring, you can say commutator, or just a split ring. That's enough. Okay, so then 9.1.2, they want us to state the energy conversion that takes place in the motor. So we know that the motor is an electrical device that converts, okay, is it mechanical? No, it's electrical to mechanical. So we're gonna say electrical to mechanical. Okay, so electrical energy to mechanical energy. So that's the energy conversion that takes place within a motor. Then 9.1.3, in which direction is the coil going to rotate? Choose either clockwise or anti-clockwise. So if we look at our terminals, this is the positive, which means the current is moving in that sort of direction. Okay. And then when we look at the field, let me just put this. So the field is moving in that sort of direction from right to left. Then we can use, okay, the left-hand rule for Fleming. So, which means that our field is going to be that side. Our current is in this direction. Automatically, the force must be up. Okay, so this is going to move up and then this is going to move down. So the rotation is going to be clockwise. Then state 2 changes that can be made to the motor for the coil to rotate faster. So number 1, we can increase the magnetic strength or the field strength. Okay, so if we say increase, changes that can be made to the motor. Okay, increase the field strength. Okay, that's number 1. We can increase the number of turns. Increase the number of turns. Okay, that is. Then the last one that we can use is we can increase the strength of the current. Okay, increase the strength of the current. So all these 3 can be applied if we want to make the motor to rotate faster. The 9.2, they're telling us the circuit diagram below shows the electric kettle and the toaster that are connected to an AC source with RMS voltage 220 V. The ammeter, connecting wires and switches have negligible resistance. And then they're asking us for what the term root mean square current is. So we know that root mean square will be basically, I'll say the DC current, okay, that dissipates this right, that dissipates just the same amount of power, as the average. Okay, I can say the average that is dissipated by the AC. So in this case, DC current is this. That current, the root mean square current is a DC current that is more like equivalent to the same current that is dissipated by the AC current. So I'm saying the DC current that dissipates the same amount of power as the average dissipated, same amount of power as that average dissipated by the AC current. So it's like a comparison between the AC current and then the DC. So the equivalent of the AC is what we call the root mean square. Then 9.2.2 are telling us that when S1 is closed, okay, we're closing this, and S2 is open, the maximum current through the circuit is 3.6 amps. Can we calculate the root mean square of the current? So the RMS current, normally abbreviated as IRMS. For me to get this, I must find my Imax divided by the square root of 2. So our maximum current is 3.6 divided by the square root of 2. So 3.6 divided by square root of 2, what do we get? I'm getting 2.55. Okay, that will be amps since it's current. The 9.2.3, we're being told that switch S1 is now open. Okay, and then they choose to close S2 so that they look at the toaster. And then the root mean square current is 2.62. So the IRMS of the toaster is 2.62 amps. Calculate the energy that is consumed within 2 minutes. So we know that if I look at power, it will be the work done over the time. So which means that my work done will be the equivalent of the energy that will be consumed. So my work done will be the power multiplied by the time. But what I have, I'll just say the average power in this case, the power average. Since I have the current, I do not have the voltage. No, do I have the voltage? Yes, we have the voltage, which is 220. So which means the VRMS is 220. We don't need the resistance. You can calculate it if you want, but it's not a big deal in this case. So from our formula page, we can look for a formula that combines voltage and current. Ne? Voltage and current. We need the work done. I think we can even use this. Voltage squared over R times T for us to get the work done straight away. Or we can just say voltage squared over R and then multiply by the time afterwards. Okay, so what I'm going to do, I'll just get my V squared over R multiplied by T. So what's our V? It's 220. So 220 squared over, wait a minute. Do we know the resistance? No. I need to use the current since I have the current one. So let me look for the formula with the current. Is it the P is equal to IV? Does that make sense? Yeah, I can use this. VIT. VIT. Okay, so say VI and then T, so it's 220. The current is 2,62. The time should be in seconds, né? So that is 2 minutes multiplied by 60. When I punch this into the calculator, 220 multiplied by 2,62 multiplied by 2 multiplied by 60. That is giving me some big answer, which is 69. Okay, 168 joules. Or someone can say 61,17 kilojoules. No problem. So that is the work done, or the energy that is consumed by the toaster in 2 minutes. Question number 10. Question number 10. We're being told that two small spheres, okay, two small spheres, A and B, both of them are made up of pure zinc at rest, okay, and they're 0,1 meters apart on the wooden table. Sphere A is negatively charged, okay, and is free to move on the table, while B is fixed and it's uncharged. All right, so we have that. We have high intensity ultraviolet light of this frequency that is now shown on to sphere B. The work function of zinc is this much, so that is W naught. This is the frequency that is given. Can we define what work function of a metal is? So work function is just the minimum amount of energy required, or we can say the minimum energy needed, or say needed, or required to remove or to extract an electron from a metal surface. My friends, forgive me for my handwriting. Okay, so minimum energy required needed to remove or extract an electron from a metal surface. That is the work function of a metal. Then 10.1.2, they want us to explain using suitable calculation why the ultraviolet that is shown on B will be able to eject electrons. Okay, so eject is more like to remove or extract. So for us to answer this question, we need to calculate the work function, okay, of the ultraviolet or of the zinc metal. So we know that work function will be given as H multiplied by the F naught, the threshold frequency. So what we know is we are given the work function of zinc, which is this. Now let's get the work function. Will it make sense? Yes, the work function, if we have the ultraviolet light that was shown. That. So what I'm gonna do, I'll get the Planck's constant, which is H, which is 6,63 multiplied by 10 to the negative 34. I'm gonna multiply it with the frequency, which is 2,8 multiplied by 10 to the 6. No, I don't need to do this. I can just, okay, this formula is fine, but I'll just look for the energy, okay? I'll look for the energy itself, which is HF, the energy that will be produced by the ultraviolet light. So when I punch this into the calculator, if I punch this into the calculator, I'm getting 1,856. What's going on? Okay, we're saying 1,856 multiplied by 10 to the negative 6. But this will be joules. Okay. If I'm to compare it to the work function, I'll have 185,6 times 10 to the negative 19 joules. Now we can see that 85 is greater than the 6,63. Then we can draw the conclusion that the energy that is produced by the ultraviolet light, is greater than the work function, is greater than the work function. So since the work function of zinc, the minimum energy required is 6.63, and then 185 is way greater, so which means we shall be in position to extract electrons from that metal surface. And then 10.1.3 sphere A carries this charge and then requires a minimum force of this much. Calculate the minimum number of photons of ultraviolet light that must strike in order to remove sphere A from the rest position. Okay, so what I did in this case, I tried to look at that electrostatic force of K, Q1, Q2 over R squared. If that is A and then that is B, I want to see the charge on B that is going to cause an attraction, and then I'll take it from there. So since our net force is 0.027, that's what the question says. I'm not assuming my own things. They told us this is the force that is required. All right, so that is the Emax. Okay, so this is 9 times 10 to the 9 multiplied by the first force, which is 5.4 times 10 to the negative 6. I'm multiplying it by the QB over the distance of separation, which is 0.1 squared. So do the maths, 0.027 multiplied by the 0.1 squared. Then I'll divide this by the 9 times 10 to the 9 multiplied by the 5.4 times 10 to the 6. That will give me my QB. Then QB, what are we getting? I'm getting 5.56 times 10 to the negative 9. Okay, this is just the charge. Now, if I look at the Q is equal to NE, okay, I think I'll just use this approach. For me to get the N, I'll just say Q over E. Then my charge is the 5.56 times 10 to the negative 9, dividing it by 1.6 times 10 to the negative 19. Okay, and I simplify that. I'll have a total of 3.47 times 10 to the 10 electrons. Okay, so that's what I'm seeing, because they're asking us for the number of photons. Remember, photons are just packets of light, and it's more like electrons themselves to move from the rest position. So that's what I would have done for that question. Then question 10.2. I'm telling us a beam of light. This is why it is shown through cold gas. So the keyword here is cold gas. Okay, then the emerging light dispersed, and then the line spectrum is observed on the screen. What type of line spectrum is this? So this is the absorption. I don't know if that's the spelling. So that is the absorption spectrum. Absorption spectrum, and then they want us to describe or define it. So this is a type spectrum where, or a type of spectrum that consists of frequencies of light that is transmitted with dark lines when electrons absorb energy with the ground or from the ground state so that they can reach the higher stages. So in other words, in this type of spectrum, the electrons will gain energy, okay? And that energy will enable these electrons to move from levels of low energy to levels of high energy or high energy levels. So which means they move from the ground state to higher energy levels. They're telling us that diagrams below indicate some possible energy transitions that are made by the electrons or by the atoms. Which of the diagrams will represent the type of spectrum? Now, since we said from our description that energy has to be obtained from low energy levels, and then the electrons or the particles will be observed to be moving to higher energy levels. So I'll go with B, since with absorption, energy will be gained. All right. Which of the following? Choose A or B. So I'm choosing diagram B. I'm choosing diagram B. So guys, that is that. If there's any feedback, please, you can leave it in the comments. If there are any deviations, please, you can still slot them under the comments. We are more than welcome and we appreciate your positive feedback. It helps us grow. Thank you very much, guys. All the best in paper 2. Good day and welcome to yet another episode where we shall look at the suggested memorandum for the Physical Sciences paper 1, grade 12, 2023. Okay, so looking at the paper, we have 10 questions and let's try to see what could have been done in this paper. Remember, this is just the suggested memorandum. It's not the official one, okay? So question number 1, which is the multiple choice, they're telling us that various options are provided. We know that. Then 1.1, a constant net force is applied to a block. Okay, now which one of the following is correct? Okay, is the block going to move with a constant velocity? No, so that is out. Is the block going to move with a constant acceleration? There is some bit of truth in that. Then will the block move with a constantly increasing acceleration? No. Constantly decreasing? No. So for as long as the net force is constant, which means the acceleration will increase. No, the acceleration will be constant, will not increase. So B would be my option for 1.1. And then 1.2, they're telling us we have a crate of mass M that is stationary on a plane inclined at an angle of theta with the horizontal. Which of the following statements regarding the magnitude of the frictional force that are acting on the crate is correct? So one thing we know is that the forces that are acting on this object will be the FG parallel. Okay, and since there is no other extra force, let's say the applied force or anything of that sort, we expect this block to slide down. But since it is stationary, which means the frictional force should be acting upwards to keep this block in one place. Okay, so they're telling us that the magnitude of the frictional force acting on the crate is equal to the component of the weight, which is parallel. That is correct. Let's explore the other options. The frictional force is greater than the weight. So if frictional force was greater, then what would that mean? Then this object would be sliding upwards, so which doesn't even make sense for me. Okay, frictional force is equal to the component of the weight that is perpendicular, so the perpendicular part is wrong, and then is larger than the component of the weight. Frictional force is larger, that is perpendicular, so the perpendicular part also makes it wrong. Okay, so between option A and B, but in this case, since the object is not moving, I'll choose option A, since the net force is gonna be 0. Is that true? But that is my option anyway. If you have anything different, please, you can slot it under the comment section. Then the next one, 1.3, they are telling us there's a ball that is projected vertically upwards from the top of the building. Points P, Q, R, and S represent the different positions during the motion of the ball shown in the diagram. Okay. So if you are ignoring the friction effects, between which 2 points will the ball undergo the greatest change? Okay, so greatest change in kinetic energy. So we know that for kinetic energy, okay, let's say the change, if you have M, you can say V final minus V initial, you can even square that, or you can just look at it independently. Vf squared minus the Vi squared, this multiplied by half M. So if we look at P and S, if this object has a velocity, which we know, let's say, because we're not dropping this object, we are throwing it up with some magnitude of velocity, okay? Unless we also have this, the change between P and S is not that significant, okay? Let's look at P and R between this. It won't make any change that is significant. But my option, R and S, let's see, R and S, not really. My option would be D, between Q and S. Because we know that at S, this ball or this object will have the greatest velocity. Okay, the V maximum will be at S. Then at Q, that's when the body is going to have the V minimum, the minimum velocity. So this maximum and the minimum, we know the minimum velocity is going to be a 0. So this change of the maximum and the minimum will be the greatest. Okay, then 1.4, telling us a ball is dropped from a height h, okay, and strikes the floor with a momentum v. The ball is then dropped from a height which is a half of h. If we are ignoring friction again, which of the following represents the momentum of the ball when it strikes the floor after being dropped from that? So what we need to look at in this case is basically, we can look at the formula of momentum where we have mass multiplied by the velocity. But we don't have the velocity. We know that the ball is just having the same mass, whether dropped from h or half of h. So if I try to kind of look for the velocity and I use the V final squared is equal to, I can use V initial squared plus 2 multiplied by G delta S or delta X for the displacement. In this case, it can even be a delta Y since we're moving in the Y direction. Now, since we are dropping, I'll take G to be positive in this case, and our initial will automatically be a 0. So if I consider the H, okay, so at height H, my V final will be the square root of just this, since that is a 0. So 2 times 9,8, I'll just say H. Okay, let me call this, why can't I say VH? We're saying 2 times 9,8H and the square root. Okay, then I'll do the same thing for V when it is a half of H. I'll still be left with the same thing. So this will be a 0 again, since I'm just dropping the object, then I'm gonna have 2 times the 9,8 times now the half of H, which is H over 2. Okay, so then for me to simplify that, I can see that this 2 is gonna cancel that, and I'm only gonna be left with 9,8H under the root sign. Now, if I try to get the momentum, the masses are the same, so basically I'm comparing. If I call this P1, okay, it's going to be root 2 multiplied by the root of 9,8H. Okay, and then my P2, which is the momentum at a half, is going to be, let's just call this one. That's the way they're calling it, that this whole thing is a P. And then momentum 2, we just have the 9.8 h multiplied by the mass. Now the question wants us to compare this second momentum. How does it relate with the first one? Okay. So we can see that we have this and we have that. The only difference that we don't have is the square root of 2. So the option that I'll go for will be a B, because the second momentum will be half or 1 over root 2B. Okay, then 1.5, they're telling us a box moves on a horizontal surface. Diagram below shows all the forces acting on the box. Which of the following combination of forces will do the work on the box? Now pay attention to the direction. So we're looking at moving on a horizontal surface. So it's moving horizontally. Regardless of the direction, fine, horizontal. So our interest will be basically the horizontal forces. Okay? So we know that this Q will have a component of the Q cos of the angle of inclination, okay, that will act horizontally. So the forces that are going to do work will be basically this S, and I'm seeing this Q. Is there friction? There is no friction in this case. Okay. Work will not be done by the weight, work will not be done by the normal force, since those are vertical forces. So I'm gonna go for S and Q. So the option I have is Q and S in that case. Then 1.6, a train that is moving at a constant velocity towards a stationary listener emits sound waves at a constant frequency. Which of the following statements about the sound waves observed by the listener is correct? Now remember, the listener is stationary, not moving. So as the train is approaching this listener, we expect the frequency to increase, okay? And if the frequency is increased, which means the lambda, the wavelength, must be smaller or shorter in that case. So let's see, they're telling us that the observed frequency is higher than the emitted frequency. That makes sense. They're telling us that the wavelength is longer, which is wrong, because we said if the frequency is high, the wavelength must be shorter. And the frequency is lower, no. The wavelength is equal to the emitted wavelength. That is also wrong. So I'll go with option A. And then 1.7. If we are referring to the diagram below, they're telling us Q and R are small spheres that are suspended by light insulated strings. When a negatively charged rod is brought close to Q, sphere Q is repelled. And then when a negatively charged rod is brought close to R, there is attraction that takes place. So which of the following combinations below can be possible for the nature of that? Now, we know about the signs or charges, that like charges will repel and then unlike charges will always attract. So automatically, since Q is repelling a negative rod, Q will be negatively charged. Okay. Now, with attraction, there are two scenarios. Attraction can take place between two opposite charges, let's say negative and a positive. But attraction can also take place between a negatively charged rod or charged sphere or object and a neutral object as well. Okay, there will still be attraction. So R can either be positive or it can be neutral. But we're saying Q is a negative. So where is Q negative? We have option A, and then we have option D. Then we're saying R, we only have two options. It's either positive or neutral. So A is out. We shall go with D. Okay, then 1.8, 4 voltmeters, V1, V2, V3, and V4 are connected in the circuit as shown below. So which voltmeters will have the same reading as V1? So our focus is V1 that is connected across the terminals. So connected across the positive and the negative. So when you look at V2, V2 cannot have the same reading since it's just connected, not across the terminals. V3, I feel is the correct option because connected across, okay? We have the positive and then we also have the negative this side, but as long as the switch remains open. So V3 becomes the option because V2 and V4 are basically in the same sort of scenario. So this is out, that's out, and then that is also out. So B would be my best option for that. Then 1.1.1.9, they're telling us that a split ring commutator connects the coil of a generator to the external circuit. Okay. Which of the following combination is correct of the magnitude and direction of the induced current within the external circuit? So focusing on the generator and then about the external circuit. So the magnitude of the induced current, since, so we need to ask ourselves, which generator uses the split ring? Is it an AC or a DC? Okay. If we can tell that, then we shall be able to look at this or to determine that. So the generator that uses the split ring, remember for the motor, is the DC motor that uses the split ring. Okay, but then which generator uses the split ring? Okay, so since we have a split ring commutator, I'll go for a DC generator. Okay, and with the DC generator, what we know about the magnitude of the induced current is gonna keep on changing. Okay, so I have option C and D for the magnitude of induced current. But the direction, since it is a direct current, it has to stay the same. Okay, so option C would be my best. It would change if it was an AC. Then 1.10, light of a suitable frequency is shown on to the surface of a metal and electrons are ejected from the metal. Which of the following is equal to the ratio of the work function to the threshold? So from our formula page, we have something like this. Work function is equal to H times F naught. Okay, so they want the ratio. It's like we are dividing W naught over F naught, the threshold frequency. So this will only be left us with H, and this H is what we call Planck's constant, which is A in that case. So that is question number 1. Question number 2. Question number 2, they are telling us that 2 blocks A of mass 4 kgs and then the 9 kg are connected by a light string. The blocks are held at rest on a plane which is inclined at an angle of 35. Okay, so paper was out of 153 hours, okay, just as we discussed in the prediction. Okay, so let's look at the multiple choice. So they are telling us we have various options that have been provided. We just need to choose one. 1.1. 2 forces, F1 and F2, are applied on a box that is lying on a frictionless surface as shown below. The magnitude of F1 is greater than the magnitude of F2. Okay, so what will happen to the box? The box will accelerate to the left? No. The box will accelerate towards the right. That is going to be correct. Will it move at a constant speed towards the right, move at a constant speed towards the left? So I'll go with the option of accelerating towards the right. Then 1.2, they're telling us that a 5 kilogram iron shot put and a 10 kilogram aluminium shot put with the same diameter both fall freely from a shelf that is 12 meters above the ground. So if we are to ignore the effects of friction, when the shot puts are 3 meters above the ground, the shot puts will have the same momentum? No. We can't go for momentum because momentum will be dependent on the masses, and since the masses are different, we cannot have the same momentum. Will they have the same kinetic energy? Kinetic energy depends on mass also, because it's mv squared. Potential energy depends on the mass, so it cannot be the same. So in other words, only option that is reasonable is option B. Acceleration needs to be the same, regardless of the mass or the height. Okay, 1.3. Two asteroids S and T are having masses m and 2m respectively. They are on the course for a collision. Okay? So if the magnitude of the acceleration on S is a, then the magnitude of the acceleration on T is. Now, for as long as the collision is going to take place, the Newton's third law will have to apply. So the F net on this case is going to be ma, and then the F net in this case must be 2m multiplied by a. Let me just call that as and at, but it's just the same acceleration, so let me just keep it the same, just a and a. So for me to get this acceleration of t, the force that will be acting will be equal, but just in the opposite direction. So ma is equal to 2m at. Then I make 80 the subject, so the m will cancel the m, and then 80 is going to be a over 2, which is a half of a. And option B is going to be my option to go with. And then 1.4, a sound source approaches a stationary observer at a constant velocity. Which of the following describes the observed wavelength and the frequency from the sound source as it approaches? So the observed frequency, number one, for as long as the source is approaching, it must be greater. Okay, so we're going with option A and option D. Now, from V is equal to F lambda, or C is equal to F lambda, we can see that frequency and wavelength are going to be inversely proportional. So if one is greater, then the other one has to be less. So option D would be the best for that. And then 1.5, they're telling us two objects, M1 and M2, with a distance r apart, experience a force F. The mass M1 is now doubled and the distance is halved. The gravitational force between M1 and M2 now is. So from Newton's law of universal gravitation, we know M1, M2 divided by r squared. This is the original. Now, if we apply the conditions, it's going to be G 2M1, and then it's going to be M2, then divided by, say, the half r squared. So that's going to be 2gm1 m2 multiplied by 1 over 4r squared. When we simplify, 2 divided by a quarter, that must give us 8. So which means it's going to be 8 times the force, which is option D. Then 1.6, if we have an object that is thrown vertically downwards towards the ground from a height h with a velocity v. The object strikes the ground and bounces upwards. Then it's caught when it reaches the maximum height. So at maximum height, the velocity has to be 0. So this one, I'll consider it to be an option. This one, I'll consider it to be an option. These two are out because we are seeing that after bouncing, I'm assuming this is the maximum height. Okay, or this is the maximum height, but then it just continues. Maximum height, but then it continues. So B and D, they're out. Now, when I look at the direction of the velocities, if a ball or an object is thrown downwards, we expect the velocity to increase and not decrease. So option A is going to be the best because velocity is increasing. And then the bouncing, and then it gets to 0. So I'm going with option A as my best option. And then 1.7, the crate is pulled up a slope. Which of the following forces will do 0 work on the object? The pulling force, this one is going to do work. The normal force, since it's acting perpendicular, it might not do work. Frictional force is going to do work. Gravitational force is going to do work, since there's a component of the gravitational force. So I'm going with option B, which is the normal force. Then 1.8. Okay, 3 identical spheres x, y, z are placed together in a triangular arrangement, each touching each other. The spheres are then moved back to their original positions. So for us to get the net or the charge on each one, remember they must all have the same charge after the separation. So I'll get the total -5. Okay, so that's a -5. What's happening to my pen? Okay, so -5 plus 0 plus 2. This gives us a 3 negative. Then divided by 3, we get a -1. So A is the best answer for that. Then 1.9. A positively charged object has fewer electrons, yes, but compared to what, neutrons? No. It has fewer protons. This is wrong. It has fewer electrons, yes, than the protons. This one makes more sense. Okay, if the electrons are more, then the object will be negatively charged. Okay, so I'm going with option C because it's the only one that makes sense, because this one more protons than neutrons, no, can only have more protons than electrons. All right, then 1.10, the minimum resistance that can be acquired from a connection of two 4-ohm resistors. So when we have two 4-ohm resistors, remember the connection can either be in series or in combination, or in parallel. Okay, so if I look at the series combination, I'll have a 4-ohm and then a 4-ohm. So a 4 plus a 4, that will give me 8 ohms. That is maximum. Okay, and then if I look at the parallel combination, I'll have my product, which is 16 over the sum, which is 8, and then I'll have a 2. So I'm going to go with option B. Okay, because we say the product over the sum. So it's 4 times 4 over 4 plus 4. 16 over 8, it's 2. This is the smallest resistance that we can have. Okay, so that is how my number 1 would have gone according to the way I understood the questions. Okay. Then question number 2. Block M, that is 10 kilogram, is connected to block small m with a 2 kilogram with a rope T of negligible mass. Okay, there is a pulley here. Okay. Both blocks are at rest, and then the slope is 30 degrees with the horizontal. The frictional force cannot be ignored. And then they want us to define the term normal force. So it's a force with which you can say a surface a force which a surface exerts on an object, okay, with which we can say it is in contact. It is in contact and perpendicular to the surface. So something like that. That could be the definition of a normal force. And then they want us to draw a labeled free body diagram of all the forces acting on the 2 kg. So when you look at the 2 kg, it's just the tension and then probably the weight. So we're not going to waste time there. We're going to say this is tension and then that's the weight. Then they want us to calculate the frictional force needed to keep the blocks at rest. The frictional force needed to keep the blocks at rest. Okay, so what I'm going to see, I can look at it block by block. Okay, if I look at T, I know that I'm going to have the frictional force. I don't know which direction should I assume the object is moving. So since the 10 kg is bigger, I'll assume the direction of motion is this side. So I'll have Fg parallel, then I'll have my frictional force there. Okay, let me try to make sense out of this. So when I look at the first body of the 2 kg, okay, so we're gonna say that with the 2 kg body, with tension, let me start with net force is equal to MA. Okay, so tension minus the weight must give me the mass and the acceleration. But the objects are at the rest, which means they're not going to move. So our acceleration has to be 0. So which means the tension is equal to the weight, which weight is going to be 2 multiplied by 9,8. Okay, so when I punch that into my calculator, I'm getting 19,6 newtons. Then let me also consider the 10 kg body. So what we are saying is that we are assuming that the object is moving downwards. So which means the F net is going to be the Fg parallel minus the frictional force minus the tension must give us the MA. I don't know if that is going to make sense. So we're saying the Fg parallel minus the tension minus the frictional force must give us MA. But our MA will be 0. Then, since we're looking for the frictional force, we can just transpose it that side. Fg parallel is the same as mg, the sine of theta minus the tension is equal to the frictional force. The mass is 10 times 9,8. The sine of 30, I'm subtracting the 19,6. Why am I saying 19,n? Okay, I'll punch this into the calculator. 10 times 9,8 sine of 30 minus 19,6. This gives me 29,4 newtons. So this is what I'm ending up with as my frictional force. Okay, just to keep the object without moving. Okay, then 2.4. They're telling us that the rope snaps. Okay, and then M decides to slide down. The kinetic frictional force is 25 Newton. Okay, since there is no tension, the frictional force is going to be that much. Now they want us to draw a free body diagram on this 10 kg. So we can see that there is no tension. The friction is going to act upwards, and then we're only going to have the Fg parallel we're going to have the weight and then the normal force there. So how many marks is it? It's 4 marks. So we can have approximately 4 forces. Okay, so I'll just, let me get it this side. This is 2.4.2. 2.4, it's 0.1. Okay, so we said frictional force there. We said FG parallel. We're saying the weight there. And then that's going to be our normal force. So that should be our free body. Then for 2.4.2, they are asking us to calculate the magnitude of the acceleration. Okay, so we need to get the acceleration with which the object will be moving downwards. So what I'm going to do is I'll still consider more or less the same thing and look at my free body and say that my F net is equal to MA. So I'll have my FG parallel minus my frictional force must give me the mass multiplied by the acceleration. So mg sine of theta minus my frictional force, we already have it, must give us the MA. I'll substitute, so 10 times 9,8 sine of 30 minus the 25 must give us the mass, which is 10, and then the acceleration A, which I don't know. When I substitute, when I punch these numbers, 10 times 9,8 sine of 30, then I'm subtracting 25, I'm getting 24 on the left. Okay, is equal to 10A. Divide both sides by 10, which means our A is 2,4 meters per second squared. Okay, so that is what I'm getting for 2.4.2. And then we move on to 2.5. They're telling us that block M, the small block, just takes a half of a second to reach the ground. They want us to get the final velocity. Okay, so what are we going to do? So they're telling us that the time, this is 2,5.1, is 0.5 seconds. What do they want? They want us to get the final velocity, Vf. So V initial, I'm going to take it to be 0 initially when it was just hanging and dangling. Okay, so I'll use the V final is equal to V initial plus acceleration times delta t. So my V final is going to be 0 plus my acceleration now is going to be under free fall, which is going to be 9,8 multiplied by 0.5. And that's going to give me 4.9 meters per second. That's what I'm getting in that case. Since it's after the snapping, the object will just fall under the gravity. So that is 2.5.1, and then 2.5.2. How would the final velocity of M be affected if the mass was doubled? Okay, and dropped from the same height? Increase, decrease, or remain the same? So in this case, I'm going to go for remain the same. Okay, why? Because it's just more or less the same as the first question we answered under the multiple choice. Okay, so I'm going to say it's just going to remain the same. And the reason for this is that our velocity is independent of the mass. The velocity is independent of the mass, and the motion of the object will entirely be affected, I'll say, by only the gravitational force, gravity. gravitational force. So in other words, it would be some sort of a free fall. Okay, so that is question number 2. Question number 3, they are telling us that the Curiosity rover was dropped from 125 kilometers above the surface of Mars. The mass of the Curiosity rover is this much, and then the mass of Mars is this. The radius of Mars is 53.25% that of the Earth. Then they want us to state Newton's law of universal gravitation. So we know that objects in the universe, they exert a force between them that is directly proportional. Let me just write it this side. So it's saying 3.1. So the force between two objects in the universe is directly proportional to the product of the magnitude of their masses, and then inversely proportional to the square of the distance, between their centers. Okay, something like that. That would be universal law of gravitation. And then 3.2, they want us to calculate the weight of the Curiosity on Earth. So we know that weight is given as mass times gravitational force. We know that the mass is 899. We're multiplying by 9.8 because the gravity on Earth is 9.8. So 899 times 9.8, that gives me 8810.2 newtons. Okay, so saying this, 2 newtons. That is 3.2. Then 3.3, they want us to get the gravitational acceleration on Mars. Let me just write it. So we know that G is equal to capital Gm over r squared. Okay. So what is the value of G? G is given as 6.67 times 10 to the negative 11. What is the capital M? That is the mass of Mars, which is 6.42 times 10 to the 23. And now when it comes to the radius, we need to determine the radius of Mars. They told us it is 53.25, that of Earth. So for R, I'll say 53.25% multiplied by the radius of Earth, of the Earth. So I have to check the formula page. From the formula page, we can see that the radius of Earth is 6.38 times 10 to the 6. 6.38. Okay, so 6.38 times 10 to the 6. Okay, so what does this give us? 53.25% of 6.38 times 10 to the 6. So I end up with 3397350. Let me just use it the way it is. Okay, I'll substitute 6.67 times 10 to the negative 11 multiplied by 6.42 times 10 to the 23 over 3397350, but then I have to square this. Okay, so when I punch this into my calculator times 10 to the negative 11 multiplied by 6,42 times 10 to the 23, dividing it by 3,350 squared. It's giving me 3,71. That's going to be meters per second squared. So this is the gravitational pull or the force acceleration. Okay, then 3.4. Would the mass of the Curiosity be different on Mars than on Earth? Yes or no? The answer is a no. And what is the explanation? So mass is always constant. Mass is constant, but weight will change. So you can just tell us that the weight is dependent on the gravity and not the mass. Mass is independent of the gravity. Remember, mass is just a measure of content that an object is having, whereas the weight is the product of the mass and then the gravity. So if the gravitational force is different, which means even the weight will change. So that is question number 3. Question number 4. They're telling us that a learner that is standing at the bottom of the building throws a ball A upwards at a constant speed, at a speed of 11 meters per second, and ball A reaches the maximum height T. Then after 0.72, another learner standing on top of the roof. But you're already on the roof. Why are you on top of the roof? Standing on the roof of the building, throws the ball B upwards. The two balls reach point T at the same time as shown in the diagram. All right, they want us to define what free fall is. So free fall is just a motion. Okay, it's a motion. We can say during which the only force acting on the object, is the gravitational force. Okay, so that is free fall. And then a projectile. So projectile is an object. Okay, which object has an object which has an initial velocity. Okay, and this object will move. We can say moves under the influence of the gravitational force. Gravitational force only. So projectile is there, and then free fall is there. Okay, then 4.2. They want us to determine the time taken by ball A to reach the maximum height. So what do we have? We have the V initial, which is 11. We know that our acceleration is going to be the G, which is 9,8. We know that the V final is going to be 0, since T is the final point. They are asking us to get delta T. Okay? So by looking at the information I have, I can use the first equation. Okay. First equation, whereby I will say V final is equal to V initial plus A delta T. Just write the equation, you'll get a mark for that. So when I do my substitution, we know that our A is going to be the G. So V final is a 0, V initial is 11, plus, I'm going to say negative 9,8 multiplied by T, or delta T. Then I can transpose the 9,8 to that side. is equal to 11. So delta T is going to be 11 over 9,8. Okay, with my calculator, I'm getting 1,12 seconds. All right, then 4.2.2. They're asking us to get the initial velocity of ball B. So the fact that ball A takes 1,12 seconds to reach the maximum, it simply means that ball B is going to take a shorter time. So the time for ball B is going to be 1,12 minus the 0,72, since they're going to reach the maximum height at the same point. So 1,12 minus 0,72, I'm getting 0,4 seconds. Okay, question wants the initial velocity. So V initial is what I want. V final is 0. My delta T is 0,4. So I can still use the same first equation. So V initial plus A delta T. So 0, that's V initial, plus going to be negative 9,8 multiplied by 0,4. So I can move, no, let me just keep it there. So 9,8 multiplied by 0,4, that gives me 3,92. Move it that side, which means VI is 3,92 meters per second. Okay, then 4.2.3. They want me to get the height of the building. So what I can do for the height of the building, I can decide to get the displacement that the object A traveled. Okay, so the maximum height of A, and then I also get the maximum height of B, and then I subtract it, and I'll have my height of the building. So 4.2.3, I'll do it this side. So I'll say the displacement of A. I can use VI delta T plus a half A delta T squared. Okay. So my V initial was 11. My time was 1,12 plus a half. I'm going to use negative 9,8 multiplied by 1,12 squared. Okay. When I punch this into my calculator, I'm getting 6,17 meters. Then I'll do the same with B, which is V initial of B multiplied by delta T plus a half A delta T squared of B. So the V initial, we got it as 3,92. We are multiplying by 0,4 plus a half multiplied by negative 9,8 times 0,4 squared. I'm taking the upward to be negative. Okay, so when I punch this into the calculator, I'm getting a 0,78 meter. So the height of the building is going to be YA minus the YB. So 6,17 minus 0,78. I end up with a 5,39 meters. So that is question 4.2.3 and the entire question that. Then 4.3. The following position time graph is given for the motion of the two balls A and B as described above. Study the graphs and answer the questions below. Okay, so ball A started from the ground and we said it reached point W, or it reached the maximum. So we are assuming this is our maximum point. So the maximum point was reached after 1,1 seconds. And then we saw that the maximum point for ball A is 6,17 meters. Even ball B reaches that height. But then the difference between the two, because it's going to be after 0.72. This when this one is projected. So the difference here is the 0.4 time it takes for this one to reach the maximum. Okay. And then the position, we say this one is at the top of the roof, on top of the building or at the roof. And then we say that height was 5.39. Okay, 5.39. Okay. So let me just punch those values down here. So my x is going to be 6.17 meters. Okay, my y, we are saying it's 5.39 meters. Okay, and then my z is 0.72 seconds, and then w is 1.12 seconds. So that is question 4. Question number 5. Okay, they are telling us that a wrecking ball is used to demolish an old building by smashing it. Okay, so this ball has a mass of 950 and suspended in air with a rope. They're at 3.5 meters above the ground. The ball is then released. So at the point of suspension, it's not moving. So our initial velocity is 0. The ball is at a height of h above the ground. Ignore that term. Then 5.1.1 state the law of conservation of mechanical energy. So we can say that in an isolated system, the total mechanical energy, or the mechanical energy, is conserved or remains constant. All right, then 5.1.2, the ball swings and hits the building at a height h. Calculate the speed with which the ball hits the building using only energy principles. Okay, so when we are to use energy principles, remember, mechanical energy is conserved. So at a height of 3.5 meters, the ball is having EP max, and then the EK is going to be 0. But then at a height of 1 meter above the ground, the ball is having EP and EK, which must be equal to the EP max since there is conservation. What are they asking for? They want us to get the speed with which it hits. Okay, so what I'm going to do, let me get the EP max first, which is mass, gravity, and then the height. So 950 multiplied by 9.8 times 3.5. Okay. Let me just combine the whole thing into the equation. Is equal to the EP at 1 and then the EK at 1. So which is 950 times 9.8 times 1 plus a half times 950 and then b squared. Remember, this is mgh and then a half mv squared is equal to that. Okay, so my left hand side we say 950 times 9.8 multiplied by 3.5. I'm getting 32,585. And then when I use 1 as a height, I'm getting 9310 is equal to 950 divided by 2 is 475. 475 is squared. Okay, so I need to transpose this that side. 32,585 minus 9310. Okay, I end up with 23,275 is equal to 475 is squared. So divide both sides by 475, and then let's take the square roots on either side. So 475 and then square root of that, which means our V, I'm getting a 7 meters per second. All right, so that is 5.1.2. Then 5.1.3, they're telling us that what happened? Okay. Okay, so the ball hits the wall and takes 0.1 seconds to stop and then rebounds. Calculate the magnitude of the force with which the ball hits the wall. So what we're going to do here is we can look at the impulse. Okay, so this is 5.1.3. You know that F delta T must give us the change in momentum. So since the ball is hitting the wall with this, so this is our V initial, and then our V final is going to be 0. Okay, so let's see, we're saying force is going to be the change in momentum over delta T. So that's the mass V final minus V initial over delta T. The mass was 950. I'm multiplying it by 0 minus that. It's going to be 0 minus 7, which is negative 7 over 0,1. Okay, so 950 times 7 divided by 0,1. I end up with 66,500. Okay, so that is negative 66,500 newtons. So it's just 6,500. What was the question asking for? Determine the magnitude of the force with which the ball hits the wall. So it's just in the opposite direction. Okay, so newtons. Okay, so that is 5.1.3. And then 5.1.4, write down the force that the wall exerts on the ball. So it's just going to be the same force. Okay, so we said it is 6,500 newtons. Then name and state the law. So it's Newton's third law that is used to arrive at this. And how do you state that? And say that when body A exerts a force on body B, saying that body B reacts by exerting the same amount of force. So exerts a force of equal magnitude, but in the opposite direction. Opposite direction. Okay, so that is how 5.1.4 will be answered. So Newton's third law, and then you state the third law. Then 5.2 are telling us that there is a grade 12 learner with a mass of 75 kilograms that is on a skateboard of mass 2 kilograms that is moving at a constant speed of this much east over smooth surface. There's a ball of 500 grams that is moving at that velocity west that is thrown to the learner. Then the learner catches the ball, and then the final kinetic energy after the collision is this much. Calculate the initial speed, 5 Mach. So what I'm going to do, since I know that kinetic energy is given as a half mv squared, let me start by getting the final velocity. Okay, so I'll have my 146 is equal to a half, then the mass of everything combined. So the learner, the skateboard, as well as the ball. Okay, so that's gonna be 75 plus 277 plus this is a half of a kg. So 77,5 and then bf squared. Okay, then I'm gonna have my vf as the square root of 2 times 146 over 77,5. When I punch this into my calculator, I'm ending up with 1,94. So V final is 1,94 meters per second. But the question is asking for V initial. Then we need to apply the momentum, conservation of momentum. So I'll say mass of the learner, velocity of the learner, plus mass of the ball velocity of the ball. These are initials. Must give us the mass multiplied by the V final. This is going to be now the combined mass of everything. Okay, so initially we had a 75 and then a 2, which gives us now a 77. The V initial was a 2, plus the mass of the ball was 0.5, but it is moving in the opposite direction, which is negative V. The mass of everything combined is 77.5 multiplied by 1.94. Then I need to do my subtraction, so I'm going to transpose this to that side. So I'm going to have negative 0.5V is equal to 77.5 multiplied by 1.94, subtracting 77 times 2. This gives me negative 3.65. Then I'll divide both sides by negative 0.5. Okay, and then my V is going to be saying negative 0.5 becomes 7.3 meters per second. So that is 5.2. All right, then question number 6. They're telling us that an object that is having a mass of 85 kilograms was initially at rest on the ground, then it's pulled vertically upwards at a constant acceleration of this much by means of a light rope. Ignore resistance, the mass of the rope, or any effects. Then they want us to draw a body diagram of the mass while it is moving upwards. So 6.1, we know that for as long as the object is moving upwards, there's going to be the tension, and then there's going to be the weight. Okay. And then 6.2, name the non-conservative force that acts on the mass. Okay, so we can go for drag or the resistance, but they told us we must ignore the resistance. Okay. And then any rotational effects. So we can go for the, what do you call that? All right, then 6.3. They're telling us to calculate the work done on the mass by the gravitational force when the mass has reached a height of 11 meters. So this is 6.3. So for us to get the work done, it will be the force, the gravitational force, multiplied by the delta x, and then the cos, I'll say 0. Okay. So our gravitational force is going to be the mass and then the g. So that's going to be 85 multiplied by 9.8 multiplied by the distance and then the cos of 0. Okay. Then when we multiply 85 multiplied by 9.8 times 11, that gives me 9163 joules. This is what I'm getting for 6.3. Then 6.4, state the work energy theorem in words. So we know that the net work done is equal to the change in kinetic energy. Okay. Then 6.5, use the work energy theorem to calculate the speed at the height of this 5 Mach. Now, when I look at this question, remember this object is moving upwards. I can look at it as a projectile. Okay. So if I use that scenario, I might end up losing the marks, but I will get the same answer. Okay. So let me, what do they want? They want the speed when the object is at a height of 11. Now let me use the work energy so that I don't deviate from what we have. Okay, so this is 6.5. So what I'm going to do is, since I had a free body diagram, I can start by probably getting the tension force. I mean, I was given the acceleration of the system. I can look for the tension and then look at the work done by almost everything there. So what I'm going to do, I'll say W net is equal to the change in EP plus the change in EK. Okay. But why do I need, no, there's no need of using this. I'll just use the change in EK. But for me to get the work net, I'll get the work that is done by the tension minus the work done by the FG. Should be equal to the change in the kinetic energy, which is going to be a half m V final squared. You can resubtract the V initial squared, it's fine, but we already know that the V initial is a 0. Okay, so we need to get the tension first of all. So we're gonna say that F net is equal to MA if I just focus on the body or the free body that I drew. So it's gonna be tension minus the weight should give us the mass and the acceleration. So which means my tension should be the mass acceleration plus the weight. So the mass is 85. The acceleration is 0.7. They said 5. Perfect. And then plus our weight, which is 85 times 9.8. Okay. So 85 times 0.75 plus 85 multiplied by 9.8. I'm getting 896.75 newtons. Okay, so initially, now I need to get the work done by this. Okay, so it's 896.75 multiplied by the distance, which is 11, and then the cos of 0, since it's moving the same direction. Okay, that's gonna be 9864.25 joules. Okay, so 9864.25 minus the gravitational, we got 9163 is equal to a half times 85 V final squared. Okay, so when I subtract that 9163, I'm getting 71701.25 is equal to 40. Is it 47.5? No, 42.5 V final squared. Then I'll divide both sides by 42.5 over 42.5. This cancels that, and then I need to find the square root on either side. So my V final is gonna be 4.06 meters per second. So even if I were to use the equations of motion, I was gonna get the 4.06. How? If I use the Vf squared is equal to Vi squared plus 2a delta y. We're looking for Vf. So it's gonna be square root, V initial is a 0, plus 2 multiplied by our acceleration, which is 0.7. Now I can't use that. No, I can actually. So it's 2 multiplied by 0.75 multiplied by 11 to give me that. But this does not apply to the work energy theory. Okay, then 6.6. They're telling us that a 30 kilowatt motor is used to lift the mass of 85 kilograms to a height of this. Calculate the percentage efficiency of that. Okay, so what we're going to do first of all, we know that our network was 9864.25, the network done by the tension, because we're focusing on the motor, and then the motor is having the cable within it. So we can say that power is given as the work done divided by the time. Is it possible for me to get the time, which will be work multiplied by the power? So the work done was the 9864.25 that we just calculated over the power, which is 30,000 watts. Okay. Then I'm gonna get, I divide that, I'm getting 0.329 seconds. Then I need to look for also the energy input, which is still gonna give me power multiplied by the time. So I'm moving in circles. So still the 30,000 for the motor, multiply the time it takes, which is 0.329. I mean, I'm just gonna get the same answer of this. And then when I look for efficiency, it's gonna be the input over the output times 100%. So our input is 9864.25. The output is just the same thing. We're multiplying by 100%. So the motor is 100% efficient, which is very rare. According to the question, this is what I'm getting, but in real life, it's hardly possible for something to be 100% efficient. Okay, question number 7. The siren of a rescue vehicle emits waves at a frequency of 360 Hertz, and then the frequency of the sound as heard by the listener that is standing by the roadside is 405. Define Doppler effect. So Doppler effect, we know that it is just the change, okay, in the frequency of sound detected, frequency of the sound detected by the listener. Okay, and why is this? It's due to the change in the velocities of the listener and the source, but relative to the medium of sound propagation. Okay, there you have your 2 marks. Then 7.1.2, was the rescue vehicle moving towards or away from the listener? Explain the answer, making specific reference to the frequency, wavefronts, as well as the wavelength. So the fact that the frequency is higher, okay, is going to be moving towards. Okay, so what's going to be our explanation? I'm going to say that the observed frequency is higher than the emitted. Okay, so as the vehicle approaches, okay, the wavelength decreases. The wavelength will decrease, and since wavelength is inversely proportional to frequency, then the frequency will be high. Okay, then 7.1.3, take the speed of sound in air to be 340, calculate the speed with which the vehicle is moving. So I'll do it this side. So we know that frequency of the listener is equal to V plus minus velocity of the listener plus minus velocity of the source times the frequency of the source. So they told us this was a 405. They told us that's a 340. I'm going to say plus on top. velocity of the listener is a 0, over 340 minus velocity of the source, which we want, times 360. Okay, so what I'm gonna do, I can have 405 over 360 is equal to 340 over 340 minus Vs. When I do my cross multiplication straight away, I can have 340 minus Vs is equal to 340 times 360 over 405. Okay, so when I simplify what is on the left, so on the right, I'm having 302,22. Then I just have to move this aside. Vs must be 37,78, which means it's 37,78 meters per second. Okay. Then 7.2, the driver of the vehicle continues at this speed past the stationary listener. What change or changes, if any, would occur in the following? Write down the values. So the frequency of the siren as heard by the driver. So this must still be the same. Okay, 360 hertz. The frequency that is observed by the listener. So now that frequency is going to be 340. It's going to be minus 0 over 340 plus the 37,78 multiplied by the 360. Okay, when I do that, you know that it should be smaller. I'm going to have 320,47 hertz. And then the speed of sound is still going to stay the same. Okay, 340 meters per second. So that is question number 7. Question 8. Point A and point B are 0,04 meters apart as shown. The sketch not drawn to scale. X lies this much, and then sphere X has 1238 electrons that were removed from the surface. So what is the nature of the charge on X? Choose positive or negative. I'm going to go for positive. Why? Because electrons were removed. For as long as electrons are removed, then the sphere will stay more positive. Then calculate the magnitude of the charge on sphere X. So I could use the formula or the equation. This is 8.2 of Q is equal to NE. They need the charge. So the number of electrons were 1238. Multiplied by electron charge is 1,6 times 10 to the negative. What is this? Yeah. To the negative 19. That's gonna make sense. Determine the charge. Oh, that's fine. So if that is removed, so if I multiply that, I'm gonna get 1,98 times 10 to the negative 16 coulombs. Okay. Let me just check this paper. Okay, mass of electron. Is this? Okay, that's fine. I'm gonna take that to be my answer. And then define the term electric field. So electric field is just the region of space, okay, in which a charged particle or a charged object experiences what we call an electric force. And then 8.4, draw a net electric field pattern of two identical with opposite charges. Okay, so we know that opposite charges usually do attract. Okay, so we're gonna have 8.4, that's a positive, it's a negative. Just have field lines that are moving. As long as the field lines do not cross. or do not touch each other. So the arrows should also be indicated correctly. Okay, so that is 8.4. And then 8.5. At point A or B, or at what point between A or B is the magnitude of the electric field due to the charged sphere X greater? We must explain our answers. So we know that electric field is given as a force over Q, which is the same as AQ over R squared. Let me use this. So you can see that the electric field is inversely proportional to the radius squared, which means if the radius is increased, the electric field is going to become smaller or weaker. And if the radius is smaller, the electric field is going to be stronger. So I'm going to go between point A or B. So I'm going to go with A. Okay? And the reason for that, I can say that E is inversely proportional to 1 over R squared. That could be my answer. But I can put it in words and say electric field is inversely proportional to the distance of separation, or to the square of the distance of separation. Then 8.6, calculate the electric field of sphere X at B if sphere X is replaced with that. So let's do that. KQ over R squared. So 9 times 10 to the 9 multiplied by now our Q, which is going to be 2 times 10 negative 9 over the distance of separation, which is going to be 0.03 squared, because the difference between that is that. Okay, then I'll just do the substitution. 9 times that and that, I'm getting 20,000 Newton per Coulomb. Then 8.7, a negative point charge Y with this is replaced at B. Okay, this is B. Let me just put it this way. Okay. So B is somewhere there. We have X, and then we have A. Okay, so we have 3.2, and then we have negative 2.8. Initially, remember, it was a 2, it's just a 2 times 10 to the negative 9 at point X. They want us to draw a vector diagram to show the direction of the forces on the charge X as a result. So why can't I just put it down here? We can see that B is positively charged. No, Y with this is now placed, so it's a negatively charged, 2.8. And then at A, we have a 3.2, which is positively charged, and then X was negatively charged. Okay. So between A and X, since the signs are opposite, there's going to be attraction. So which means at X, the force of AX is going to act to the right. And then since these two are of the same signs, is going to be repulsion, which means the force of B due to X is going to be on the opposite direction. So this should be your vector diagram. The force on X as a result of A, force of X as a result of B. That should be the vector diagram. And then 8.7.2, they want us to calculate the net electrostatic force between the two. So we need to calculate the FBX and then the FAX separately. Okay, so I'll come down and say this is 8.7.2. FA of X, KQ of A, Q of X divided by the distance of separation, 9 times 10 to the 9, multiplied by my A, we said is 3.2 nanocoulomb. So that's going to be 3.2 times 10 to the negative 9. Our x is negative 2, so just use the 2 times 10 to the negative 9 over 0,01, but everything is squared. Okay, so when I punch that into my calculator, I'm getting 3,2, and that I'm getting 5,76 times 10, 1, 2, 3, 4 to the negative 4. This is newtons. And then f v of x, still the same formula, substitution, negative is positive 9, multiplied by 2 times to the negative 9, multiplied by, we say it's going to be 2,8 times 10 to the negative 9. Dividing this by 0,03 squared. This is going to give me 5,6 times 10 to the negative 5 newtons. Then my F net is going to be 5,76 times 10 to the negative 4 minus 5,6 times 10 to the negative 5. Okay, so that gives me 5,2 times 10 to the negative 4 newtons. So that is the net electrostatic force. Okay, then question number 9, telling us that a circuit diagram is set up as in the diagram below. Resistors R1, 2, and 3 are identical, which means they have the same value. Switches S1 and S2 are closed. Ignore the internal resistance because it's for third term. Good. Then they want us to state Ohm's law in words. So we know that Ohm's law will tell us that the potential difference across an electric conductor is directly proportional. It's directly proportional to the current through the conductor, directly proportional to the current through the conductor at a constant temperature. So the temperature has to be the same or constant for that to happen. 9.2, they want us to name the component of a non-ohmic conductor in the diagram above. So I'm going to go for the bulb, or some people call it the lamp. Okay, because resistors are all ohmic. The ammeters, these ones just measure, so they cannot be used as non-ohmic conductors. So I'm going for the bulb because name the component of a non-ohmic conductor in the above. The component. So we know that the bulb, what does a bulb have? What do we call those springs inside that give the light? That could be also an option to tell us that those constants. Okay, then 9.3, write down the reading of the voltmeter with both switches closed. So if both switches are closed, these systems are going to be in parallel. And if that is true, which means the voltage is maintained, it has to be the same. So it's going to be a 12V. Then S2 is open, and it's just these two that will be in series. But we know that the total voltage across the VR2 and the VR3 must be equal to the Macoule V. So still 12 volts, since the voltmeter is connected across the terminal. Then 9.5, switch S2 is closed and S1 is open. Now the moment you open S1, there is no current that is flowing. Nothing is happening there. They want us to get the voltmeter read. So it's going to be 0V. then S2 is opened, how would this affect the ammeter reading? So if this resistor is out and we have just this two, is the ammeter reading gonna stay the same, increase or decrease? Now let's take this to be 2 ohms, 2 ohms, and then 2 ohms. These two are in series. For them to be combined, we shall have just a 4 ohm resistor, one block that is a 4 ohm. Now the moment we have a 2 ohm and a 4 ohm combined, if both switches are closed, we shall have a product over the sum, which is like 8 over 6. That's 4 over 3, which is 1,3 ohms. That's going to be our effective resistance. Now, if this resistor is out, we're going to have an effective resistance of 4 ohms, which is bigger. So if the resistance is bigger, the current is going to be. Let's see. If that is going to make sense, let's see. Telling us if S2 is opened, okay, so there's no more flow of current this side. It's just the same current that is flowing through the circuit. Originally, the ammeter reading was constant. So if switch S2 is opened, how would this affect the ammeter reading? But the ammeter reading is connected, not even close to any of these. So the ammeter reading is going to stay the same, guys. It stays the same. Okay, then 9.4, both switches are opened. Resistor R1 is removed. How would this affect the voltmeter reading? So both switches are closed, but then R1 is removed. So there's no resistor here. It's just that. Is there any voltage across? Is there any voltage across? Yes. So how will it affect the voltmeter reading? Voltmeter reading is gonna stay the same. It's gonna stay the same. So guys, that's all that we have to do. But remember, this is a proposed memorandum. Yes, there could be hiccups here and there. We're human, okay? If there are any issues, please just load them under the comment section. We shall rectify them. With multiple choices, we can use elimination format before we can get to the correct option. Okay, so we have various options that have been provided as possible answers. The following: each question has only one correct answer, and we need to choose that correct answer and then write that in our answer book. Okay, so I'll start with question number 1. So which one of the following quantities is the tendency of an object to resist a change to its state of motion? Is it inertia? Is it impulse? Is it momentum or acceleration? So we know that acceleration cannot apply that. Okay, because acceleration is the rate in change of velocity. Momentum is the product of mass and velocity. Impulse, it's something else. So the correct option would be A, which is inertia, the tendency of an object to resist motion from Newton's first law. Okay, then 1.2, we have a ball that is dropped from rest at a height above the concrete floor. Okay, and then they're telling us that this ball strikes the floor and bounces vertically up and down on the same spot on the floor. So the velocity time graph is being drawn for us for the bouncing ball. with the points P, Q, R, S representing the different times during the motion. So this point here will represent the time when the ball was just at that height. And when it is dropped, probably it's moving, and then reaches the floor. Okay, and then it starts to move up. And then at this point, it's probably reaching maximum because you can see that the velocity is 0 at Q. So probably that's the point where the ball reaches its maximum and then drops down, and then at point R, and so on and so forth. So what are we going to say? At which time does the ball reach its maximum height? After the first upward. Okay, so when you talk of first upward, remember here it's coming down. And then between this point and this point, the ball is going up. And then as it goes up, the velocity decreases. We have in that point where the velocity is 0. So point Q will be our answer, and that is option B. And then 1.3, we have two blocks, P and Q of masses M1 and M2, respectively, that are held at rest on a frictionless horizontal floor. Both of them are being compressed with a spring, as shown. So blocks are released, and then the spring decides to drop to the floor. Block Q, this one moves to the right with velocity V. What will happen to P? So in normal cases, under the conservation of momentum or impact, we know that the momentum or the impact that Q will have on P would be the same, but just in the opposite direction. So in this case, they are asking us to determine the momentum of P. Okay. Now, since they were held together with a spring, and then the spring was removed, so we expect the reaction to be the same, but just in the opposite direction. So if Q is having M times V as its momentum, so it's M2 times V, then the same should be applicable to P, but in the opposite direction. If this is to the right, then this is going to be to the left. So we expect to have M2V, but to the left. Is there an option like that? M2V to the left, that is option D. Okay, then 1.4, they're telling us that the magnitude of the gravitational force that spheres X and Y exert on each other is F. So from Newton's law of gravitational force, if that is X and then that is Y, if these two are separated with distance R, what happens? So we know that the force is directly proportional to the product of the masses, and then inversely proportional to the square of the distances apart. Now the mass of X is doubled. So instead of us having M, we're gonna have twice M, 1. And then they're telling us the mass of Y and the distance just remain the same. Okay, so which means our new F is gonna be G, and then twice M1, and then M2 over R squared. We can move this 2 in front so that it is a G, M1, M2 over R squared. Okay, so we're seeing that this is representing the F, and it is the same thing that is there. So which means our final result must be 2F, or twice the original force. So remember, the force that X exerts on Y should be the same force that Y exerts on X, but in the opposite direction. Okay. So they're asking us which one of the following combination is correct for the magnitude of the forces that the spheres exert on each other. So remember I said they have to be the same, but currently our force has to be twice the original F. So this and that, which is option D. Then 1.5, hot air balloon, vertically downwards. Is moving vertically downwards at a constant speed. This is in capital letters, okay? So something is happening. So constant speed, so velocity is the same. Assume that the mass of the hot air balloon remains constant. So mass is the same, speed is the same. Okay, which of the following physical quantities associated with the hot air balloon will change during the motion? So is it the weight? They told us the mass must stay the same, so weight cannot. Okay, is it the momentum? Momentum, remember, is mass times velocity. So if the mass is the same and the velocity is the same, this must also be the same. So momentum is out. Is it kinetic energy? We know that kinetic energy is a half mv squared. So if mass and the velocity are the same, which means kinetic energy is also the same. What about potential energy? We know that potential energy is mass, gravitational force, and the height. The mass, gravitation, or acceleration due to gravity, and then the height. So the height will keep on changing. There's no way height is going to stay the same. So it's the potential energy that is going to change during the motion. All right, 1.6, a learner that is standing by the roadside records the frequency of sound waves that were produced by a siren of an ambulance, okay? So the ambulance is moving at a constant velocity along the road, and then they drew the graph for us. So the y-axis is representing the detected frequency or the frequency of the listener, and then as time passes. So what we can see is that the graph is below, which means the frequency starts by being low, and then all of a sudden the frequency increases. What does this tell us? So if the frequency of the listener overall increases, which means the ambulance is approaching the learner, or it's moving towards the learner. Yes, approaches the learner. Okay, that is the kind of conclusion you can have. So probably it was moving from a distance and then it comes towards the learner. Okay, so which of the following statements concerning the motion of the ambulance is correct? So the ambulance approaches the learner and then passes the learner. You see, if it's approaching then passes, then we'll have another extension where the frequency drops again. Okay, so this is a 1-2 approach. It's either approaching or leaving. Okay, so because of this last statement, I'm nullifying A for now. Okay, then let's look at the second option. It moves away from the learner and then turns and approaches the learner. Moves away. So when it's moving away, the frequency is low. And then when it approaches the learner, the frequency increases. There's some truth in that statement. Let's see, option C. It approaches the learner and then turns and moves away. No, that is not correct, because if it was turning away, then the second part of the graph would be below, or would be lower than the first one. And then moves away from the learner and then stops. This is out. So I'll take option B because it has some bit of truth in it. It moves away and then turns and approaches the learner. So as it's moving away, the frequency is below or less. And then as it's approaching, the frequency that will be observed by the learner will be high. So option B is the correct answer there. And then 1.7, we have two identical spheres, X and Y, that are carrying +2 and then -6 Q respectively. Sphere X experiences a force F to the right, X to the right, when the distance is that, all right. Then the spheres are brought into contact and then return to the original positions. Which one of the following represents the magnitude of electrostatic force that X experiences now? So just like Newton's law of universal gravitation, it's just the same as electrostatic force, okay? What differs is just that this has a constant of K, not G. Okay, and then in this case, we're going to be talking about charges Q1, Q2 over R squared. Okay, I'm not going to simplify everything. I just need to look at what's going on. So I'll maintain the K, I'll maintain the R squared since those are constants. So this will be a 2 times a 6, okay, which will give me 12K over R squared. So currently, before the spheres touch each other, this is the force that each sphere will exert on each other, okay? Then when spheres are brought into contact with each other, okay, so a positive 2 and then a negative 6, the charges are going to combine, and then the resultant charge on each sphere will be divided, or will be a result of division between the sum of the charges. So this would be 4 plus negative 6, that's going to be negative 4 divided by 2, which means after the separation, each sphere must be a negative 2 charge. If the distance is still the same, then you try to look for the force, that is K, Q1, and then Q2. So that's over R squared. So that's a K. That is a K. I'm maintaining the K. Q1 is a 2, my Q2 is a 2 over R squared. So that's going to be 4K over R squared. Remember, this was 12K over R squared. This is 4K over R squared. So this is the new force. This is the original. So which one of the following represents the magnitude of the electrostatic force right now? So when you divide 12 by 4, or when you divide this force by this force, it's going to be 3 times smaller. Okay, so if it is 3 times smaller, which means it's 1 over 3 of the original force. Get this new force, divide by the original force. So the option I'll go with is B. That is 1.7. Okay. Then 1.8 in a circuit diagram below, R1, R2, and R3 are identical resistors. So identical simply means they have the same value, and the battery has negligible internal resistance. Okay. What happens to the power that is dissipated by R1? No, they're telling us the power dissipated by R1 is P. Okay. So if the power dissipated by R1 is P, the question is asking us, what happens to the power that is dissipated by R2? Now, if I were to assume that, okay, so I'm saying if I'm to assume, let's say, since they're identical, I can call this 2 ohms, as well as 2 ohms. I can just come up with I can set 10 volts as my voltage there. Just I want to bring about the picture of everything. So the effective resistance within this parallel combination, remember we have 2 resistors, so product over the sum, that's going to be 4 over 4, which is 1 ohm. Okay, that is for the parallel combination. Now, since this parallel combination is going to be in series with R1, I'll plus the 2 ohms, which means my effective resistance is going to be 3 ohms. Then if I want to find the current, because I need the current that is passing through, current is going to be given as V over R. Okay, so if I have 10 over 3, which will be the same as 3 comma something. Okay, let me just leave it as 10 over 3 ohms. Okay. Then I know that from the formulas of power is given as IV. Okay. Or I can use the combination that has what? Because now this 10 over 3 is the current that is flowing through this entire circuit. And it's the same current that is going to pass through the R1. So if I were to look at, do I need the voltage? I can use I squared R. Okay, let's say I'm looking for the power of R1. So it's going to be 10 over 3 squared times the 2. Just 10 over 3 squared. That's going to be 100 over 9. Okay, and then times 2. That's going to give me, I need the fraction. It's going to give me 200 over 9 watts. Okay, that's the power in this. Then what will be the voltage of R1? Voltage of R1 is going to be 10 over 3 times the 2, which is going to be 20 over 3 volts. But if my original was a 10, then I'll have 10 minus 20 over 3. Okay, 10 minus 20 over 3, which gives me a 10 over 3 volts as well. Okay, so we're saying that this voltage is going to be the voltage of the parallel combination. Okay, now we have the voltage, we can get the current that is passing through there, or we can directly look for a formula that has voltage, because we know the voltage across R3 is going to be the same voltage across R2. Okay, the power formula that combines voltage and resistance, is P is equal to V squared over R. Okay, so when I get my voltage, which is 10 over 3 squared, and then I divide it with my R, which is a 2. Let's see. That's gonna be 100 over 9, and then I'm dividing it by 2. What do I get? I end up with a 50 over 9. So this is the power in 2. This is the power in 1. So now the question is asking, which one of the following represents the power that is dissipated by R2? Okay, so the question is, how does this, remember, for R1 is the same as P, this P. So how does this relate with this? Okay, how does this 200 over that relate with that? So what I'm gonna do, I'm gonna say if I have 50 over 9, then I divide it by 200, still over 9. I'm getting 1 over 4, okay? So I'm saying 50 over 9 divided by 200 over 9. Then I'm getting 1 over 4. So which means this R2 is a quarter of P. And the correct option is A. So I just had to come up with numbers just to create an idea of what's going on there. Then 1.8, they're telling us that the following is a simplified drawing that represents a DC motor. Okay, so one thing we know about DC motors or AC motors is that they use what we call the Fleming's left-hand rule. Okay, that's the basic thing we need to know. They are asking us, okay, that the diagrams below indicate some changes that we made to the motor. So we can see the north and the south being switched around. And then you can see that the terminals are also being switched around in the second option. And so on and so forth. Okay, what is the question asking for? Which of the changes to the motor above will change the original? Okay, what changes are going to change the original direction of rotation? Okay, so what we need to know is from the original, this is the positive and this is the negative, which means current is going to flow in this sort of direction. okay, because current flows from the positive towards the negative terminal. We know that the field is from the north to the south pole. Okay. Then if we apply our Fleming's left-hand rule, okay, what is happening? All I can see is that this structure of ours, or this plate of ours, or coil, is going to rotate in which direction? Which direction is this? Okay, this is going to be downwards. So which means it's rotating in the anti-clockwise direction. Okay, if I use my Fleming's, I'm going to end up having something like that. Okay, if this is my force, so this is my thrust of the force, this is the field, and then this is the current. I'm just looking at this part alone. The field, current, then it's going to go down. Okay, once it goes down, then the rotation is going to be anti-clockwise. Okay, so the question is asking us what change, or from the given drawings, which one is not going to be anti-clockwise? In other words, which one is going to be clockwise? So changes were made. If I'm to get the question correct, which of the changes will change the original direction? So we want something that's going to create a clockwise direction. Okay, so let's see from diagram number 1. So current is moving in the same direction, but what is being changed is the polarity of the magnets, that now the field will be moving in that sort of direction. So if I look at, I don't know, I will still just look at this side alone. Okay. Okay, so from our Fleming's left-hand rule again, when I try to twist this kind of thing, okay, so I'm looking at this green line. Does that make sense? Green line, green line. Yes, this is going to be moving upwards. Okay, because current is moving that side. So if I'm to draw more or less the same thing, where this is at 90 to each other, it's going to be moving upwards. It's moving upwards. This is a clockwise direction. Okay. Let's try to look at option number 2. Option number 2, the field is to the right, current is moving in that sort of direction. Okay. With my Fleming's left-hand rule, let me just look at just this portion. Just this portion, okay? Current is moving in this direction, and so this one is moving upwards also. So which means it's a clockwise. Okay? Let's look at option number 3. If I focus, current is moving in this sort of direction. If I look at my field, and focus on this, that current is moving in sort of direction. Okay. Current, where are you? See, your field is moving that way. So it means it's going to move downwards. This one moves downwards, which is the anti-clockwise. Okay, anti-clockwise. So, which of the following changes will change the original? So, number 3 is original. Okay, so 1 and 2 are the changes that are going to change the original direction, since both of them are giving us the clockwise. So 1 and 2, which is option A. Then 1.1.0, 1.10. An atom has a ground state energy, that is X. When the atom moves to a higher energy state, which is Y, there's a line spectrum that is observed. Okay. So one thing we know is that when atoms move, so we say if the energy at ground is X and the energy at the higher state level is Y. When that happens, there's an absorption that will take place when atoms move from low energy levels to higher energy levels. That is absorption that is taking place. When they move from high energy levels to low energy levels, that's when they emit their energy. Or that's when they emit light in the form of that. Okay, so our options have to be C and D. Okay, since there is absorptions moving from a low energy level to a high energy level. Then the change in the energy, since this energy is higher than this one, so the change is always highest minus lowest. So Y minus X, and then that's the absorption. So I'll go with option D. Okay. If there's any difference, please let us know under the comment section. Okay. Then question number 2. Question number 2. They're telling us that a block A of mass n is connected. A block of mass n is connected to block B of mass 7.5 kilograms by a light inextensible rope passing over frictionless pulley, as we can see. Okay, we have a height of 1.5 meters above the ground, and so on and so forth. All right, let me just try to decrease this so that we can see the entire question. All right, I think that's much more better. Okay, this is our height, that's all that. All right. So while block B is released, okay, remember, initially it's been held at this point without moving. When B is released, it moves vertically downwards and strikes the ground with 3.41 seconds, or meters per second. Okay, if we are ignoring friction, can we show by means of calculation that the magnitude of the acceleration of block B is 3.88 meters per second squared, while the block was moving vertically downwards? So what I can see is that if our focus is on block B alone, then we shall assume something like a free fall in that case, where the motion is entirely under the influence of acceleration due to gravity. It's more like a vertical projectile kind of scenario, okay? And if I'm to look at it in that form, then I'll have to apply those equations of motion, okay? In this case, I could say that, what do I have? I have my displacement. So change in Y is 1.5. What else do I have? I have my final velocity, which is 3.41 meters per second. What is our initial velocity? It's a 0. Okay. Is there anything else we need? Is there anything else we have? We want the acceleration. Okay. Projectile. Okay, that's fine. So I can say that if I have V squared, Vf squared is equal to Vi squared plus 2A delta Y. Okay. So I know my final, my initial I know, acceleration is what I want. I have my displacement. Okay, so this is going to be 3,41 squared is equal to 0 plus this is 2 times 1,58. Okay, when I have 3,41 squared, that's going to give me 11,6281 is equal to 3a. Then I'll divide both sides by 3. And then what is my a? My a is 3,876. When I round it off, I'll get 3,88 meters per second squared. Okay, so that is how I would go about answering 2.1. Then when I look at question 2.2, okay, 2.2, they're asking me to draw a labeled free body diagram showing all the forces that are acting on B. So when you look at B, there's just weight that is acting downwards, and then this tension force that is within the rope. Okay, so my free body would be just tension, and then we're saying this is the weight. That is just enough. And then 2.3, can we state Newton's law, Newton's second law of motion in words? Okay, so there are different formats, there are different scenarios to this law, but they are just some keywords that we normally want. Okay, and so one can say that the net force that is acting on a body, an object, is directly proportional. Okay, the net force acting on an object is directly proportional to the acceleration. The net force is directly proportional to the acceleration and inversely proportional to the mass of the object, the net force acting on an object is directly proportional to the acceleration and inversely proportional to the mass of an object. Okay. And one thing we know is that this acceleration will always be in the direction of the force, directly proportional to the acceleration and inversely proportional to the mass of the object, and acts in the direction of the object, direction of motion of the object. Okay, just play around with those words, but for as long as we see this word of directly proportional, okay, so that the force is directly proportional to the acceleration. At least it must be within your statement. And then inversely proportional to the mass, and then acts in the direction. So they're just keywords that we're interested in, but play around with the English. Then 2.4, they want us to calculate the value of M. Okay, M is the mass of the second body by applying Newton's second law on each block. Okay, so when I look at my object A, I have tension that will be acting upwards. And I know weight will be acting downwards. So from Newton's second law, we know that F net is equal to MA. Okay. And then when I look at, we're saying body A, my F net is going to be the tension, which, because I'm assuming if the whole direction is moving downwards, whereby B is moving downwards, which means A is going to move upwards. And for A to move upwards, the tension must be slightly greater. Okay, so I'm going to say tension minus the weight of A must give me the mass of A times the acceleration. Okay, I can do my substitution. I don't know my value of the tension, so I'll say weight is given as the product of mass and the gravitational force. So I'll say weight. Why don't I just move everything so that I can make tension the subject, so that I have mass times my acceleration minus my weight, which is going to be mass times the gravitational force. So what is this going to become? Mass is common. I don't know the mass of A. So that's going to be my A, which is 9, sorry, the acceleration that we got, it was 3,88. Okay, that's 3,88. When this one moves that side, it's a plus, sorry, it's not a minus. And then that's 9,8. So guys, I'm factorizing out the mass. I'll be left with the acceleration and then the gravitational force. So which means my tension is gonna be, what's 3,88 plus 9,8? I'm getting 13,68, 13,68 M. I'm gonna call this equation number 1. Okay, and then when I look at body B, okay, with body B, remember we said the weight from the free body diagram that we drew. Okay, the weight is moving downwards, so which means the weight has to be a bit greater. So we're saying F net is equal to MA. So we're saying the weight minus the tension must give us the mass and the acceleration. So the weight of B, remember our mass for B was 7,5 times 9,8. From the definition of weight, we said mass and the gravitational force. We are subtracting the tension, which we don't know, should give us the mass, which is 7,5 times 3,88. Okay, so when I simplify, or I can even substitute at this level. Okay, but let me first simplify. I know I have 7,5. Hello, 7,5 times 9,8. That's 73,5. Minus my tension is equal to 7,5 times 3.88. That's giving me 29,1. Okay. I can move the 73,5 to that side. I transpose it. So negative T is going to be the same as 29,1 minus 73,5. When I get 29,1 minus 73,5, I'm getting negative 44. Okay, 4. Divide both sides by negative. So which means our tension is 44,4. Then I'll get this tension and substitute it into origin, the first equation, which means 44,4 is equal to, that was 13,68. 13,68 M. And then I can divide both sides by 13,68, divide by 13,68. Okay, when I do that, I'm getting 3, so my M becomes 3,2456, which is the same as 3,25 kilograms. Okay, so that is that with that question. And then 2.5. So we've answered 2.4, now we're going to 2.5. They want the maximum height above the ground that block A is going to reach. Now, for as long as there's motion and the entire system is moving, the entire system is going to move with the same acceleration of 3,88, because that would have been the other option that we could have used to get 2.4, okay, when you're calculating the thing. But since they wanted on each block, that's why we worked it out separately. So with 2.5, since the whole system is using the same acceleration, which means when this block B strikes the ground, okay, that would be the velocity with which block A will also be moving upwards. Now, since block B is gonna move 1.5 meters down, we expect block A to also move more or less the same distance up. But because of the 3.41 meters per second, and because of inertia, this body will continue moving upwards till this velocity dies to a zero. Okay, so what we need to know, or what we need to differentiate, is that after the 1.5 height, 1.5 meters height, this body A is still gonna continue with the 3.41, since at that height, body B is halving the 3.41. It's a system, so everything is more or less the same. Okay, so we're gonna say at a height of 1.5 meters, at h of 1.5 meters, A will have what we're calling the VI of 3.41 meters per second. And we know that at maximum height, at height maximum, the final velocity must be a zero. Okay, the question is asking us to find the displacement. So we need to find the height that the object moves. Good people, what do you think? What do you think? What do you think? What do you think? So I can use that formula of the VF squared is equal to VI squared plus 2G. If I use G, I can use A. I don't need to use G as such. I can use A delta Y. Okay. When I apply my substitution, we are saying our VF is 0 is equal to the VI, which is 3.01 squared plus 2. Why am I using a plus? It should be minus, since the body A is moving upwards. So I can say plus, then I can use negative 9, negative 9.8. Will it make sense? It makes sense for me to say that. Use 9.8. Why can't I use my acceleration, which is 3.8? 3.88 delta Y. Okay. Then I can move this to that side. I know that 3.88 times 2 is going to give me 7.76 delta Y, and then 3.41 squared is giving me 11.62. Does that make sense? Guys, I need to change this because remember, after the height of 1.5, this is going to behave as a projectile. So negative 9.8. It cannot be positive, the 3.8, because the system would have stopped moving because of the block B. Okay, so this must change to a 19.6. Okay, because 9.8 times 2, that's 19.6. Then I can divide both sides by 19.6 over 19.6. Okay, when I do that, Then my y is gonna be 11,6281 divided by 19.6. That's giving me 0.59. Okay, 0.593. So which means this is the extra distance that the block moves upwards before it reaches the maximum height. Now, since the question is asking for the maximum height above the ground, then we're gonna get our 1.5 plus the 0.593. And then that's gonna give us 2.093 meters or 2.09 meters. Okay, so that is question number 2. Let's look at question number 3. Number three. We have a ball A that is dropped from rest. Okay, the keyword there rest, and the height is 15.2 meters high. Then after ball A has fallen, just a small distance of 3.2 meters, a second ball is projected upwards from the ground. And then after a while, the two balls strike the ground at the same time. Okay. Let's see, define the term free fall. So one thing we said about free fall is that this is basically a motion of an object that is entirely under the influence of acceleration due to gravity. And so the motion of an object or motion that is entirely influenced or that is entirely influenced by acceleration due to gravity. That would be my mini description. Okay. Then they're asking us to determine the time that it takes for ball A to strike the ground. So when we look at ball A, what do we know about ball A? Okay, this is 3.2.1. So for ball A, we know that the initial velocity is a 0. The displacement that it must go through is 15.2 meters. Okay, is there any other information that was given? They want us to find the time. Okay, that is what we need. We know the final velocity. We know the final velocity. So good people, what do you think needs to be done? So when I look at this question, which equation of motion are you going to use? Because V final is equal to V initial plus this won't work. But since we don't have our final velocity, we can use this one where we look at V initial times time plus a half G times delta T squared. Okay. So our displacement is 15.2. Our initial velocity is 0. So that is going to die out. Since the object is moving downwards, I'll treat it as positive. So that's a half times 9.8 T squared. Okay, so 15.2 is equal to a half of 9.8 is 4.9 T squared. Then I'll divide both sides by 4.9. So 15.2 over 4.9 is equal to T squared. And then I'll take square roots on either side. So 15.2 over 4.9 gives me that square root of the answer. I'm getting 1.76 seconds. Okay, so that is what they want us to find for 3.2.1. Then 3.9.2, 3.2.2, that's one with me with 9. They want the magnitude of velocity with which B was projected. So guys, what I can see, remember, since we have our time as 1,7, we need to find out how much time did this object travel a distance of 3,2. And then perhaps if we can subtract that, then we could get the time with which object B is going to travel. Okay, to go up and even come down. Okay, the total time for object B. So I'll say that I'll say this is 3.2.2. Time taken for A to travel 3,2 meters. Okay, so I can still use the same formula of delta Y, delta T plus a half delta T squared multiplied by G. So where there's delta Y, I'll have my 3,2. You say that is a 0 plus, remember object A is going down, so I'll still take my G to be positive. So that is a half times 9,8 delta T squared. Then I'll have 3,2, I'll divide it by 4,9 is equal to T squared. And then I'll take square roots. Okay. So square root of 3,2 over 4,9 is giving me 0,81 seconds. Okay. So this is the time that the object A had traveled just for this small distance. Now, if that is 0,81, then how much time is left for object B? Okay, I'll say time of travel for B is going to be 1,76 minus the 0,81. Okay, 1,76 divided by 0,8, sorry, minus. Okay, so we said 1,76 minus 0,81, and that gives me 0,95. Okay, seconds. Now, remember the question wants the initial velocity for B. Okay? So if this is the time of travel, the total time of travel, I can look at a point where this object goes. I don't know where it ends, no? But then it's going to come back down. So it's saying the total time is the 0,95 seconds. So I'm going to take my displacement at that point, okay? So my displacement, I'm going to take it as a 0 because it went up with a positive displacement and then it came down to the point of projection. So my displacement is 0. My time is this. I need my initial velocity. So initial velocity is what we want. So from delta Y is equal to VI delta T plus a half G delta T squared. Okay, so where there is delta Y, I'm saying I'm going to use a 0. Initial velocity is what I need times 0,95 plus, I'm going to say a half times, since the object is moving upwards, then my gravity is going to be negative 9,8, but with a T squared. I simplify this. I'm going to take this, I'm going to move this to that side, to the left, the equal signs. So that's going to be 4,9 T squared is equal to 0,95. What's happening? What's wrong with me? Why am I not replacing T with 0,95? Okay, 0.95 squared. Okay. Then if I simplify this, I have 0.95 times 4.9. Okay, I can just cancel this with just one of these. Just pick my V initial as 4.655, which is approximately 4.66 meters per second. Okay, so that is that. Or if not, simplify this whole thing with the square and then divide by 0.95. You get the same thing. All right. Then the next question is telling us that on the same system of axes, can we draw a position time graph to show the motions of ball A as well as ball B? After time it was dropped and reaches the ground, we're taking the ground to be the zero position. We need to label the graphs A and B, and we need to indicate the following. So there is one thing we need to know. Let's see. With the initial velocity of 4.66, how far is the object going to go? Let's say I'm looking for the maximum height. So delta y is equal to vi delta t plus a half. Does that make sense? Let me use v squared is equal to v initial plus 2 g delta y. Okay, so my final is 0. That's 4.66 squared plus 2 times negative 9.8 delta y. So 4.66 squared gives me 21.716. It's going to be equal to 19.6. So 19.6 delta y. And I divide both sides, 21 divided by 19.6. I'm ending up with a very miserable answer, guys. 4.66 squared. Okay, that is 21. So which means this object is going to move just a small height and then it drops back. So which means it's not going to go beyond the 15.2. That's what I was looking for. So if this is our position, I can say delta y in meters. This is our time in seconds. So if this is my 15.2, this object is just going to move to that point. So if this is our time that we said it was 1.76. The second body, I'll call this A. Body B, we said starts at 0.81 seconds. It moves up, reaches its maximum, and then falls back within the same sort of time. Then I'll call this my B. So guys, this is how the graph for 3.3 would look like, according to me, guys, no? According to my understanding of the question. Then let's look at question number 4. So question 4 is telling us that trolley A that is having this mass moves 0.4 meters per second to the right in a straight line on a horizontal front, collides with a stationary. So if the velocity is 0.4 meters per second, which means the initial velocity here is 0, then after the collision, they're telling us that the trolley is locked together. In other words, they move as a combined body to the right. State the principle of conservation of linear momentum in words. So what we know about conservation, we can say that in an isolated system, okay, we can say that the total linear momentum. Momentum. What is spelling of momentum? It's constant. So what that means that it stays the same. The linear momentum before collision is the same as that after collision. Then 4.2, they want us to get the magnitude of the velocity of the trolley is immediately after the collision. So from the law of conservation, we know that mass A, velocity initial of A, plus the mass of B times the velocity initial of B must give us the velocity combined of mass A plus mass B, since they're going to have the same velocity after a collision. So the mass of the body A was 7,2. This is 7,2 times the initial velocity. We told us is 0,4. Plus, we know that the mass is 5,3 there, times the velocity 0 is equal to V into 7,2 plus 5,3. So we know that 7,2 times 0,4 is going to give us 2,88. We know this is a 0, so on my left I'll have 2,88, and then 7,2 plus 5,3, that's a 12,5 velocity. And I'll divide both sides by 12,5, divide by 12,5. So this cancels that. And then my velocity is going to be, what is it? I'm having 0,23. 0,2304. So just 0.23 meters per second. 0.23 meters per second. So that is the velocity of the combined, okay, 0.23 meters per second. Then 4.2.2, they want the average net force exerted by A on B during the collision, if the collision time or the time of contact is 0,02 seconds. Okay, so remember, they want the average net force. Average net force. So we know that F net is the same as mass times the acceleration. We know the acceleration now. You can say that acceleration is the same as the rate in change in velocity. Okay. So which means it's M, which is V final minus V initial over delta T. Or someone can look at it as the net force being the change in momentum. Okay, the change in momentum, so that it is F times T is equal to that. Then what we say from this, we know that our mass, we're going to use the mass of B, which is 5,3. The final velocity that we got was 0,23. The initial velocity of B was 0 since it was stationary over the 0,02. So when I substitute that into my calculator, this is 0,23 minus 0. Let's say 0, okay, over 0,02. The answer that I'm getting is 60.95. This is force, which means it will be measured in newtons. Guys, that is question number 4. Let's look at question number 5. Number 5, they're telling us that we have an electric motor that pulls a 20 kg crate from rest at point A up an incline by means of an inextensible rope. The inclined plane makes an angle of 18 degrees with a horizontal. We have B, C, and D are points on the incline, and the distance between A and C is 15.6. Then the motor exerts a force. Okay, this is important. So which means like the force applied is 96.8. And then there's a frictional force of 13.5. It's constant. Okay, define a non-conservative force. So we know that a non-conservative force is one where the work done, okay, is dependent, where the work done, let's say, depends on the path is taken by that force. Is a force where the work done depends on the path. Remember, for a conservative, it's independent. All right, then 5.2. 5.2, use the energy principles to calculate the speed of the crate when it reaches point C. So what I see is that, let's say this crate is somewhere there at point C. What forces will be acting on this crate? I can see the force applied. I just want the forces that are acting along the incline. And since it was moving upwards, then there's a frictional force somewhere there. And then there's also the FG parallel that will be acting along the incline as well. So since we say the work done depends on the path, I can try to look for the work done by each individual forces. And that work done, remember, is equal to the change in the kinetic energy. Okay, we know that work done is the force times the displacement, and then the cos of zero, or the cos of it in that case. So what I'm going to do, I'm going to say work done, or the net work is going to be F delta X, and then the cos of Z. Okay, but remember, this is our F net. Let's get the F net. F net, since the what? I'm going to have the 96. Why don't I just call it the force applied first? Okay. Plus, we can see the frictional force that is acting in the opposite direction. And then plus the FG parallel that is also acting in the opposite direction. Okay, so I'll just attach the negative signs just because they are working in the opposite direction. So this is 96.8. Okay. Minus, they say the frictional force was 13.5. I'm not changing that. Okay. And then minus FG parallel. Remember, FG parallel is given as mg, the sine of the angle of inclination, which is 18 in this case. So it's going to be 20 times 9.8 multiplied by the sine of 18. I'm just looking for the F net. When I punch this into my calculator, 733 times my delta X. Remember, delta X is the displacement, which is 15.6. And then I'll say the cos of 0, since it's acting in the direction of motion. Okay, so I'll multiply this times 15.6. That's gonna give me 354.63 if I'm to round it off. Okay, these are joules. But he's saying net work done is equal to the change in kinetic energy. So initially, the question was specific and told us that the initial velocity was at rest or zero. Okay, where is that statement? So the constant and that the matrix, that's this and that's when it reaches C. Okay, so which means I'm gonna have my 354,63 is equal to a half m, that is V final minus V initial, that's squared. Okay, so that's gonna be, what am I looking for? I'm looking for the velocity. So 354,63 is equal to a half times 20. Remember, my final velocity is what I'm looking for. Initial velocity is 0. So that's going to be V final squared. So that is 354,63. When I multiply a half of 20, it's going to be 10. Divide both sides, I have my VF squared, and then I'll find my square root. All right, so the square root of 35,463 is giving me 5,955. 5,955, which is approximately 5,96 meters per second. Okay, so that is what I'm getting. 54 to 5,96 meters per second. Okay, so guys, that's what we have. Then we look at the next question. They're telling us that when the crate reaches point C, the rock breaks. Okay, the crate continues moving up the inclined plane, and then it comes to a stop at point D. Okay, so at point D, the crate has stopped moving. Then the question is asking us, after stopping to move, it slides down past point B. They want us to draw a label diagram of this crate when it is moving down at point B. Okay, so at this point B, if it's moving downwards, remember there will be no longer the applied force. So what will be affecting this will be the frictional force and the FG parallel. Okay, this side, no, it's just the FG parallel that will be acting downwards, and the frictional force will be acting upwards. We shall have the normal force and then the FG perpendicular in that manner. So which means my free body diagram is going to have my frictional force. This is the FG parallel. You can have the FG perpendicular, then the normal force, Fn. So just that, how many marks is it? Question is 3 marks for 4 forces. It's reasonable. Then 5.5, they want us to draw a velocity time graph for the entire motion of the crate. So what I can see, okay, is that the initial velocity of the crate was here before it started pulling or being pulled. Then it reached a maximum of, we said 5,96. Okay. And then from there, the block continued slowing down. Okay, this is going to be velocity in meters per second. Okay, it slowed down and it got to a point, probably D, where the final velocity was a 0. and then it started dropping or coming down, sliding downwards. So remember, this must be straight lines, but this doesn't look like it. Okay. So I'm just going to draw a straight line. So we're saying this point is the point D, where the velocity is 0. After it snapped, it continued a little bit till the final velocity was 0, and then it came down. All right, so what do they want us to do for the entire motion until it passes point D, again on its motion down the incline? So you can just extend this limits. There's no harm in that. This was time in seconds. Okay, guys, I think that's that. Question number 6. Question number 6. A car is moving at a constant velocity of 20 meters per second on a horizontal road towards a stationary device, which can both emit and detect sound waves. The device emits. Okay, so this is the frequency of the source. Waves that are reflected off the car and then they are detected by the device. Define Doppler effect or state Doppler effects in words. So we know that Doppler, it does skip a question, guys. It does skip a question. That's 5.5, no? Yeah, we never skipped any questions. So okay, so we're saying Doppler effect. Doppler effect. What is Doppler effect? Doppler effect. Doppler effect, Doppler effect. Okay, so we say is the apparent change. Doppler effect is the apparent change within the frequency. Okay. Apparent change within the frequency of the source. Frequency of the source when there is relative motion. When there is relative motion, relative motion, not motive, relative motion between the source, okay, between the source and then the observer. Okay, something like that. Apparent change. Okay, assume the change when there is relative motion between the observer and then the listener. Sorry, observer and the source, because listener is the same as observer. Okay, then 6.1.2, they're telling us that if the speed of sound is 340, calculate the frequency of the reflected waves detected by the device. Okay. This question is 6 marks, guys. Because when you look at it, frequency of the listener. Something is fishy here. Okay. Let's see if we can break it down. Because 6 marks for was frequency of the listener from the formula. You know that it's V plus minus velocity of the listener over V plus minus velocity of the source times the frequency of the source. Okay. Let's see. So we know that the frequency of the source is 24,000 hertz. Then the velocity of the source is 0. Frequency of the listener, we don't know it as yet. Then we need to find what's gonna be the velocity of the listener? We said it's 22 meters per second. And then our V is 340. Okay, let's first find the frequency that the person in the car is gonna observe. So from FL, we have V plus minus, we said VL over V plus minus Vs times Fs. Now, since the listener is approaching the source, then we expect the frequency to increase, which means we're going to have a plus on top and then minus down. So that's going to be 340 plus frequency of the listener, sorry, the velocity of the listener is 22 over 340, that's minus 0, times the frequency of the source, which is 24,000. Okay. This looks to be for 6 months, which means there's something else that needs to be done as well. Okay, I have that multiplied by 24,000. I'm getting to 5,552,94 hertz. I can write this in circuit notation. There's no problem in that. 2,94 hertz. Okay. So that is the frequency that the listener is going to observe. But what is the question asking for? Calculate the frequency of the reflected sound detected by the device. So which means when this frequency is reflected, now the car acts as the source. Okay, so which means the frequency of the source is 25552,94 hertz. Now we want the frequency that is detected by the device. Okay, we know that the velocity is still 22, that is velocity of the source. Okay, velocity of the listener is going to be 0 now. Then we do the same thing, apply V plus minus VL over V plus minus Vs times the frequency of the source. So that is 340. Listener is going to be 0 since the difference is not moving. And then that's going to be 340 minus 22 times 25552,94. So 340 over 318 times 25552,94. Okay. 340 over 318 times 255,94. Is it going to make sense though? Let me try and look to decimals. Doesn't going to make sense. So I'm having 27,320,75 hertz. Okay, so this becomes the frequency that they want, that the machine detects, because there's a bouncing of, which means there is a trip of 2. There's going, and then this coming back. Okay, then 6.2. They're telling us that the spectral lines observed from a distant star will show that the star is moving away from the Earth. Explain by referring to the frequency how one can deduce that the star is moving away from the Earth. Okay, so one thing you need to know is that when the star moves away, the distance increases. In other words, the wavelength increases as the star moves away. As the star moves away. And one thing we also know is that from V is equal to F lambda, we know that our frequency is inversely proportional to the wavelength. So what we can say is that as the wavelength increases, okay, the frequency must decrease, or the frequency decreases. So what does this mean? It simply means that there's going to be a redshift. There is what we call a redshift, where the lines, or the spectral lines will move towards the red, the orange, and the yellow kind of thing. So that's what we call a redshift. So talk about the wavelength increasing and then the frequency decreasing, since the wavelength is inversely proportional. So we can just say wavelength or frequency is inversely proportional to wavelength. We don't need this. And just use this. Okay. And then just draw a conclusion. So there's a redshift towards the smaller frequency. Okay, then question number 7. Question number 7. They're telling us that 2-point charges X and Y are held at 0.03 meters apart as shown on the diagram. Then the charge X is this, Y is that. State Coulomb's law in words. So that is 7.1. 7.1, Coulomb's law. Coulomb's law. Okay. Okay, so we know that for any 2-point charges that are placed next to each other, the product, okay, or we can say that the force between the charges is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance apart. That is Coulomb's law. That the force between any 2 charges is directly proportional to the product of the magnitude of the charges and inversely proportional. They will say product of the charges Q1, Q2 over the square of the distance of separation. You know that when that is removed, then you have your Q1, Q2 divided by R squared, where K is a constant. Remember, it's 9 times 10 to the positive 9. Okay. Then they want us to draw the net electric field pattern due to the 2-point charges. So what we can see is that the magnitudes are the same, 7.2 and 7.2, as much as the signs are completely different. Okay. So I'll say I have my negative there, and then I have my positive. So from Coulomb's law, we know that like charges will repel, and then unlike charges will attract. Okay, just draw the line. What's wrong with me? Why is it moving in that direction? So the field lines must be seen to move from the positive up to the negative charge. Okay, we can have this, that, and then remember, these field lines should not touch or should not cross each other. The lines must be seen. I can add another line somewhere. So remember, since the magnitudes are the same, which means the number of field lines leaving one must be the same as number of field lines that are reaching other. Okay, 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, something like that. That is 7.2. Then 7.3, they want us to get the force, electrostatic force that Y exerts on X. Remember, this force has to be the same as the one that X exerts on Y. It's just the directions that will be opposite. So we know that the electrostatic force is K times Q1, Q2 over R squared. So we say that is 9 times 10 to the 9. The first Q1 is 7.2. Don't need to really stress about the sign. That's negative 9. And that's 7.2 times 10 to the negative 9. I'm dividing this by my distance of separation, which is 0.03, but squared. Okay. So when I punch this into my machine, 7.2 times 10 to the negative 9 times 10 to the negative 9 over 0.03 squared. Okay, I'm having 5.18 times 10 to the negative 4. Okay, since this is a force, so you can say newtons. Now someone will talk about the direction. Magnitude that force Y exerts on X. It's not a big deal. So that is the magnitude of the force. Then 7.4 has information that a third point charge Z with unknown positive charge. So which means there's a positive charge somewhere there. Is positioned that point X on the line. All right. Can we draw a labeled vector diagram showing the directions of the electric fields at a point X, at a point where X is positioned? So all we can see is that the electric field as a result of this is going to act in that direction. And then in this case, it's going to act in that direction. Since the signs are opposite, so there has to be attraction. Okay. So that, then it's going to be that. I can call this E, the result of XY, E as a result of XZ, or EZ and E. It's okay. No problem. So that has to be our vector there. Then 7.5, they're telling us that the magnitude of the resultant electric field. Okay. Remember, electric field is given as KQ over R squared. Okay, so I need to first of all get, we need the magnitude of Z. So we're gonna get the electric field in this direction, and then the electric field in this direction also. So I'll say the electric field, EXZ, it's gonna be KQ over R squared. So which is 9 times 10 to the 9 times my Q here, which is gonna be a Z over 0.01, but squared. Okay, so that's 9 times 10 to the 9 over 0.01 squared. That is giving me 9 times 10 to the 13Z. Okay. And then when I look at the electric field, XY, it's going to be the same. The Q that I'm using is the Y. The Q that I'm using is the Z over R squared. So 9 times 10 to the 9 times, we say 7.2 times 10 to the negative 9 over 0.03 squared. Okay, when I punch this into the calculator, 7,2 times 10 to the negative 9 over 0,033. I'm having 7,2 times 10 to the 4. Okay. But now they are acting in opposite directions. Okay. So one is going to be positive, one is going to be negative. So we're saying E net is going to be E xz, okay, plus the E xy. Let me try to do my substitution into the formula so that I can see what I get. So they gave us the net as 4,91 times 10 to the 5. Exz is 9 times 10 to the 13z plus, this is going to be negative 7,2 times 10 to the 4 xy. All right, then I'm going to move this to that side. I'll move that to that side. So that's going to be 4,91 times 10 to the 5 plus 7,2 times 10 to the 4 is equal to 9 times 10 to the 13z. I simplify the 4,91 times 10 to the 5. Okay, but I'm adding the 7,2 times 10 to the 4. That's giving me 5,63 times 10 to the 5. I'm dividing this by 9 times 10 to the 13. So what is my z? 9 times 10 to the 13. That gives me 6,25555. So that's 6,26, I think, times 10 to the negative 9. But since it's a charge, so I can call it coulombs. Or someone can call it 6,269 coulombs. No problem. No problem. Question 8. Question 8. They're telling us that a battery of some unknown EMF and some unknown internal resistance. So we don't know this, and we don't know the internal resistance as well. It's connected to 3 resistors and a high resistance voltage, 2 switches, and 2 ammeters of negligible resistance. All right. They want us to state Ohm's law in words. They want us to state Ohm's law in words. So with Ohm's law, all we need to know is that the potential difference across a conductor, is directly proportional. Directly proportional to what? To the current. Okay, but at a constant, to the current across the same conductor at a constant temperature. At a constant temperature. So that is Ohm's law. Then if both switch S1 and S2 are closed, the ammeter reading A1 is 1,5. Can we get the reading of the voltmeter? What's going on? Okay. So what I'm gonna do, since this and that are in series, I can combine this so that I have a total of 7 ohms. Okay. So the current through this is going to be 1,5. So I can say that the resistance, let me just say 8.2.1. The resistance at the bottom is going to be 2 plus 5, which we are getting as 7 ohms. And then the current is 1.5. We can get the voltage. V is equal to IR. And that is going to be 1.5 times 7. What is the question asking for? We want the voltmeter reading. So we need to get the voltage across. 1.5 times 7, I'm having 10.5 volts. So this must be the voltmeter reading. And then 8.2.2, they want us to get the reading on the ammeter, A2. So this ammeter reads the total current that is passing through the circuit. Okay. Now we know that this 7 ohm, if we combine these two and we get one single equivalent resistor, the 7 ohm and the 3 ohm are going to be in parallel. Okay. So since we know our voltage is 10.5 across, we need to get the effective resistance of the circuit. Okay. So effective resistance, I don't know, someone can get the effective resistance, but why should I go the long way? I feel like that is a long way. I know I don't need to combine. The voltage across a parallel combination is the same. So 10.5 is across this, 10.5 is across the 3 ohm. Why can't I just get the current? Okay. So I'll say from Ohm's law or from the Ohm's formula, V is equal to IR. The current across the 3 ohm is going to be 10.5 divided by 3. 10.5 divided by 3, which is 3.5. And then the total current through here is not the same as 1.5. So 1.5 comes when I combine the two, I'll get my total current. So it's saying 3.5 plus 1.5, which gives us the 5 amps. Okay, 5 amps. I feel this is shorter. And as much as someone that finds the effective resistance, okay, effective resistance within the parallel combination of 3 and 7, remember it's the product and the sum. So product over the sum, which will be 21 over 10. When the voltage is still the same, so the current is going to be voltage over resistance, which is 10.5 divided by 21 over 10. And simplify that, we should be able to get 21 over 10. Okay, it also gives us 5. Okay, so whichever way. So this is a bit long. This is quite cheap and quick. All right, so whichever option you choose, guys, for as long as we get the same answer, okay? Then 8.2.3. They're asking for the power that is dissipated within the 3 ohm resistor. Power dissipated within the 3 ohm resistor. Now, since we have the current of the 3 ohm, okay, the same current within the 3 ohm, we got it as 3.5. We have our resistance as 3. All we need is the formula of power, the equation of power that has current and resistance. Formula of power with current and resistance is I squared R. So which means it's going to be 3.5 squared, okay, times my 3. So when I simplify that, that is 3.5 squared times 3. I'm getting 36.75 watts. Alternatively, I can use the voltage approach where I have V squared over R, because you know the voltage across the 3 ohm is 10.5. Okay, and then I'll divide by 3. 10.5 squared divide by 3, I'll still get the same thing of 36.75 watts. So whichever option you take to use, we shall be happy for you. So that is 8.2.3. Then we move on to the next condition. S1 is open. Okay, so if S1 is open, which means our main focus is just the 3 ohm. Since which one is open and which one is closed? S2 is opened. S2 is opened. So which means S1 is closed, and we shall have just the 2 ohm and then the 5 ohm. So they're asking us to calculate. No, skip the question, guys. Sorry. S1 is opened while S2 remains closed. The reading of the ammeter changes to 3.64. Can we calculate the EMF? Okay. If S1 is open, which means these 2 resistors are out, we're just focusing on the 3 ohm. And the current through would be 3.64. So I feel there is a simultaneous that we can solve. Okay, this is 8.3. From the EMF formula, we know that it's current into capital R plus the small r. Okay, we don't know the value of the small r and all of that. So initially, our EMF would have been, we say the current, the total current that is passing through the circuit. What answer do we get for 8.2.2? 8.2.2, got 5. So that's going to be 5 into the effective resistance for the total circuit. Remember, this is a 3, that is a 7 combined. So the product is 3 times 7 over 3 plus 7, which is 21 over 10. 21 divided by 10 is going to be 2.1. We just use it as 2.1 plus R. I can simplify this further so that my EMF is going to be 2.1. 2.1 times 5. That gives us 10.5 plus 5R. I can call this equation number 1. And then now when I look at the condition that I've been given, the ammeter reading changes to that. So which means my EMF currently now, the EMF, the current is 3.64. The total resistance, so the resistance external is going to be just 3 ohms plus R. Open this up. I'm going to have 3.64 times 3, having 10.92 plus 3.64 R. I can call this my equation number 2. Since the EMF is the same, I can equate equation 1 and equation 2. So that my 10.5 plus 5R is equal to 10.92 plus 3.64 small r. Let me move the r's this side, let me move the constant that side. So 5 minus 3.64 is going to give me 1.36 r. And then 10.92, when I subtract 10.5 plus 3.64 times 0.009, I'm having 12.04 volts. 12.04. Our focus is now the 7 ohm combination. They're asking us, how does the voltmeter reading change? We need to choose increase, decrease, or remains the same. Okay, so what I can see is that looking at the combination, this was in parallel, okay? And we got the effective resistance to be 2.1. Now, if we remove the 3 ohm, the effective resistance is now going to be 7. In other words, the resistance external is going to be 7 ohms. So what I'm saying is that one, resistance is going to increase. Okay, the resistance is going to increase. And if resistance increases, what happens to the current? The current through the circuit decreases. Okay, which means the V external is going to decrease. But then the V internal, which means the IR, must increase to make sure that the voltage across or the EMF is maintained. So if the internal voltage increases, which means even the voltmeter reading is going to increase. Since remember, the voltmeter is connected across the battery source. Okay, let's answer the question. So say this is 8.4. 8.4, so saying it's gonna increase. Reason being that opening S2, you can say just cuts off the 3 ohm, hence increasing the resistance external, and this decreases the current in the circuit. Okay. Therefore, the V external will decrease, but then the V internal will increase. That's the increase in the voltmeter reading. That's the increase in the voltmeter reading. All right. Question number 9. They're telling us that the simplified sketch below represents an AC generator. So guys, remember, before we move forward, motors use the Fleming's left-hand rule. Before I forget, this is motors. Generators, they use the right-hand rule. Fleming's right-hand rule. Okay, with a coil that was initially horizontal between the poles of the magnet, X and Y are 2 points on the coil, YA is one of the poles of the magnet. All right. So the question is asking us that when the coil of the generator rotates clockwise, just as indicated, between the 2 poles, the direction of the induced current is from X to Y, okay? As shown above. Is A the North Pole or the South Pole? So remember what we did when we were looking at the multiple choice question. So if I focus on this and I apply my Fleming's right-hand rule, okay, I look at the current on that side, and then the direction is upwards, which means my force is going to be moving in this sort of direction. Okay, so since this is an AC generator, this is going to be our EMF measured in volts. And this can be the time in seconds. Since it's EMF, time graph for 2 complete rotations. But they are telling us that we must start from the position of the coil as shown. Okay, so when the coil is horizontal, that's when we experience the maximum EMF. Okay, so what I'm gonna have is something like this. Okay, that is one rotation. And then I'm gonna have another rotation, something like that. So that would be my EMF time graph. In the 9.2, they're telling me that an electrical device is connected to the AC generator, and then the root mean square potential difference across is 200 volts. So RMS is 200 V. Okay. And then the maximum current. Okay. Current maximum is 6 amps. What does the question want? They want us to get the resistance of the device. So before we get the resistance, I need to change this maximum current to the root mean square current. So IRMS is going to be the same as 6 over root 2. Okay, since we know that I max is the same as IRMS over root 2. Then from Ohm's law, V is equal to IR. Since I'm looking for resistance, it's the voltage over the current. So it's VRMS over the IRMS. So 200 divided by 6 over root 2. When I punch this into my calculator, 200, not 2000, okay, over 6. And that's the root 2. I'm having 47 for my 1.4 ohms. Okay, that is 9.2.1. The 9.2.2, they want us to get the energy that is consumed, energy that is consumed by the device in a time of 2 hours. So time is 2 hours. We need to change these 2 hours to seconds. That's 2 times 60 minutes times 60. Okay, what we get? That is 7.2 seconds. From the formula of power, we know that power will be the work done over the time. The work done over the time. Okay. What do we have? We have the power, current, and the voltage. We can use that. We want the energy. Okay, so one thing we know is that it will be the energy divided by the delta time, because we know that work done over time, we know that work depends on the energy. Okay, because under the definitions of energy, we will tell you that it's the ability to do work. That's why then the units are usually the same. So I'm gonna just put it that way, so that for me to get my energy, I'll get my power times delta T. So since I have my voltage and then I have my current, I also have my resistance, I can use any of it. So I'll prefer to use the IV and then delta T. So the current that I'm using is the root mean square RMS. So that is 6 over root 2 times the 200 for the voltage from the previous question. That's what we stated. Okay. And then I'm multiplying this by my time. We said it's 7.2. So simplifying this, put 2, okay, that's times 200, and then times 7.2. I'm getting something weird. Okay, getting something weird. Let me just punch it again. Okay, so my weird answer is 6.11 times 10 to the 6 joules. Okay, 6.11 times 10 to the 6 joules. So guys, that is question number 9. Let's move on to question number 10, which is photoelectric effect. So in an investigation of photoelectric light of different frequencies was radiated on each of the two metals, we have A and B. Then the graph of maximum kinetic energy of the ejected electrons from metal A and the frequency of the incident photons is shown. This is the energy. And then that is that frequencies times 10 to the 14. Then 10.1, they want us to write down the numerical value of the gradient of the graph. So it's a 1-mark question, which means it's kind of direct. So in any graph of photoelectric effect, the constant, which is the gradient in this case, is what we call the Planck's constant. Okay, and Planck's constant is usually given as 6.63 times 10 to the negative 34 units. Okay, 6.63 times 10 to the negative 34. That is the gradient. Then 10.2, they want us to define what work function is. Work function is basically the minimum energy. Okay, the minimum energy that is required. Minimum energy that an electron in the metal its minimum energy that an electron in the metal needs, okay, or the minimum energy that a metal needs for an electron to be moved off its surface. I don't know, that's better. Remember, work function is just the minimum energy, the minimum work that must be done to remove an electron from a metal surface. So whichever way you put it, but there has to be minimum involved. Minimum energy that is needed. Minimum energy needed to remove an electron from a metal surface. Okay. Then 10.3.1, they want us to get the work function of A. So usually where the graph starts from along the horizontal axis, that represents the minimum frequency or the frequency of the work function. So we know that work function W naught is given as H times frequency naught, because this 5 represents our frequency naught. So Planck's constant is 6.63 times 10 to the negative 34. Then we are multiplying this by, and so we're multiplying by 5 times 10 to the 14. Is that true? Yes. Okay, so what I'm going to do is just punch this into my calculator, 6.63 times 10 to the negative 34. I'm multiplying this by 5 times 10 to the 14. I'm having a weird answer, guys. Again, which is 3.32 times 10 to the 19, but negative. That will be joules, since it's work function, work done. Okay, so guys, we're done with, oh, we're not done. They told us the work function, okay? So we got the work function as 3.315 times 10 to the negative 19 joules. We know that our E is going to be H multiplied by the frequency is equal to the work function plus the EK max. Okay, so at a point of EK max, where we need our E, we can see that the frequency is 12.54. So I'm going to say 6.63 times 10 to the negative 34 times the 12.54 times 10 to the 14 is equal to our work function, which is 3.315 times 10 to the negative 19 plus the EK that we want. Okay, then we multiply on the left. I'm getting something like 8.314 times 10 to the negative 19 is equal to 3.315 times 10 to the 19 plus the EK. Then I can move this that side, and then I'll subtract. Okay. When I insert this into the machines, 8.314 times 10 to the negative. Okay, what's happening? Saying 8.31. We said 14 times 10 to the negative 19. Okay, we're subtracting 3.315 times 10 to the negative 19. That becomes 4.999 times 10 to the negative 19. So if I round these two decimals, it's just going to be 5 times 10 to the negative 19 joules. We're looking for kinetic energy. Okay, then the next question. The next question, which is going to be 10.4. 10.4. 10.4. Okay, so 10.4, how will each of the following be affected if the light of the frequency 12.54 times 10 to the 14 hertz, but of a higher intensity? So we're using the same sort of frequency light, but the intensity is the one that changes, okay? How will this have an effect on the value of X? So now one thing we need to know that under the factors that influence kinetic energy, intensity is not one of them, okay? So in this case, it's just gonna be the same. The kinetic energy is going to be the same. It has no effect on the intensity, or kinetic energy is not affected by intensity of the light. And then 10.4.2, how about the number of photoelectrons emitted per unit time? So this will increase. Okay, these are going to increase because as the intensity increases, which means the number of photons that are being released will also increase. Then 10, they are telling us that metal B has a larger work function than metal A. It has a larger metal function. It has a larger work function than metal A. Can you redraw the graph above in answer book, not include values? On the same set, sketch the graph of B and label this. So one thing we know that one thing that we discussed before, we said work function is directly proportional. Okay, said work function is directly proportional to the frequency. So if the frequency is high, which means even the work function is going to be high. And then if the frequency is small, which means even the work function is going to be lower. So from the graphs, okay, I don't need to draw. I'll just maybe just use this. If this is our graph A, okay, with this sort of work function, the graph B has a higher work function, which means it must be drawn somewhere there. And then we call this a B, because let's say if this is a frequency, if this frequency is high, which means even the work function is going to be high. So in your drawing, in your answer book, all you needed to do is just draw something like that and draw something like that. Call that A and call that B. So this is the frequency of A, and then this is the frequency of B. So guys, that's what we had to do, and that is what will be expected of us. So thank you very much for watching. Let's meet in the next paper. Thank you. Hello, welcome to this episode where we shall be talking about physical sciences, paper 1, the May, June 2023. The paper was out of 150 and the duration was 3 hours. Okay, the instructions will always be the same. The paper is having 10 questions. Each question will be 2 marks, okay? And as much as it's a multiple choice, but there is some bit of reasoning, some bit of calculations that might be involved. And it's usually a combination of all topics, so it cuts across, okay? And then from that, we shall break down some topics and also look at some sample questions that we can work with as we enforce, or we go into detail of what is really expected. Okay, so as per the weighting of the paper, we shall have mechanics. Mechanics is going to carry most of the marks, which is like maybe 65 plus minus, okay? And then the waves, sound, and light shall have 15 marks plus minus. Then electricity and magnetism will account for plus minus 55, and then matter and materials will go for 15 marks. Okay, so those marks will be cutting across all the levels, as we can see here, at least for level 1, level 2, 3, and 4. So the most complex is going to carry more or less the least amount of marks. Okay, so skills in physical sciences: identify the question phenomena, formulate an investigative question, and all of this. This is basically things that we always cover in classes, okay? Listing all the possible variables, a testable hypothesis, and so on and so forth. Okay, so under graphs, what we need to know, how to draw at least some graphs if you're given information. Okay, this normally comes under mechanics, where they ask for velocity time graph or position time, and even under electricity. Let's say that they've given you the relationship between current and then the voltage or the potential difference. And then how do you interpret them? That's also vital. And then how do you draw conclusions from those graphs? then calculations using 2 or more steps, and so on and so forth. And then the knowledge of grade 10 and 11 will be vital also, because we need to know some of those aspects, because when you look at some topics, most of the work that is usually tested is probably from grade 10 and okay, so I'll skip this part of the guideline, and then we look at how we elaborate the content. Okay, so these are the topics that will be covered. Number one, you look at Newton's laws and their application. Remember, we have quite a number of laws of Newton. Okay, so we have the laws of motion, and we know that these are law 1, law 2, and law 3. At least we should be in position to state them and even work around them, okay, especially with the formulas and stuff. Then we also have the universal law of gravitation. So those are the 4 laws that we mainly need to put our emphasis on. Okay, so below this, we have different types of forces. An example, we have weight, we have normal force, frictional force, applied force, tension, and so on and so forth. So we need to know how to at least define the normal force, okay? How do we define frictional force, and then static frictional force, and the formulas, and so on, okay? Then solving problems that deal with friction. So for as long as we know that our frictional force, whether kinetic or static, is the mu s and then the normal force. So this mu is basically the coefficient of the friction, static or kinetic. And then there's a note where they are telling us that if a force F applied to a body parallel to the surface does not cause the object to move, F is equal in magnitude to the static frictional force. And then the static frictional force is maximum just before the object starts to move. So static friction is basically that force that keeps the object in one place without any motion. So this formula is quite important as we shall move on. Then 2, we also need to know how to draw our force diagrams or the free body diagrams, okay? Because in almost all papers, there's always an element of draw a free body diagram, and those are marks that we should not leave out, okay? Just get all those marks. So draw the force diagram, draw the free body diagrams, and indicate the forces, and so on and so forth. So this, even the mark allocation should guide you. If they're giving you like 3 marks, we expect at least maybe 3 forces around, at least, which means the minimum should be 3 forces acting on that body. And then we need to remember how to resolve forces, okay, into the horizontal and then the vertical components. And then how do we determine the net force as well as the direction? Okay, then under Newton's first, second, and third laws, you need to know how to state the first law, which will be a body will continue in its state of rest or uniform motion unless a non-zero resultant net force acts on it. That's the way it is. Now, in most cases, there are certain keywords that are important, like 1, remain in a state of rest or motion. And then we also have constant velocity, and then the non-resultant. So this key statement, if some is shorting, then you'll probably be penalized. And then we also need to discuss why it's important to wear seat belts using Newton's first law. So this is more like the application. Okay, why is it relevant to wear seat belts? Okay, and then also when it comes to the airbags and so on and so forth. Then we need to know how to draw force diagrams, free body diagrams of that are in equilibrium or accelerating. Okay, apply the laws, moving on a horizontal plane without friction, with or without friction, and so on and so forth, okay? And then we also look at the 2 body systems. This is usually something that they like, okay, as examiners. Then state Newton's third law, that when an object A exerts a force on object B simultaneously also exerts opposite, and so on and so forth. Then be able to identify the action-reaction pairs and then list the properties of those pairs. And then there was Newton's second law, iron state. but we also need to remember it. Okay, because that is the F net one. Okay. Then we also need to know Newton's law of universal gravitation. They hardly ask this under structured, but under multiple choice, it's usually an if. Okay. Know how to state the law itself and then the formula itself. Okay. Then describe weight as a gravitational force the Earth exerts on any other object. How do we calculate weight? Is the product of mass and the gravitational force. Calculate the weight of an object on other planets and all of that. Distinguish between weight and mass. This is also something that is always an issue with people. So remember, mass is basically the measure of content within an object, and then weight is just the product of mass and then the gravitational force. So explain weightlessness. So that is more like a feeling, weightlessness. Like an object does not have a normal force. Okay. Shall go into detail if we come across a question of that sort. The next, still under mechanics, we need to look at momentum and impulse. How do we define momentum? Okay. How do we describe linear momentum as a vector quantity with the same direction? How do we calculate momentum of a moving object? There is the formula, and we also have such formulas on the formula page at the back, okay? How do you describe the vector nature of momentum and then illustrate this with examples, draw the vector diagrams, and so on and so forth, okay? There we are, Newton's second law. So this and momentum usually go hand in hand. Okay, so how do you state Newton's second law? There are still keywords, okay? The net force acting on an object is equal to the rate of change in momentum and so on and so on. Okay, so this is just a simplified version of the momentum. And then there's that other one that talks about proportionality and so on and so forth. So F net from Newton's second law will be given as this, the rate in change in momentum over the change in time. Then we need to explain how does the net force and change in momentum of various motions occur. And then how do we calculate the change in momentum? That is P final minus P initial. So momentum final minus momentum initial will give us our change in momentum. Okay. Then we also need to at least understand the effect that will be caused as we increase in the direction of motion, especially with the rocket engine fires. What happens with the decrease if brakes are applied, if we have some sort of reverse direction or reverse motion, what goes on, okay? Then next we have impulse, and we know that impulse is the product of the resultant net force acting on an object as well as the time. So force times time can be F net. Then we have this formula. We just need to remember how it works, how it goes. Then explain the concept of impulse as it applies to safety consideration in everyday lives like airbags, seat belts, and then arrestor beds, okay? Then we have conservation of momentum. So in this, you just need to explain or state the law of conservation of momentum, okay? Then an isolated system, you just need to know it. Okay, you need to know what a system is, and then internal and external forces. That is basic that we need to know. So this we need to know, okay, know how to state this, that the total linear momentum of an isolated system remains constant. Then we need to know how to apply this and then distinguish between elastic and then inelastic. So the confusion usually comes when they say, I've seen learners giving reasons like inelastic is when objects collide and then they separate and move separately after the collision. That is wrong. Okay, it's not more like elastics in clothes and rubber bands as no, it's completely different. In this case, remember momentum from the law of conservation. Momentum is always conserved for both elastic and inelastic. The only difference lies within the kinetic energy. Okay, so kinetic energy within the elastic is conserved. Okay, within the inelastic, it's not conserved. So what we mean by this is that the EK initial is equal to the EK final when we're talking about the elastic collisions. If it is inelastic, okay, the EK initial is not the same as the EK final. Reason for that, there is probably loss of energy through sound, through heat, or even light. That's why the energy will not be conserved and bodies will be considered inelastic if this condition is met. Okay. Then still under mechanics, we have the vertical projectile of the VP, and in grade 12, we only focus on the 1D, okay, one dimension. So explain what a projectile is: an object with an initial velocity and then moves under just the influence of gravitational force. Define free fall, okay, just know the difference between a projectile and then free fall. Then use the equations of motion and know which one exactly to use, okay, based on the given information of variables. We need to know how to sketch the position time graph, velocity time graph, and then the acceleration time graph, okay? So you can always revisit some of the videos that we've done before when we're explaining some of this content in detail, okay? So we need graphs for a free-falling object, for an object that is thrown upwards, object that's thrown downwards, and then an object that is bouncing, okay? So from the graphs, we also need to know how to determine the position, the displacement, the velocity or acceleration at any time, okay? Then still from the graphs, we need to look at the motion of bouncing, thrown vertically upwards, and then basic, okay? Then we have the work, energy, and power. Define what work done is, and then the constant force and how it works. Then we need to be able to draw force diagram and free body diagrams, usually on the incline. Calculate the net work done on the object, distinguish between positive net work and then the negative, okay? Work done on the system and then the work done by the system. Then we love this, the work energy theorem. You need to know at least how to state it in words and then how to apply it under the calculations, okay? So you need to apply it to horizontal, vertical, and then inclined planes. And then the conservation of energy. So it's a two-way. Number one, you need to define what conservative force is. The force for which work done in moving an object between the 2 points is independent of the path. An example, you look at the gravitational force, the elastic force in a spring, and then the electrostatic force. So these are automatic. Directions are just having not, let's say, the directions are already determined in which the work is going to be done. Okay, that's why we say that the direction is independent. In other words, the work does not depend on the direction because we already know what's going to happen with the directions. Then the non-conservative, saying which work done in moving an object between will also depend on the path. An example, frictional force. We know that the direction of friction will always depend on the motion. Okay, so if the motion is moving east, friction must move west. Okay, and so on and so forth. And then we should be able to state the principle of conservation of mechanical energy. So mechanical energy is just a combination of the EK and then the EP. Okay, the gravitational and then the kinetic. So this usually applies to an object that is midway, okay, from the point of projection towards the end point. So in between, that's when it has both the EK and the EP. So they're telling us to solve conservation of energy problems. We can use this. The change in EK plus the change in EP, we get our that. And then I use the relationship above to show that absence of non-conservative forces, mechanical energy will always be conserved. And then power, Like we define power as the rate at which work is done, expanded, and then use this formula, calculate the power involved, perform calculations, and so on and so forth. So I'm going to stop here with just this guideline for now. Let me just look at the sample questions, and then we shall come back and carry on with our expectations. Okay. Now I'll start with the multiple choice, in as much as most people, I don't know, feel it's kind of obvious with the multiple choice. Let me choose this. Okay. So in this case, options are always given. Okay, you just have to choose what is correct. Now, you can use different options to answer these multiple choice questions. So you can, there's an option of elimination. Eliminate what you feel is wrong, and then you'll be left with the correct answer. Or if you know what is going on, just go straight to the correct answer and then circle what is left. Okay. So the question tells us that a car is moving at a constant velocity. It's even in bold. Which of the following statements about the forces acting on the car is correct? 1, the net force acting on the car is 0. 2, there are no forces acting on the car. The weight of the car is equal to the normal force acting on the car. And then there is a non-zero net force acting on the car. Wow. So one thing we know is that for as long as a car is moving at a constant velocity, which means the V final is the same as the V initial. Let's start with option number 1. They're telling us that the net force, how do we calculate net force? F net is equal to MA. Okay, and we know that M is the mass, this is the acceleration. So literally, for as long as the velocity is constant, there is no change that is happening within the velocity. So which means our acceleration is going to be 0. We know that acceleration is given as the change in velocity over the change in time. Yes, time will be there, but then the change in velocity is going to give us a 0. So for as long as the acceleration is 0, which means the net force is also 0. So I feel like this option is the correct option. Okay, so I already have a correct option. So these ones, there are no forces, that's wrong. I mean, there's always a force that must push the car forward. Okay, and then there's always friction that must try to bring the car down. And then the weight of the car is equal to the normal force that is acting on the car. I mean, this is okay, this is true. But then we're talking on a car we're talking about a car that is moving. This is possible if the car is stationary and there's nothing else. And then there is a non-zero net force. No, this is wrong because we said the net force is a 0. So option A would be the best suited for that. And then 1.2, a ball is projected vertically upwards. We ignore resistance. Which of the following statements about acceleration of the ball at its maximum is correct? Statements about acceleration is correct. So we know that for as long as a ball is projected back upwards, there is just one acceleration, which is G. It's more like the influence is just gravitational force, but in which direction? So gravity just acts downwards, regardless of the position of the ball. So acceleration is 0, no, this is out. G, now that the acceleration is G and then it's directed downwards, which is the correct direction, and G. G directed upwards, no. G directed horizontally, no. G will always be directed downwards. Whether the object was vertically up or vertically down, regardless of the initial direction of projection. Then 1.3, we have a graph that is not to scale, the relationship between the gravitational force and then the mass and its distance. Okay, so this is the distance, this is the force. They are telling us that the magnitude of the force at a distance r is F. Which of the following statements is correct? for the magnitude of the force X. Okay, so if the distance is now 6 times bigger. So what do you suggest? Okay. So from the universal law of gravitation, m1, m2 divided by r squared. So we know that if it is r, just capital R, this is going to be the force because F is going with capital R. Now, what if we increase this to 6? So that's going to be G m1, m2 over 6 R but squared. So we know that 6 squared is going to give us 36R squared. So if I exclude this, okay, I'll be left with just 1 over 36F. So this whole thing represents F. So 1 over 36F should be the correct option. Now that's the force. For as long as you increase the distance, the force must also decrease. So D is the best option for this. Then ball M, moving at a speed v to the right, collides with a stationary ball N on the smooth surface. Immediately after collision, ball M comes to rest. And then N moves to the right with a speed v. Which of the following about the collision is correct? 1, total momentum is conserved, and then the masses are unequal. So the first statement is correct. Okay, but then how do we tell about the masses? The fact that the speeds are the same after and before, because this is, one is at rest, the other one is moving with v. After the collision, this one loses the velocity and then just goes to rest, and then this one moves off. So there's no way that the masses are unequal. There has to be something unique. Chances are high that the masses are the same because it's more like looking at balls of equal masses, and then this one carries the same velocity or carries a velocity v, and then this one just transfers the velocity to that one. And then this one moves off with the velocity. So the masses have to be the same for the velocity to be the same. So total kinetic energy is conserved and the masses are unequal. This is not making sense. I'm not at peace with it. I don't know. I'll see. Let's see. Total momentum and total kinetic energy are conserved, and then the masses of the balls are equal. I'll go with C. Why? Because of the masses being equal. But also D has masses being equal. Okay. Total momentum is conserved and total kinetic energy. So what sort of collision is this? It definitely has to be elastic collision. Why? Because it's going to be m1v plus 0 is equal to m2v plus 0. So momentum will be conserved. What about the EK? Same story with the EK. It's going to be m1v squared, and that's going to be m2v squared. Now, for as long as the masses are the same, it means so C is the best option. Because this one is telling us momentum conserved, kinetic energy is not. So C is the best. Then 1.5, a small stone is dropped from rest and undergoes free fall. Which of the following below shows the correct gravitational potential and V and so on? A stone is dropped from rest, undergoes free fall. So we know that with the energy, if it is at the highest point, it's going to have EP max. And then at the bottom, where it reaches the ground or the surface, it's going to have EK max. So if it's EP max, this is going to be EK minimum. Now I say 0. Then if it's EK maximum, then EP will be minimum. So EK. Okay, both graphs, that is that, starting from there, going that side, which is okay. This one and that, which is still fine, makes sense where the graphs are starting from. This and that, okay, this and that is also fine. So all the graphs represent the correct orientation of the EP max and the EK minimum and so on and so forth. Now let us look at some other aspect. Okay. So how will these graphs look like? So chances are high. These graphs are not going to be straight lines because the change that is happening within the energy is not uniform. So I'm going to cross this. I'm going to cross this out because it has a straight line. Let me just focus on just these two. Okay. So if the energy is being lost from the EP, is it going to be this much or this sharp? In other words, is it going to be an inverse proportion? Chances are high it won't. Is the EK going to increase exponentially? Which is correct. So we can see that these two have the same type of graphs. Actually, 1, 2, 3. The EK is just the same. So the issue is for us to highlight the correct E. So I'll go with option C for number 5. Then 1.6, the stationary passenger at a railway station listens to a train approaching at constant speed. So this is Doppler effect. Which of the following is correct for the sound of the approaching train that is heard by the listener? Okay. So for as long as the source is approaching, we expect the listener to get the most, the loudest sound. Okay, and if the sound is the loudest, which means it has to be a higher pitch. And for as long as the pitch is high, then what's going to happen to the frequency? Let's first look. So this one is out. And then the last option is also out. So that is lower pitch. Now, the observed frequency, since the source is approaching, should also be more because you tend to hear more of the noise or the sound. So higher pitch, higher frequency. Because pitch is how high or how low a sound note is. Then 1.7 particle P and Q, as well as R, have charge of 2Q, separated by a small distance R. Which of the following statements below allowed about electrostatic forces, FPR, which P exerts on R, and FRP, which R exerts on P, is correct? So we're being told particle P has a charge of Q, and then particle R has a charge of 2Q. They're separated by this. They want us to tell about the forces between FPR and FRP. Now, without even doing calculations or what, okay, we can start with that. You know that the force will be K, Q1, Q2 over R squared. That's K. In this case, we have a Q. We're going to have a 2Q over a distance R squared. So which is 2AQ, Q1, Q2 over R squared. Does it make sense? Doesn't matter. Doesn't matter. This is relevant. We know that if two bodies are being separated, the forces that will exist between them will be the same, but just in the opposite direction. So FPR must be the same as FRP. So this is out. I'll take this out as well. I need to have the same values. So we have this option and this option. So which one do we take? I'm going to go for the last option. Why? Because if P is experiencing a force as to Q, let's say the force will be in that direction, and then this one's force will be in that direction. Okay? The forces have to be the same, but opposite from Newton's third law. Okay, then 1.8, so the same thing applies to universal gravitation. So will be the charges. 1.8 is electricity, battery of EMF of that and that. Negligible resistance, there's an internal what resistance and so on. So which of the following combination about the ammeter reading will be correct when the switch is closed? Remember, ammeter reading is giving us the value of the amount of electricity that is flowing within the entire circuit. Okay, let's look at option A. Ammeter only reads the current in R1. This is wrong. Because remember this, where the ammeter is located, it's going to read the current of the entire circuit, which means this current that is passing through R1 and R2. I don't even need to, wait a minute. Why am I doing it like that? Let me read nice. They're telling us if the switch is open. Okay. If the switch is open, will it make any difference? Ammeter reads only R1. It's still wrong. Because the moment you open or close the switch, I mean there's a connection through R1. It's not a big deal. Only thing is that there's just an alternative path of the electricity that side, or even a short circuit. Okay, so that is wrong because it's just not R1. R2 is part of it because the two tend to be in series, or I can say this whole part is in series with R2. So that is out. We're not going for that. Then ammeter. So this 7 is also wrong. Ammeter reads only the current in R2. That is wrong also because it's both. Ammeter reads the current in both R1 and R2, which is correct statement. Let's look at this side. If we close it, if we close this, ammeter reads the current in R1 and R2. No, it's not going to do correct. Because now, the moment you close the switch, there is no resistance here. There is resistance this side. So the current will just go through straight via that channel. So which means the only current or the only resistor to focus on is R2. I don't know. It's what's option 4, R1 and R2, and then just R2. So option D is the best. 1.9, the direction of an induced current in a coil of a generator depends on ... The length of the coil, the speed of rotation, direction of the magnetic field, the strength. So this is out. Does that make sense? 1.9. Saying it's out. Why am I saying it's out? Because it just stands out compared to the rest. Okay. How does the length influence direction? How does speed influence to? Doesn't. How does the strength of the field influence? No. So all these ones will just work on the amount of induced current or induced EMF. So C, the direction of the magnetic field. That will tell us more about the direction of the induced current. Okay, then 1.10, the work function of a zinc is greater than that of magnesium. Which of the following statements about threshold frequencies is correct? So remember, threshold frequency is just the minimum frequency needed to eject an electron from a metal surface. So the threshold of zinc is greater. So if zinc is having a greater work function, remember, work function is HF naught. So if the work is greater, which means even the frequency will be greater. So zinc than that of magnesium, that makes sense though. Makes sense. Threshold of zinc is smaller, no, both, no. Threshold of zinc and that are independent, no. So A would be the best. Okay, let's move on to question number 2. Okay, this mechanics now. A person pushes a lawnmower of mass 15 kilograms at a constant speed. Pay attention to this constant. So I know that the mass is 15 kilograms of a flat surface with a force of 90 newtons. So force applied is 90 newtons. And then it's directed along the handle. The handle has been set at 40. Okay, the horizontal, refer to that. And then they want us to draw a free body diagram for the lawnmower. Free body diagram for the lawnmower. So, when I look at the lawnmower, I can see that this force applied is in that direction, which can still be translated to that sort of direction. Then we have the weight, we shall have the normal force. And then is there friction? Definitely there has to be friction. Definitely, because it's grass. So with what I'm going to do, since it's 4 mass, so I need a minimum of 4 forces. So I can indicate my N, and then I can indicate my weight. I can indicate my F friction, and then the force applied, since it is just in that direction. So in most cases, we dislike components of forces, just want the forces themselves. Then 2.1.2, why is it correct to say that the moving lawnmower is in equilibrium? Okay, what would be the explanation? This for 1 mark. So we could say that it's in equilibrium because the lawnmower is moving at a constant speed. And for as long as the constant speed, the net force is 0. The left-hand side is equal to the right-hand side. The force being applied, which is just a component, should be equal to the frictional force. So we can say that it's moving. Okay, it's moving at a constant speed. Moving at a constant speed. Thus the acceleration. Thus the acceleration is 0. Okay. And then they want us to calculate the magnitude of the frictional force acting between the lawnmower as well as the grass. Okay, so since we already know that it's moving at a constant speed, let me just try to break this down. If this is a 40 with a horizontal, which means this is also 40. Okay, if I try to resolve this applied force into components, it's going to be in this sort of direction, down and okay, so it's going to be F, the sine of 40, this is going to be F, cos of 40. So looking at the number of forces that are acting on the lawnmower horizontally, I'll only have, I can start by saying F net is 0, or F net is equal to MA. Then my F cos of, it's fine, I can say cos of 40 should be equal to my frictional force. So that's a 90 times the cos of 40. Okay, so I put that into my calculator. I end up with 68.94. Okay, 68.94 newtons. Since the direction of motion is just horizontal, then we focus on the horizontal component. Okay, then the next part, they're telling us that the lawnmower comes to a stop. Okay, calculate the magnitude of the constant force that must be applied through the handle in order to accelerate the lawnmower from rest up to 2 in a time of that. So we have our V initial as 0. The velocity with which the lawnmower is moving is 2 meters per second, and then within a time of 3 seconds. Assume that the frictional force between the lawnmower and the grass remains the same as 68,9. What is the question asking for? Magnitude of the constant force that must be applied. Okay, so that does not take away, what do you call this thing? It does not take away the 40 degrees at which the applied force is acting. So you can start by determining the acceleration of the lawnmower itself, okay? We can say that our V final should be equal to V initial plus A multiplied by delta T. Okay, so our final velocity, if it's a 2, the initial is 0, because they told us that it's moving from rest. Plus now the acceleration multiplied by the 3 seconds. So when I divide both sides by 3, my acceleration becomes 2 over 3, which is a 0.6, I can say 7 meters per second. Okay, so that would be just the first step. Then if I apply, where should I write this? Let me just jot it here. If I bring in the F net is equal to MA, what I need is the constant force, which is F. But we know that the horizontal component has to be F, the cos of 40. So that's what I'm going to use. I'm going to say F applied minus my frictional force should be equal to the mass of the lawnmower. They told us the mass, which is 15 kilograms. Okay, multiplied by the acceleration that we just got up there. So this is going to be F applied, the cos of 40, minus our 68,94. Okay, should be equal to 15 multiplied by, let me use 2 over 3 straight away, just to avoid the decimals. So this is going to be F cos of 40 is equal to, that's going to be a 10, because by 3, 1 by 3 is 5. So 10, when I add that, I'm going to have 78,94. And then when I divide both sides by the cos of 40, so 78, okay, divided by the cos of 40, I end up with 103.05 newtons. So that should be our force applied. All right, so that is that. That is that with that question. Then 2.2. A planet Y has a radius, okay, of this much, and then a 10 kg mass weighs 20 newtons on the surface of planet Y. Calculate the mass of the planet Y. Okay, so one thing we know about Newton's law of universal rotation is that the force that is experienced between the bodies must be the same. Okay, so regardless of how big or how small it is. So if a 10 kg is experiencing this much of force, which means the 10 kg must also apply this much of force onto the planet Y. So from F is equal to G M1, M2 over r squared. So which means my force is going to be 20. The question wants the mass. So if I called my G to, no, I know my G from the information table, 6,67 times 10 to the negative 11. I'm multiplying it by the 10, multiplying it by the mass of y, and then they told us the radius is 6, that's just going to have 6 times 10 to the 5. Everything must be squared. Okay, so I can simplify the right-hand side, can exclude that my. So 6,67 times 10 to the negative 11. Okay, I'm multiplying it by 10. And then I'm dividing everything by 6 times 10 to the exponent of 5. That's squared. That's giving me 1,85. To 8 times 10 to the negative 21 my. And then I have to divide both sides by that. So I'm going to say my 20. Let's just have that. And then we're saying 20 divided by my answer. I'm getting 1,079, so which is like 0.8 times 10 to the 22 kilograms. Okay, guys, so that is question number 2. Then question number 3, we're being told that a ball is thrown vertically upwards, okay, with a velocity of v from the edge of the roof that is 40 meters tall. The ball takes 1,53 seconds to reach the maximum. Okay, so might is 1,53 seconds. Ignore that. Can we define free fall? So free fall is just the motion of an object under the influence. Okay, under the influence of gravity, or you can just say gravitational force. Then 3.2, calculate the magnitude of the initial velocity v. So it takes 1,5 to reach the maximum. So we know that at maximum height, okay, I'll say height max, the final velocity must be a 0. So I can use the first equation of motion. V final is equal to V initial plus the A delta T. So my V final, we say is a 0. V initial is what I want, but we know that G is going to be 9,8 multiplied by 1,53. Now, the direction that you use for the G will matter. Let me take downward to be positive, and since we're going up, I'm just going to use negative, okay? So then I have 0 is equal to V initial minus 9,8 times 1,53. That gives me 14,99. Then I'll move it that side. So my V initial is 14,99 meters per second, which is more or less the same as 15. I don't know. I'll just leave it as that. It's fine. Then 3.2.2, calculate the maximum height that is reached. So we can still use the effects that we have, that the delta T is 1,53. The V final is 0. And then we're looking for the displacement. So you can use, we can choose to use the V initial. Either way, we have to use the V initial, because if I look at my displacements, V initial multiplied by time plus a half G delta T squared. Either way, there is V initial. If I use V final squared, it's going to be V initial squared plus 2 multiplied by G delta X or delta Y. So either way, so let me use this second and say that my delta Y is going to be the V initial. My V initial is 14,99 multiplied by the 1,53. Now I'm going to use minus a half times 9,8 multiplied by 1,53 squared. Now you can use a plus, yeah, but then the value of the sign next to the G should be a negative. That's if you're using the same direction as my source. So 14,99, okay, times 1,53 minus a half times 9,8 times 1,53 squared. I'm getting 11, something. 11,47 meters. So that is the height, or the maximum height, 11,47. All right, so that is 3.2.2. Then 3.3, can we take the edge of the roof as the reference point? We need to determine the position of the ball relative to the edge of the roof after 4 seconds. So from this point of projection, if this is our 0 line, that's what it means to take it as a reference point. So after how long, or after 4 seconds, what will be the position of the ball? So I can still use the same formula of the delta Y, but where there's time, I can just use the 4 seconds. Is that okay with people? Good. So we said we're using the same formula. So delta Y is equal to V initial times delta T plus a half G delta T squared. Okay, my delta Y. So let me just correct this, guys. It's supposed to be A. Let me even correct this. It's supposed to be A because A is the formula. We don't have G in the formula. So let's write the formula down. You get that mark. And then the substitution, then you replace A with a G. Okay, so V initial, we said is 14,99. Now we're looking at 4 seconds plus a half. That's going to be negative 9,8 times 4 squared. Okay, if I punch that into my calculator, saying times 4 plus 0,5 multiplied by negative 9,8 multiplied by 4 squared. That gives us negative 18,44. Okay, so one thing we need to know is as long as an object moves from the point of projection, reaches maximum and comes back to the point of projection, we call that a displacement to be 0. Then afterwards, this 18,44 is just the distance below the building or below the reference point. So we interpret the negative sign by telling us the position is 18,44 meters downwards, or we can say below the top of the building, below the edge of projection. Edge of projection. All right, then 3.4. We'll end of the answers in 3.2 and 3.3 change if the height of the building is now 30 meters. Choose a yes or a no. Now, looking at what we've been working with in 3.2 and 3.3. I mean, we've not applied this height in any way. Okay. So the fact that this 40 is not in any of our calculations and it does not have an effect on the maximum height that the ball must reach, I mean, there's not going to be a change. Because remember, we are ignoring air resistance. I mean, if air resistance was there, then we would say that yes, it might have a change. But since air resistance being excluded, our answer is going to be a big no. Okay, it's a no. And what is the reason? It's saying that motion of the ball is only independent. Should I say independent or dependent? Let's use dependent. Dependent on initial velocity. It does not depend on the point of projection or what. Okay. Then someone says, will that give you 3 marks? Yes, it will give us 3 marks. Remember, we took a stand to say it's a no. And then our explanation can give us the other 2 marks. All right, then question number 4. This is momentum. We also looked at it. They're telling us that a soccer player kicks the ball of mass 0.45 kilograms to the east. And then the ball travels horizontally at the velocity of this. Okay, I'll just write this there, 9 meters per second, along a straight line without touching the ground, and enters the container lying at rest. I mean, this soccer player should be a star. That's magic. Okay, then the mass of the container is 0.2 kilograms. And we know that its velocity is a 0. Then okay, maybe this 9 is here. Okay. The ball is stuck in the container after the collision. And then the ball and container now move together along a straight line towards the east. So the direction is still the same. Okay. Then they want us to state the principle of conservation. Okay. So remember what we said? That in an isolated system, okay, any isolated system, the total linear momentum stays constant or remains constant or stays the same or is conserved. Can use those things. And saying an isolated system, total linear momentum remains conserved. Okay. And then 4.2, they want us to calculate the magnitude of velocity of the ball and the container immediately after collision for 4 marks. So let's just use the principle of conservation. So I'm going to say that if I get the mass of the ball, velocity initial of the ball, plus the mass of the container, velocity initial of the container, must give me the mass of the ball plus the mass of the container multiplied by the combined velocity. Okay, so this is what we want. So the ball is 0.45. Okay, they told us it's moving at 9 east. Plus the mass of the container, it was 0.2, but initially it was at rest. This gives us 0.45 plus 0.2 times V. I'll say V final, it's fine. So this dies out to a 0. Then I'll be left with 0.45 times 9. That gives me 4.05 is equal to 0.65 VF. Then divide both sides by 0.65 over 0.65. That cancels that. So my VF is something like 6.23 meters per second. Okay, so that is 4.2. And then 4.3, determine by means of statistical calculation whether the collision between the ball and the container is elastic or inelastic. So remember what we said. For as long as a question of this nature comes, the first thing you need to go for is the kinetic energy. Okay, so go calculate the EK before, and then we also look at the EK after. So for the EK before, I'm going to say it's a half mass of the ball, velocity of the ball squared, plus a half mass of the container, velocity initial of the container squared. This is initial. When I do my substitution, it's going to be a half times 0.45 times 9 squared. This is going to die out because the initial velocity is a 0. So that's going to be 0.5 times 0.45 multiplied by 9 squared. That's giving me 18.225. So this is energy to be in joules. Then let's get the EK after, which will still be the same as a half. This is now going to be the combined mass since the two are moving together. Mass of the ball, mass of the container multiplied by the velocity that we got. So it's 6.23. We square that. Okay, so that's going to be a half. Mass of the ball was 0.45, but we saw the combined mass. Why am I stressing myself? Which is, we said 0.65 multiplied by 6.2 squared. What we get? Okay, multiplied by 0.65 multiplied by 6.2 squared. I'm getting 12.49. Remember, this was 18.225. This is 12.49. So just by looking at this, I can already see that the kinetic energies are not the same. And the fact that the kinetic energies before and after are not the same, therefore the collision is inelastic. The reason EK before is not the same as EK after. Okay. Question number 5. Here we saw also energy. So I believe this will be the last question. Then we go back to the guideline. Okay, a 70 kg box is initially at rest. Okay, at the bottom of a rough surface. This word is important. It's even in capital letters. At an angle of 30, okay, to the horizontal, the box is pulled up by means of a lightning eccentric string held parallel to the, okay, force applied is 700, good. What is the name given to the force in a rope? So all ropes, all strings, they usually possess one force, and that is the tension force. So the force there is tension. Please don't tell us force applied. It's the tension force. Okay. Then 5.2, give a reason why the mechanical energy of the system will not be conserved as the box is pulled up the plane. So the reason for this, okay, why energy is not going to be conserved, because the surface is rough. I mean, as you're trying to pull it up, friction is trying to pull the box downwards. So in that way, you'll have to cover up for the losses and all of that. So we can say that the presence of friction, the presence of the frictional force, we can also say the tension in the system. Both tension and frictional force will have an effect on that. Okay, then the box is pulled over a distance of 4 meters. So from here up to there is 4 meters. And then the kinetic frictional force between that is 178.22. They want us to draw a free body diagram as the box, or for the box as it moves up the incline. Okay, so with this, before I even draw the free body, just look at the forces that are going to be acting on the box, the way it is. So we know that this is going to be the force applied. Whenever we have an incline, it's automatically that the FG parallel will always act downwards. Okay, remember we said we don't want components, but I might be forced to put it. So frictional force is also going to act downwards. And then we're going to have the weight and then the normal force, the N up. How many marks is it? It's 4 marks. So if we can have just 4 forces, that will be good. Okay, so we're saying force applied, and this force applied is in the form of the tension. Okay, and then we can also have the frictional force, which is F. And then we say the normal force, and then we can have our weight, which is also okay. Alternatively, you could have the normal force, the tension, even this component, FG parallel, because it's acting downwards anyway. Okay, because our focus is just going to be the motion along the incline. So you could also indicate it the FG parallel. Okay, so that is the free body diagram. These two have to be in a straight line. I don't know why mine is Q. I know it's a weekend, but good. Okay. Then 5.4, they want us to calculate the work done on the box by the frictional force over the 4 meter. So from our formula page, we know that the formula for work done do we have it here? It should be here. So this formula here is what I'm going to use. Okay. So we're going to have W, work done by the frictional force. I'll just call it WF, is equal to F multiplied by the delta X and then the cos of theta. So my frictional force is 178.22 multiplied by the displacement, which is 4 meters. And then I'm going to use the cos of 180. Why are we using 180? We know that the object is moving up the incline. Okay. So up the incline will be our reference point, which is a 0. But then frictional force is acting on the opposite, which means it's acting within an angle of 180 in the opposite direction. Okay, that's why I'm using cos 180. So I punch that into my calculator. That's going to be 178.22 times 4 the cos of, we said 180. That's correct. So that's going to give us negative 712. Okay, 88. Remember, this is work done. Work done is measured in joules. So the explanation for the negative sign is just the direction. It's acting in the opposite direction. All right, then 5.5, use the energy principle to calculate the speed of the box after it has moved 4 meters up. I need space, I need space. Okay, let's just explain this nicely. So, one thing we know about energy principles. Remember we said we have WNC is equal to the change in EK plus the change in EP. But we also say that the net work done should be equal to the change in the kinetic energy. Okay? So I think I can use this one for me. The net work done should be equal to the change in kinetic. So in that way, I'll have velocity involved straight away. So let me just scratch this out because I need space like badly. All right, so for the network, since the direction is up, and there's just one force that is working up there. So I'll look at the, let me not use that. We're saying net is going to be the work done by the tension, okay, plus the work done by the frictional force, and then the work done by the FG parallel, because from our free body we saw that FG parallel and F frictional force are acting in the same direction. Okay, let me just get this first. So work done by the tension is going to be 700 multiplied by 4 multiplied by the cos of 0, since it is acting in that direction. And then the work done by the frictional force, we already got it as 712,88. Then plus the work done by the FG parallel, we know that the force FG parallel is given as the mg sine of theta. Okay, so this theta is this angle of inclination. The cos theta here has to do with just the direction of motion.